The vast expanse of the universe is a cosmic treasure chest, brimming with secrets that challenge our fundamental understanding of reality. From planets that appear to defy the very laws of physics, to catastrophic cosmic events unfolding in ways that seem to elude any explanation, the night sky above us is far from a static, predictable backdrop. Instead, it is a living canvas, intricately woven with mysteries, each one waiting for the curious mind to decipher. As we look up, we are called to explore, to question, and to embrace the awe-inspiring wonders that lie just beyond our grasp. Today, we journey into the unknown, where the very edges of scientific inquiry are tested. We invite you to join us in this exploration, to challenge conventional wisdom and peer into the enigmatic wonders of the universe. One of the most captivating mysteries uncovered by modern science is the existence of rogue planets, planets that drift freely through the vastness of space, untethered to any star. These solitary worlds, without the warmth and light of a stellar parent, have intrigued scientists for decades. Their elusive nature raises profound questions about the origins of planets and the dynamic forces that govern the cosmos. Rogue planets have long been the subject of intense study, and compelling evidence for their existence has emerged from a variety of observational techniques and theoretical models. One of the most intriguing sources of evidence comes from a phenomenon known as gravitational microlensing. This occurs when a rogue planet passes in front of a distant background star. The planet's gravity bends the light emitted by the star, temporarily brightening it in a manner akin to the magnification effect of a lens. Over time, astronomers have detected several such microlensing events, revealing the presence of objects that seem to be wandering through space without orbiting any star. This has provided strong evidence for the existence of these enigmatic, free-floating planets. In addition to microlensing, direct imaging techniques have also played a pivotal role in the discovery of rogue planets. With the advent of cutting-edge telescopes equipped with state-of-the-art technology, astronomers are now able to capture the faint light emitted by these wandering worlds. In some instances, these direct imaging surveys have led to the identification of objects that appear to be planets, but without the familiar gravitational pull of a star. These discoveries add a new layer of complexity to our understanding of planetary systems, and force us to rethink what we know about the processes of planetary formation and the stability of planetary orbits. Theoretical studies offer further insights into how rogue planets come into being. One leading theory suggests that some of these planets were once part of established star systems, only to be ejected due to violent gravitational interactions with larger celestial bodies. Others, however, may form entirely in isolation. In these cases, rogue planets are believed to emerge in regions of space where conditions are favorable for planet formation, but where no nearby star exists to anchor them. This new perspective is helping astronomers piece together the complex dynamics behind the formation of these mysterious starless worlds. The discovery of rogue planets forces us to expand the boundaries of our knowledge, raising fascinating questions about the scale and diversity of planetary systems throughout the universe. How many more of these solitary planets might be wandering through the vastness of space, lost to any known system? What role do they play in the greater cosmic landscape? As each new discovery is made, it adds another piece to the puzzle of planetary formation, migration, and the architecture of our galaxy. Our understanding of these rogue worlds expands, providing valuable insights into the broader mechanics of the universe. Meanwhile, the field of exoplanet research continues to make remarkable strides. Exoplanets, planets that exist beyond the boundaries of our solar system, have become one of the most exciting frontiers in modern astronomy. Discovering and studying these distant worlds requires a combination of advanced technology, cutting-edge instruments, and unparalleled scientific insight. The techniques used to detect exoplanets have evolved over the years, with several methods now employed to uncover the secrets of these far-flung worlds. One of the primary methods used to detect exoplanets is the transit method. This technique relies on the simple yet powerful principle that when a planet passes in front of its host star, it temporarily dims the star's light. By monitoring this dimming effect, astronomers can infer the presence of the planet, as well as important details such as its size and the nature of its orbit. This method has been responsible for the discovery of thousands of exoplanets, offering a window into the diversity of planets that exist in our galaxy. Another significant technique is the radial velocity method, which takes advantage of the subtle gravitational tug that a planet exerts on its host star. As a planet orbits, its gravity causes the star to move ever so slightly, leading to detectable shifts in the star's light spectrum. By carefully analyzing these shifts, astronomers can determine crucial information about the planet's mass, its distance from the star, and its orbital characteristics. This method has been instrumental in uncovering the properties of exoplanets, providing valuable data for scientists working to understand planetary formation and the dynamics of distant star systems. In recent years, direct imaging has emerged as an exciting new avenue for studying exoplanets. Unlike the transit or radial velocity methods, direct imaging aims to capture actual pictures of planets, providing an unprecedented level of detail about their physical properties. This technique is incredibly challenging due to the vast distances involved and the overwhelming brightness of the stars that surround these planets. However, advances in adaptive optics and coronagraphs, specialized instruments that block out the star's light, are making it increasingly possible to directly observe exoplanets in their natural environments. As our understanding of exoplanets deepens, so too does our appreciation for the incredible diversity of planets that populate our galaxy. From Earth-like worlds that might harbor life, to gas giants and icy moons that challenge our notions of habitability, the study of exoplanets continues to shape our view of the universe and our place within it. Through these methods, scientists are unlocking the mysteries of distant worlds, and each new discovery brings us one step closer to understanding the full scale of the cosmos. In recent years, advancements in space exploration have provided groundbreaking insights into the vast universe beyond our reach. One of the most important tools in this endeavor has been space-based observatories, such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. These sophisticated instruments are designed to monitor numerous stars continuously over long periods of time, offering scientists a powerful means of detecting even the slightest fluctuations in starlight caused by orbiting planets. Through these cutting-edge methods, astronomers are uncovering a hidden universe of exoplanets, many of which may possess conditions suitable for life. This is expanding our understanding of the cosmos in profound ways, revealing an astonishing diversity of worlds that were once beyond our wildest imaginations. One such exoplanet that has captured the attention of the scientific community is K2-18b, which stands out as a promising candidate in the search for habitable worlds. Located approximately 133 light-years away in the constellation Leo, K2-18b orbits a cool dwarf star and is classified as a super-Earth. This category of exoplanet is characterized by having a mass greater than Earth's but less than that of the giant planets in our solar system, such as Uranus and Neptune. K2-18b's remarkable characteristics suggest it could harbor conditions favorable for life, a notion that has sparked considerable excitement among astronomers. What makes K2-18b particularly intriguing is its location within the habitable zone of its star, the region where temperatures are just right for liquid water to exist. Water, as we know, is essential for life, and the potential discovery of liquid water on this exoplanet could dramatically increase the likelihood that K2-18b might host life forms. More recent observations have hinted at the presence of water vapor in its atmosphere, a further indication that K2-18b may indeed have the right conditions to support life, even if those life forms are vastly different from what we experience here on Earth. The study of K2-18b's atmospheric composition is currently a priority for scientists, who are keen to explore whether the atmosphere contains other important molecules, such as methane or carbon dioxide, that could suggest biological processes. Furthermore, K2-18b's larger size gives it a significant advantage in retaining its atmosphere compared to smaller planets, a characteristic that could help sustain a complex and diverse climate system. Such a climate might provide a variety of environments where life could thrive, adapting to different conditions over time. The exploration of K2-18b is a perfect example of the exciting frontier of exoplanet science, where each new discovery brings us closer to understanding the nature of distant worlds and the potential for life elsewhere in the universe. As telescopes and technology continue to improve, scientists are optimistic that even more secrets will be uncovered, providing us with a clearer picture of our galaxy's habitability and offering hope that we are not alone in the cosmos. In contrast to planets like K2-18b, hot Jupiters represent an entirely different category of exoplanet that challenges our understanding of planetary formation. Hot Jupiters are gas giants that are similar in composition to Jupiter, but unlike the gas giants in our solar system, these planets orbit extremely close to their parent stars. In some cases, they complete a full orbit in just a few days, resulting in scorching surface temperatures that can exceed 1,000 degrees Celsius. This extreme proximity to their stars makes hot Jupiters starkly different from the gas giants in our solar system, which reside much farther from the Sun. The existence of hot Jupiters poses a challenge to traditional theories of planet formation, which suggests that gas giants should form in the cooler outer regions of a solar system, where solid materials can condense into larger bodies. Yet, hot Jupiters seem to have settled into orbits that are far too close for comfort. This anomaly has led scientists to reconsider their theories of planetary migration. One prevailing hypothesis is that hot Jupiters may have originally formed farther out in their solar systems and later migrated inward due to interactions with nearby material or the gravitational influences of other planets. This migration process is crucial because it plays a significant role in shaping the overall architecture of planetary systems. The study of hot Jupiters has also provided new insights into the atmospheric conditions of gas giants. These planets' thick atmospheres are exposed to intense stellar radiation, leading to chemical reactions and phenomena that are unlike anything seen in our solar system. The existence of hot Jupiters not only broadens our understanding of planetary formation, but also raises fascinating questions about the diversity of worlds that may exist beyond our solar system and whether any of them could be habitable in ways we have not yet imagined. Turning our attention closer to home, Venus, often referred to as Earth's twin due to its similar size and composition, continues to captivate researchers with its many intriguing characteristics. One of the most puzzling aspects of Venus is its extraordinarily thick atmosphere, which is composed primarily of carbon dioxide. This dense atmosphere generates a runaway greenhouse effect, causing Venus to be the hottest planet in our solar system, with surface temperatures soaring to around 470 degrees Celsius, hotter than Mercury, despite Venus being farther from the Sun. The extreme conditions on Venus raise important questions about its climatic history and the potential for volcanic activity on its surface. Evidence of vast lava plains and numerous volcanoes suggests that Venus may still be geologically active, although the nature of its volcanic activity remains a topic of intense debate. The planet's thick atmosphere and extreme temperatures make it a challenging environment to study. Yet scientists continue to investigate the possibility that Venus may have once had a more hospitable climate, or that it could even harbor signs of past life beneath its scorching surface. The study of Venus offers critical insights into the dynamics of planetary atmospheres and the potential for extreme climatic conditions to shape the evolution of a planet. By understanding the unique characteristics of Venus, researchers hope to gain valuable knowledge that could inform the search for habitable worlds elsewhere in the universe. Each discovery about Venus, K2-18b, hot Jupiters, and other distant exoplanets adds another piece to the puzzle of what makes a planet suitable for life, helping to reshape our understanding of the cosmos and our place within it. However, one critical question remains. If Venus is indeed volcanically active, how does it compare to Earth's volcanic activity? Understanding the volcanic history of Venus and its current state becomes essential not only for uncovering the planet's past, but also for shedding light on its climatic evolution. By exploring the volcanic features on Venus, researchers hope to unravel the mysteries of its atmosphere, its geology, and the potential links between these factors and the planet's extreme climate conditions. The volcanic activity on Venus could have shaped its dense, toxic atmosphere, which is primarily composed of carbon dioxide. This atmosphere, unlike Earth's, acts as a runaway greenhouse, trapping heat and making the surface of Venus hotter than that of Mercury, even though Venus is farther from the Sun. These extreme temperatures raise important questions about the planet's dynamic volcanic processes, which could still be occurring beneath its thick cloud cover. Moreover, scientists are captivated by the peculiar patterns of wind in Venus's atmosphere. The planet experiences superrotational winds that travel at speeds of over 300 kilometers per hour, around 186 miles per hour, far outpacing Venus's rotation rate. This extraordinary phenomenon prompts further inquiries into the underlying mechanisms responsible for such rapid atmospheric circulation. Understanding the dynamics of these winds could provide crucial insights into the planet's weather systems, its atmospheric behavior, and potentially even the planet's internal structure. Researchers continue to explore how these superrotational winds, which swirl around the planet at altitudes far above its surface, are influenced by the interaction between the atmosphere and Venus's harsh surface conditions. In addition to these atmospheric oddities, the discovery of phosphine gas in Venus's upper clouds has sparked heated debates about the possibility of microbial life. This gas, typically associated with biological processes on Earth, was detected in Venus's cloud tops, an area where the conditions might be more temperate and less extreme than the scorching surface. While the existence of phosphine on Venus remains a contentious issue, its discovery has prompted renewed interest in exploring the planet more thoroughly. Could life, or some form of biological activity, be thriving in Venus's harsh atmosphere? This question continues to fuel scientific investigation into Venus's potential as a host for life, albeit life unlike any we know. Despite decades of study, Venus remains an enigma, a planet that continues to surprise researchers, challenging preconceived notions and revealing new mysteries at every turn. Humanity's fascination with Venus, with its extreme weather systems, possible volcanic activity, and the tantalizing possibility of life, reflects our insatiable curiosity about the universe. Venus, with its opaque atmosphere and scorching surface, remains one of the most intriguing and mysterious objects in our solar system. In the outer solar system, ocean worlds such as Europa and Enceladus, moons of Jupiter and Saturn respectively, present revolutionary challenges to our traditional views of where life could exist beyond Earth. For centuries, scientists focused on finding extraterrestrial life primarily on planets located within the so-called habitable zone, the region around a star where temperatures are conducive to liquid water on a planet's surface. This idea shaped much of our understanding of life's potential on other worlds. However, moons like Europa and Enceladus have forced scientists to rethink this narrow approach. These icy moons, which orbit far from the Sun, harbor subsurface oceans beneath thick layers of ice. These hidden environments, kept liquid by tidal heating, the heat generated by the gravitational pull of their host planets, are now at the center of debates about habitability in the far reaches of our solar system. This discovery challenges our long-held assumption that life can only thrive in temperate, sunlit conditions on a planet's surface. It opens the door to the possibility that life may exist in dark, cold, and seemingly inhospitable places, thriving not under sunlight but in chemically rich, geothermally active environments. The possibility of life on these moons is further underscored by the discovery of plumes of water vapor erupting from Enceladus, as well as hints of geysers on Europa. These plumes suggest the presence of essential chemicals and nutrients necessary for life, including organic compounds, minerals, and energy sources. In fact, scientists now believe that the ingredients for life might be present in these moons' subsurface oceans. This revelation invites us to reconsider our understanding of life's prerequisites, shifting the focus from sunlight-driven photosynthesis to the potential of chemosynthesis, the process by which organisms derive energy from chemical reactions rather than sunlight. As research into Europa and Enceladus continues to accelerate, especially with advanced missions such as the Europa Clipper and proposed landers on Enceladus, scientists are moving closer to understanding how life might emerge and thrive in such extreme environments. These missions promise to provide new insights into the geophysical and chemical conditions that might make these moons habitable. The search for life is expanding our definition of habitability, suggesting that life could survive in conditions that were once considered far too extreme and alien. These findings also heighten the tantalizing possibility that we are not alone in the universe. They open the door to the idea that life might exist in forms we have yet to imagine, possibly even deep beneath the icy shells of distant moons. The discovery of water vapor plumes, organic molecules, and geothermal activity on these moons suggests that life might not be confined to Earth-like environments, but could flourish in radically different conditions. Closer to home, Mars, Earth's enigmatic neighbor, has captured humanity's imagination for centuries, especially with its potential for past or even present life. The red planet, which once may have had a warmer, wetter environment than it does today, continues to be the subject of intense scrutiny. Evidence suggests that Mars may have once harbored large bodies of liquid water on its surface, creating an environment where microbial life could have thrived. Although the planet is now cold, arid, and inhospitable, scientists speculate that Mars may still harbor signs of ancient life beneath its dusty surface. As we look further out into our solar system, these new discoveries on Venus, Europa, Enceladus, and Mars serve as a constant reminder of the vastness and complexity of the universe. Each of these worlds offers a unique window into the possibility that life, in some form, might exist in places we once thought uninhabitable, expanding our understanding of what constitutes a habitable environment and where we might find life beyond Earth. These ongoing investigations fuel our relentless curiosity and drive to explore the unknown, ever closer to answering one of humanity's oldest questions: are we alone in the universe? Evidence suggests that Mars, our neighboring red planet, was once home to flowing rivers, vast lakes, and perhaps even immense oceans. This idea, long speculated by scientists, is now gaining more traction thanks to a growing body of evidence. Features on Mars, such as dried riverbeds, ancient deltas, and mineral deposits that only form in the presence of water, hint at a time when liquid water was abundant on the surface. The discovery of these geological formations, combined with compelling data, leads us to a tantalizing possibility. Mars could have supported microbial life billions of years ago. As our exploration of Mars continues to evolve, space missions, most notably the Mars rovers, have uncovered even more clues that suggest the potential for life, or at least conditions conducive to life. One of the most intriguing finds involves dark streaks known as recurring slope lineae, which appear seasonally on Martian slopes. These streaks are believed to be caused by the flow of salty liquid water, making them one of the strongest indicators that liquid water may still exist, albeit in a frozen or briny state. In addition to these features, the Curiosity and Perseverance rovers have made groundbreaking discoveries on the Martian surface. Both missions have detected organic molecules in the Martian soil, compounds that are essential to life as we understand it. The presence of these molecules raises exciting prospects. Could they be evidence of past biological activity on Mars? And if microbial life once existed, could it have left behind traces that remain hidden beneath the planet's surface? Yet, the search for signs of life doesn't stop at organic molecules. Methane, a gas often associated with biological processes, has also been detected in Mars's thin atmosphere. This discovery is significant because methane can be produced by microorganisms, or it could arise from geological processes, such as the interaction between water and rocks. Interestingly, the levels of methane fluctuate over time, suggesting that there might be an unknown source or process at work, whether biological or geological. This ongoing mystery propels researchers to focus their exploration on specific Martian locations, such as ancient lake beds or regions with subsurface ice that could harbor hidden reservoirs of life. The more we learn about Mars, the more we realize how much we don't know. While Mars's past may have been warm and wet, the question remains: could it still harbor life today? As we peel back the layers of its history, we come closer to understanding not only the conditions that existed on our red neighbor, but also the broader, more profound question of whether life exists elsewhere in the universe. And with each new discovery, we inch closer to answering this cosmic riddle. Meanwhile, the mysteries of life beyond Earth extend to other celestial bodies in our solar system. One of the most captivating worlds in this regard is Saturn's moon Titan. Titan is unlike any other moon in our solar system. It is the only moon with a dense, nitrogen-rich atmosphere, and it is larger than the planet Mercury. This thick atmosphere, composed primarily of nitrogen and methane, creates a unique environment that has long intrigued scientists. Titan's atmosphere bears little resemblance to Earth's, and yet it could hold the key to understanding alternative forms of life. Perhaps the most groundbreaking discovery on Titan is the presence of lakes and rivers of liquid methane and ethane on its surface. This discovery forces us to reconsider our very definition of a habitable environment. While life as we know it relies on liquid water, Titan's liquid methane presents an entirely different possibility for sustaining life. Could life, in a form completely different from anything on Earth, thrive in these frigid, hydrocarbon-rich conditions? The discovery of complex organic molecules on Titan further deepens this mystery. These molecules, products of chemical processes occurring on the moon, resemble those that formed during the early stages of planetary formation. This has led scientists to wonder, could the building blocks of life, or even life itself, emerge under the most unexpected of circumstances? The study of Titan challenges our Earth-centric view of life and pushes the boundaries of astrobiology. As we explore this enigmatic moon further, scientists are considering entirely new forms of life, ones that might exist in chemical environments vastly different from anything found on Earth. Titan invites us to embrace the unexpected and think beyond our narrow definitions of what constitutes life. It serves as a reminder that when we search for life elsewhere in the cosmos, we must broaden our scope and entertain the possibility that life could take forms we cannot yet imagine. In the broader search for extraterrestrial life, another celestial body that has captured the attention of scientists is the exoplanet WASP-121b. This distant gas giant, located about 800 light-years from Earth, orbits extremely close to its host star, subjecting its atmosphere to intense, nearly unimaginable heat. The temperature on WASP-121b soars to an astounding 2,500 degrees Celsius, 4,532 degrees Fahrenheit, creating an environment that is nothing short of extreme. These conditions have led to the presence of evaporating metals in the atmosphere, an unprecedented phenomenon in the study of exoplanets. The atmosphere of WASP-121b has been found to contain elements like iron and magnesium, which exist as gases due to the extreme heat. This discovery provides scientists with an opportunity to study exoplanetary atmospheres in a completely new light. The intense heat and high-pressure environment on this planet likely cause complex chemical interactions in the atmosphere, creating unique weather patterns and chemical phenomena never before observed. Such discoveries broaden our understanding of the types of extreme environments that can exist on distant worlds. The study of planets like WASP-121b provides invaluable insights into how atmospheres behave under extreme conditions, and may eventually offer clues about how life, or the building blocks of life, could exist in hostile environments. The discovery of evaporating metals, in particular, hints at the possibility of entirely new types of chemical interactions and phenomena that are still poorly understood, but offer a wealth of new research potential. In conclusion, the ongoing exploration of Mars, Titan, and far-flung exoplanets like WASP-121b continues to rewrite the book on what makes a world potentially habitable. As we uncover more about these distant lands, we are forced to challenge our preconceived notions about life in the universe. These discoveries urge us to look beyond Earth for answers to one of humanity's oldest questions. Are we alone in the universe? Each discovery, whether on Mars, Titan, or an exoplanet millions of light years away, brings us one step closer to answering that profound question. And as we journey further into the cosmos, we continue to embrace the wonder and mystery that drives our quest for knowledge. WASP-121b, an exoplanet orbiting a distant star, offers a remarkable and extreme example of the unpredictable phenomena that can occur in planetary atmospheres. One of the most fascinating features of WASP-121b is its day-night temperature contrast, a result of the planet being tidally locked. This means that one side of the planet perpetually faces its star, while the other side is forever cast in darkness. As a consequence, the temperature disparity between the day and night sides of the planet is immense. The bright, sun-facing side reaches scorching temperatures, while the dark side remains bitterly cold. This dramatic difference in conditions creates an environment that is nothing short of extraordinary, with atmospheric winds capable of reaching speeds that are difficult to fathom. These powerful winds play a pivotal role in reshaping the planet's cloud formations and weather systems, creating a constantly changing, dynamic atmosphere. The insights that can be gleaned from studying such starkly contrasting conditions offer valuable knowledge not only for scientists studying exoplanets, but also for those focused on atmospheric science here in our own solar system. By analyzing the unique behavior of WASP-121b's atmosphere, researchers can refine our understanding of how extreme environments evolve, ultimately improving our methods of detecting habitable exoplanets and offering a clearer vision of how life might adapt to vastly different conditions across the universe. The study of exoplanets like WASP-121b serves as a critical stepping stone toward understanding the potential diversity of life-supporting environments beyond Earth. These extreme worlds may hold the key to answering fundamental questions about habitability, pushing the boundaries of what we consider life-friendly conditions. Through their study, we not only gain a deeper understanding of alien atmospheres, but also unlock the potential for discovering entirely new forms of life, expanding the very definition of what it means to live in a planet's environment. Further expanding the horizon of planetary exploration, scientists have hypothesized the existence of a unique class of objects known as rogue planets. These are planets that do not orbit any star, instead wandering freely through the cosmos. The origins of rogue planets are thought to be linked to the gravitational dynamics of planetary systems. They could have been ejected from their original solar systems due to interactions with larger bodies, such as other planets or stars. Some theories propose that there could be billions of rogue planets scattered throughout our galaxy, each with its own set of conditions that could potentially support forms of life, albeit in environments starkly different from the warmth and light provided by a parent star. The search for rogue planets is an exciting and challenging frontier in modern astronomy. These elusive worlds, which do not reflect starlight like typical planets, can be detected through a variety of innovative techniques. One of the primary methods used to spot rogue planets is gravitational microlensing, a phenomenon in which the gravitational field of a planet bends and magnifies the light from a distant star. When a rogue planet passes in front of a star, its gravity distorts the star's light, causing a brief brightening. This temporary increase in brightness is a clue to the presence of a hidden, wandering object. Observing such changes in light, astronomers can gather important information about the rogue planet's size, distance, and other characteristics. In addition to gravitational microlensing, scientists also turn to infrared surveys to detect rogue planets. These planets, lacking a star to reflect visible light, emit faint infrared radiation. Specialized telescopes can detect this heat, offering another clue to the planet's presence. By scanning the cosmos for these faint infrared signals, astronomers hope to uncover worlds that might otherwise remain unseen. Large-scale surveys, such as the Wide Field Infrared Survey Telescope, are critical tools in this effort, providing invaluable data to help researchers identify potential rogue planets. Computer simulations also play a crucial role in the search, helping scientists model how planets might be ejected from their original systems and where they might end up wandering through the galaxy. Combining observational data with theoretical models, the search for rogue planets becomes a more precise and ambitious undertaking, one that promises to reveal even more about the mysteries of planetary formation and evolution. In the grand tapestry of the cosmos, the study of rogue planets challenges traditional notions of what constitutes a planet. These dark, wandering bodies defy conventional expectations, offering a glimpse into a universe far stranger and more diverse than previously imagined. Equally captivating are neutron stars, some of the most enigmatic objects in the universe. Formed when a massive star runs out of fuel and collapses under the weight of its own gravity, neutron stars are a testament to the incredible forces at play in the universe. When the core of a star undergoes this collapse, protons and electrons combine to form neutrons, creating a dense, compact object composed almost entirely of neutrons. The result is a star with a mass comparable to that of our Sun, compressed into a sphere roughly the size of a city, with a radius of just around 10 kilometers. To grasp the scale of this density, consider that a single teaspoon of neutron star material would weigh as much as all of humanity combined. This remarkable density is due to the strong nuclear forces that bind neutrons together, preventing them from spreading out even under extreme gravitational pressure. Neutron stars also have incredibly strong magnetic fields, trillions of times more powerful than Earth's. These magnetic fields can lead to the emission of periodic radiation, making neutron stars visible as pulsars, objects that send out regular pulses of radiation as they rotate rapidly. These pulsars are some of the most intriguing objects in astrophysics, as they provide natural laboratories for studying the behavior of matter and energy under extreme conditions. Understanding the properties of neutron stars can also provide new insights into the fundamental forces of the universe, offering clues about gravity, nuclear physics, and the nature of matter itself. Lastly, black holes, which are perhaps the most well-known of all cosmic mysteries, form from the remnants of massive stars that have exhausted their nuclear fuel. As these stars run out of energy, they can no longer counterbalance the force of gravity, leading to a catastrophic collapse. The outer layers of the star are ejected in a violent supernova explosion, while the core compresses into a singularity, an infinitely dense point where gravity is so intense that not even light can escape. If the core's mass exceeds about 3 times that of our Sun, it becomes a black hole, defined by its mass, charge, and rotation. One of the most puzzling aspects of black holes is the so-called no-hair theorem, which suggests that black holes can only be characterized by these 3 properties. Any information about the star's original state or other characteristics is believed to be lost when it crosses the event horizon, the point of no return. This has raised profound questions about the nature of information in physics, with some theorists suggesting that information may be preserved in some way, even if it's not immediately apparent. The effects of black holes on their surroundings are nothing short of spectacular. Their immense gravitational pull can attract nearby stars, gas, and dust, creating accretion disks, dense, swirling rings of matter that spiral inward toward the black hole. As this matter is heated to extreme temperatures, it emits intense radiation, sometimes outshining entire galaxies. This radiation provides a unique opportunity for scientists to study the behavior of matter and energy in one of the most extreme environments known to humanity, shedding light on the fundamental laws of physics that govern our universe. Gravitational waves, those elusive ripples in the fabric of space-time, have become a cornerstone in our quest to understand the universe's most profound mysteries. These ripples, generated by catastrophic cosmic events like the collision or merging of black holes, are not just fascinating in their own right, they offer an entirely new way to observe the universe. Their discovery has opened a door to previously unimaginable possibilities, reshaping the way we study space and time. Since their first theoretical prediction by Albert Einstein in 1915, gravitational waves have been an enigma. Einstein's general theory of relativity anticipated that these waves would travel at the speed of light, stretching and compressing space-time as they pass through, creating infinitesimally small fluctuations that are incredibly hard to detect. Yet, despite the challenge in identifying them, the scientific community was undeterred. In fact, the prediction of gravitational waves gave rise to a new field of study, one that would eventually change our understanding of the cosmos forever. One of the key aspects of gravitational waves is their ability to reveal a wealth of information about celestial bodies and cosmic phenomena. Unlike traditional astronomy, which relies on electromagnetic radiation, light, radio waves, and X-rays, gravitational waves give us an entirely different perspective. They allow us to observe events that are invisible to conventional methods, such as the fusion of black holes or neutron stars. These massive collisions release energy on a scale previously thought unimaginable, sending shockwaves rippling through the universe. For decades, scientists speculated about their existence, but it wasn't until 2015 that the first direct detection of gravitational waves was made. This groundbreaking moment came from the Laser Interferometer Gravitational Wave Observatory, or LIGO, which captured the waves produced by the merger of two black holes located about 1.3 billion light-years from Earth. The waves were so faint that detecting them required cutting-edge technology, but the signal was unmistakable. This discovery not only confirmed a century-old prediction, but also marked the dawn of a new era in astrophysics, an era where gravitational wave astronomy would become central to our understanding of the universe. As researchers begin to probe these waves more deeply, they are uncovering unprecedented insights into the properties of black holes, neutron stars, and even the early universe itself. Gravitational waves offer a powerful tool for testing theories of gravity and delving into the very workings of the universe. By studying the mass, spin, and distance of astronomical objects, scientists can piece together the intricate history of their formation and evolution. With advancing technology, the study of these waves promises to unravel even more about the cosmos, possibly even upending our current understanding of the laws of physics. Yet gravitational waves are not the only cosmic phenomena to challenge our understanding. Another enigmatic event that has captured the attention of astronomers are fast radio bursts. These brief but intensely powerful bursts of radio wave energy have been a source of mystery since their first detection in 2007. What makes them particularly baffling is their extraordinary energy output. In the span of just a few milliseconds, a single burst can release as much energy as our sun does in an entire day. To put that into perspective, it's as though the universe is flashing a signal so powerful that it can outshine entire stars in the blink of an eye. The origin of fast radio bursts, FRBs, remains a subject of intense debate. These bursts seem to come from all directions, with some originating from billions of light years away. Their unpredictable nature and immense energy output have led to a variety of theories about their source. Some scientists speculate that they could be the result of collapsing neutron stars, while others suggest they might be signals emitted from distant galaxies. And perhaps the most intriguing possibility, could they be signals from extraterrestrial civilizations? The potential for discovery in this field is enormous, and each new observation adds layers to the mystery. Compounding the intrigue is the fact that some FRBs are not one-off events, but repeat themselves. The discovery of these repeating bursts has raised even more questions about their origin and nature. Are they part of a natural cosmic process that we have yet to fully comprehend, or do they represent something entirely new? The scientific community is buzzing with excitement, eager to unravel the truth behind these cosmic mysteries. As our technology improves and our methods of observation become more refined, we may soon uncover the true nature of fast radio bursts, perhaps offering a glimpse into the workings of the universe on a scale we've never imagined. As if these cosmic phenomena weren't enough to fuel our curiosity, there is another relic of the early universe that continues to captivate scientists: the cosmic microwave background radiation. This faint glow, present throughout the universe, is a snapshot of the cosmos just 380,000 years after the Big Bang. At that time, the universe was still in its infancy, having cooled enough for protons and electrons to combine and form neutral hydrogen atoms. Before this, the universe had been a hot, dense soup of particles and radiation. But as it expanded and cooled, photons, particles of light, could finally travel freely through space, creating what we now observe as the cosmic microwave background. This radiation is incredibly valuable to scientists because it provides a detailed snapshot of the universe's early state. The slight fluctuations in temperature and density across this radiation reveal key information about the distribution of matter and energy during this formative period. These minuscule variations are critical because they represent the seeds of cosmic structure, indicating where galaxies and larger structures would eventually form. In many ways, this radiation serves as the blueprint for the universe as we know it today, offering a direct link to its origins. Together, these phenomena, gravitational waves, fast radio bursts, and cosmic microwave background radiation, serve as windows into the mysteries of the universe. As scientists continue to explore and decode these enigmatic signals, we stand on the cusp of an exciting new era in our understanding of the cosmos. These discoveries challenge our existing models of physics, pushing the boundaries of human knowledge and inspiring us to look ever deeper into the vastness of space. In doing so, they remind us of the awe-inspiring complexity and beauty of the universe we inhabit. The cosmic microwave background, CMB, is more than just a faint echo of the Big Bang. It is an essential cosmic fingerprint that holds the key to understanding the universe's fundamental makeup. By examining the CMB, scientists can reveal crucial information about the universe's composition, such as the relative proportions of ordinary matter, and dark energy. These components are the unseen forces that govern the cosmos, and sophisticated tools like the Planck satellite have allowed astronomers to measure minute variations in the CMB's temperature. These subtle differences provide a detailed map that helps calculate critical parameters like the universe's age, curvature, and the Hubble constant, which defines the rate at which the universe is expanding. Additionally, this radiation aligns with predictions made by the theory of cosmic inflation. This theory suggests that the universe underwent an incredibly rapid exponential expansion in the moments immediately following the Big Bang. This dramatic growth shaped the structure of the cosmos and set the stage for the large-scale formations we see today. The consistency of the CMB's discovery has revolutionized our understanding of cosmology, offering a captivating glimpse into the universe's early stages, and continues to serve as an indispensable tool for unraveling the mysteries of its ongoing evolution. Supernovae, among the most energetic and dramatic explosions in the universe, are pivotal to our understanding of stellar life cycles and galactic evolution. When a massive star nears the end of its life, it can no longer maintain the balance required for nuclear fusion within its core. The outward pressure from fusion no longer counters the intense force of gravity, which causes the star to collapse in on itself. This catastrophic event results in a supernova explosion, a release of energy so intense that it can briefly outshine entire galaxies. But the significance of these explosions stretches far beyond the dramatic display of light. Supernovae scatter the outer layers of the star into space, enriching the surrounding interstellar medium with heavy elements like iron, calcium, and oxygen. These elements are the building blocks of planets, new stars, and even life itself. The energy expelled during a supernova also triggers shock waves that compress gas and dust, leading to the formation of new stars. Thus, supernovae are not only the end of one stellar life, but also the beginning of new ones. There are two primary categories of supernovae, Type 1 and Type 2. Type 1 supernovae occur in binary star systems, where one of the stars is a white dwarf. If the white dwarf accumulates enough material from its companion star, it can trigger a thermonuclear explosion. Type 2 supernovae, on the other hand, result from the gravitational collapse of a massive star that has exhausted its nuclear fuel. These two types differ not only in their explosion mechanisms, but also in the remnants they leave behind and the way they distribute elements across the galaxy. The energy released during these events is so powerful that it can trigger the birth of new stars, affecting the structure and evolution of galaxies in profound ways. The remnants of these cosmic detonations, neutron stars, or even black holes, play vital roles in shaping their galactic environments. They influence the movement of nearby stars and matter, adding another layer of complexity to the cosmic web. As astronomers study the aftermath of various supernovae, they uncover details about the conditions in the universe at the time of each explosion. These remnants act as markers in the history of the cosmos, offering us unique insight into the universe's past. In a similar vein, galactic cannibalism offers a stunning illustration of the dynamic processes that shape the universe's structure. Galactic cannibalism refers to the process by which larger galaxies pull in and absorb smaller galaxies through the force of gravity. These mergers play a central role in the growth and evolution of galaxies, dramatically altering their shapes, sizes, and types. The resulting interactions can lead to bursts of star formation, as the gas and dust from the smaller galaxy are compressed and heated. This process often gives rise to what are known as starbursts, periods of intense star formation that leave their mark on the surrounding galactic structures. The aftermath of such mergers can be seen in the formation of elliptical galaxies. These galaxies are typically smooth, featureless, and devoid of the spiral structure seen in younger galaxies. Galactic cannibalism also has the effect of removing gas and dust from the merged galaxy, which can stifle further star formation and reshape the galaxy's future. Over billions of years, these processes lead to the diverse array of galaxy types we observe today, from spirals to ellipticals to irregular galaxies. At a deeper level, galactic cannibalism highlights the interconnectedness of cosmic structures. The ongoing cycle of attraction, collision, and assimilation of galaxies illustrates the forces that drive the evolution of the universe. These interactions are a crucial part of the larger cosmic narrative, underscoring the delicate balance between creation and destruction that shapes the universe over time. Dark matter, one of the universe's most elusive components, remains a central mystery in cosmology. Though it does not emit, absorb, or reflect light, making it invisible to our current observational tools, dark matter is thought to account for approximately 27% of the universe's total mass and energy. Unlike ordinary matter, which we can observe through its interaction with light, dark matter interacts primarily through gravity. This invisible influence is detectable only through its gravitational effects on visible matter. One of the key pieces of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant objects passes near a massive galaxy or galaxy cluster, the gravity of that object bends and magnifies the light, creating a lensing effect. By studying these lensing effects, astronomers can estimate the mass of the foreground objects. Often, the observed mass exceeds what is visible, like indicating the presence of an invisible component, dark matter. Further supporting evidence for dark matter comes from the cosmic microwave background. The subtle fluctuations in temperature in the CMB reflect variations in the density of matter in the early universe. Analysis of these fluctuations shows that ordinary matter alone cannot account for the observed structures we see in the universe today. Dark matter must have played a critical role in the formation of galaxies and the large-scale structure of the cosmos. Though scientists are still working to understand the exact nature of dark matter, its presence is undeniable. It plays a fundamental role in shaping the universe as we know it, and continues to be a cornerstone of modern cosmological theory. As we search for answers to the mysteries of dark matter, we are also exploring the deeper nature of the universe itself, its origins, its composition, and its ultimate fate. Scientists have long been fascinated by the mysterious interaction between dark matter and visible matter, attempting to unravel the profound influence dark matter exerts on the cosmos. This area of research blends observational techniques with cutting-edge theoretical models to probe the universe's most enigmatic substance. Using advanced telescopes, scientists meticulously analyze cosmic structures and investigate how galaxies are distributed across the vast reaches of the universe. These insights are essential for understanding how dark matter shapes the universe we observe and provides us with an important window into the hidden forces that govern the cosmos. One of the key methods researchers employ involves studying the behavior of visible matter, such as stars, gas, and galaxies, within regions presumed to be influenced by dark matter. Since dark matter does not emit, absorb, or reflect light, its presence remains elusive. Instead, scientists detect its gravitational effects on surrounding matter. The bending of light around massive objects is one of the primary tools used to probe dark matter's influence. This phenomenon, known as gravitational lensing, occurs when light from distant galaxies passes near massive objects in space, such as clusters of dark matter. As light passes through these massive cosmic structures, it is bent, often distorting the images of the distant galaxies or even creating multiple images of the same object. By carefully studying these distortions, scientists can estimate the distribution and amount of dark matter in that region of space, providing invaluable insight into how dark matter interacts with visible matter. Another crucial element in dark matter research lies in the realm of computer simulations. Scientists create sophisticated models of cosmic evolution to simulate how both dark and visible matter influence the formation of galaxies and other large-scale structures across the universe. These simulations allow researchers to replicate cosmic events and observe how dark matter's gravitational influence shapes the evolution of galaxies over billions of years. By comparing the predictions of these simulations with actual observations made by telescopes and space missions, scientists can gather data about the ways in which dark matter structures evolve and affect the universe's grand architecture. This computational modeling offers essential tools to bridge the gap between theory and observation, further enhancing our understanding of dark matter. In addition to these methods, particle physics laboratories also play a pivotal role in the hunt for dark matter. Experiments conducted at the forefront of particle physics attempt to detect dark matter particles directly through rare interactions between dark matter and ordinary matter. These experiments often involve highly sensitive detectors that can identify faint signals from dark matter collisions or other forms of interaction. While such detections have not yet been conclusively made, they remain one of the most promising avenues for advancing our understanding of dark matter's true nature. Together, these observational, computational, and experimental approaches form a multifaceted strategy that continues to uncover the hidden forces shaping our universe. Among the most intriguing phenomena linked to the study of dark matter is the Great Attractor. This massive gravitational anomaly, located in the intergalactic space of the Laniakea supercluster, which includes our own Milky Way galaxy, is a colossal concentration of mass that exerts an immense gravitational pull on surrounding galaxies. Its gravitational influence is so powerful that it pulls galaxies across vast distances, including those in our local group and beyond, demonstrating the complex nature of cosmic dynamics. The Great Attractor is a prime example of the significant role dark matter plays in shaping the structure and motion of galaxies, offering crucial clues about the invisible mass that binds the universe together. While the exact details of this gravitational anomaly remain shrouded in mystery, its study has begun to reveal more about the nature of dark matter and its impact on the cosmos. The Great Attractor, by its very nature, challenges our conventional understanding of the universe's structure. It provides strong evidence that dark matter is not only responsible for the gravitational forces we observe, but also plays a central role in the larger-scale architecture of the universe, such as the formation of cosmic filaments and voids. Galaxies are not distributed randomly across space. Instead, they trace massive cosmic highways, vast filaments of dark matter that stretch across the universe. The Great Attractor lies at the convergence of these cosmic highways, shedding light on the way gravity governs the movement and clustering of galaxies. It serves as a cosmic anchor that ties together the universe's grand structure, revealing the hidden web of dark matter that permeates every corner of space. By studying the Great Attractor and its surroundings, astronomers are uncovering the intricate story of the universe's evolution. The gravitational interactions observed in this region help scientists to understand how galaxies move and evolve under the influence of dark matter. This research deepens our understanding of how large-scale structures such as galaxy clusters, voids, and filaments form and evolve over time, and how these structures shape the flow of cosmic matter. The study of the Great Attractor not only provides valuable insight into the role of dark matter, but also enhances our understanding of the fundamental forces that govern the large-scale organization of the universe. Meanwhile, another cosmic phenomenon that continues to captivate scientists is the mysterious and powerful gamma-ray burst. These bursts of energy, often described as some of the most extreme events in the universe, release more energy in a few seconds than our sun will emit throughout its entire lifespan. Despite their brief duration, gamma-ray bursts rank among the most enigmatic and awe-inspiring events in the cosmos. They are believed to result from catastrophic events, such as the collapse of massive stars into black holes or the merging of neutron stars. These cataclysmic processes release an enormous amount of energy, which is emitted in the form of gamma rays, making these bursts visible across vast distances. The origins and mechanisms behind gamma-ray bursts remain subjects of intense study, as their investigation offers important clues about the life cycles of stars, the formation of black holes, and the nature of the most energetic phenomena in the universe. Together, these cosmic phenomena, gravitational anomalies like the Great Attractor, the study of dark matter, and the mysterious power of gamma-ray bursts combine to paint a richer, more complex picture of the universe. As scientists continue their journey of discovery, they are not only delving deeper into the nature of dark matter, but also pushing the boundaries of our understanding of the universe's formation, evolution, and fundamental forces. Through careful observation, cutting-edge simulations, and groundbreaking experiments, we are inching closer to solving the cosmic puzzle and revealing the secrets of the invisible forces that govern the vast expanse of space. Gamma-ray bursts, GRBs, are among the most energetic and mysterious phenomena in the universe, releasing vast amounts of energy in the form of gamma radiation. Yet, the exact mechanisms driving these astonishing explosions remain one of the greatest enigmas in astrophysics. What makes them even more perplexing is their inherent unpredictability. These cosmic eruptions can occur anywhere in the universe without any apparent pattern or specific location. They are not confined to particular regions or conditions, which complicates the task of studying them in detail. The randomness of GRBs is a key challenge for scientists who are trying to understand their nature. With the immense distances involved, observing a GRB is often a race against time. By the time their light reaches Earth, after traveling billions of light years, the explosion's aftermath may have already faded, leaving researchers with limited opportunities to gather critical data. The light from a gamma-ray burst is a cosmic messenger traversing vast stretches of space, yet its origin remains elusive, making it difficult to trace the exact processes responsible for these colossal outbursts. To make things even more complex, GRBs are classified into two main categories: long-duration and short-duration bursts. Long-duration bursts, which last for more than 2 seconds, are believed to be the result of the collapse of massive stars, possibly in the form of a supernova or hypernova. In contrast, short-duration bursts, which last less than 2 seconds, are typically associated with the violent mergers of neutron stars or the collision of compact stellar remnants. These classifications suggest that different astrophysical processes are at work, yet the exact details of these processes are still largely unknown, and the scientific community is eager to unravel the mysteries hidden within them. Studying gamma-ray bursts is not just an academic pursuit. It offers profound insights into some of the most fundamental aspects of the universe. Their study illuminates the life cycles of stars, especially the dramatic and explosive deaths of massive stars. Moreover, these cosmic events hold the potential to reveal clues about the early universe. As they light up the distant reaches of space, GRBs act as beacons that can illuminate the conditions of galaxies at the time when they were first forming, offering a glimpse into the processes that shaped the universe during its infancy. In the quest to understand the origins of galaxies, stellar evolution, and the dynamics of the cosmos, GRBs provide a crucial piece of the puzzle. While gamma-ray bursts offer a window into some of the universe's most extreme processes, another astronomical marvel, quasars, provides equally compelling insights into the distant past. Quasars, or quasi-stellar objects, are exceptionally bright and energetic phenomena located at the centers of distant galaxies. These objects are powered by supermassive black holes, which lie at the heart of the quasars. As matter falls into these black holes, it heats up, emitting prodigious amounts of energy in the form of light, radio waves, and other radiation. In fact, quasars are so luminous that they can outshine entire galaxies, enabling astronomers to observe them even from billions of light years away. Quasars are not just objects of fascination due to their extraordinary luminosity, they also provide invaluable information about the early universe. By observing these distant ancient objects, astronomers can gain a deeper understanding of how the universe evolved. Quasars in the early universe, existing roughly between 1 and 3 billion years after the Big Bang, offer a snapshot of a time when cosmic structures were just beginning to take shape. The light emitted by these objects contains critical information about the conditions of the universe at that time, including the abundance of primordial elements such as hydrogen and helium. Furthermore, studying quasars reveals how the universe expanded and evolved over billions of years. As their light travels across vast expanses of space, it interacts with various cosmic elements, including gas clouds and dark matter. This interaction allows scientists to deduce the distribution and density of matter in the universe, helping to construct a more accurate model of its evolution from a smooth, hot mass into the complex, structured cosmos we observe today. Thus, quasars serve as cosmic lighthouses, illuminating the processes that have shaped the universe's large-scale structure. In addition to gamma-ray bursts and quasars, the unexplained luminosity of certain stars has long puzzled astronomers. One of the main theories to explain this variability is the existence of variable stars, stars whose brightness fluctuates over time. These variations can result from intrinsic factors, such as changes in the star's temperature, size, or energy output as it evolves. Alternatively, the fluctuations could be due to extrinsic factors, like the presence of a companion star that periodically blocks or obscures the light. Another intriguing phenomenon contributing to stellar luminosity is the supernova, a cataclysmic event that occurs when a massive star runs out of nuclear fuel. During this event, the star undergoes a spectacular explosion, temporarily increasing its brightness to the point where it can outshine entire galaxies. However, this intense luminosity is short-lived, and the aftermath of a supernova often leaves behind remnants that are studied by astronomers for years or even decades after the explosion. Additionally, some unexplained luminosity can be attributed to novae and peculiar stars. Novae occur when a white dwarf star in a binary system pulls material from its companion, eventually triggering a thermonuclear explosion on its surface. This explosion causes a rapid increase in brightness, often by several orders of magnitude. On the other hand, peculiar stars such as luminous blue variables, LBVs, exhibit unusual brightness variations linked to massive stellar winds and changes in their atmospheres. These stars are often in a state of instability, undergoing dramatic fluctuations in size and luminosity as they approach the end of their life cycles. Together, these phenomena, gamma-ray bursts, quasars, and variable stars, present a fascinating and ever-evolving puzzle for astronomers. Each offers a unique window into different stages of cosmic evolution, helping to unravel the mysteries of the universe, from its earliest moments to its present state. As our understanding of these remarkable events deepens, they promise to reveal even more about the fundamental forces that govern the cosmos and the remarkable processes that shape it. Dark matter and exotic energy sources have long been subjects of speculation in the scientific community, and recent research has only deepened their mystique. Although dark matter primarily influences the dynamics of galaxies, its effects might also extend to star formation and evolution, leading to surprising and sometimes unpredictable patterns in stellar luminosity. These theories offer just a glimpse into the complexities of our ongoing exploration of the universe's more enigmatic forces. As scientists continue their journey into the heart of these cosmic mysteries, the quest to understand the intricate behaviors of stars across the universe becomes increasingly urgent. One of the most compelling aspects of this cosmic investigation is the study of cosmic voids, vast, nearly empty regions of space that stretch across hundreds of millions of light years. These voids pose a direct challenge to our understanding of the universe's structure, revealing that the cosmos is not a uniform sea of matter, as we might have once believed. Instead, the universe unfolds like a vast, interconnected web, where dense clusters of galaxies form intricate structures, bound together by filaments of dark matter and gas. In contrast, expansive voids surround these dense clusters, leaving behind vast regions where galaxies are sparse or altogether absent. These voids represent more than 80% of the observable universe's volume. Their existence forces scientists to rethink how matter is distributed on a grand scale. Rather than galaxies being evenly scattered throughout space, they tend to gather in clusters or superclusters, leaving immense areas almost devoid of galaxies. This uneven distribution raises fundamental questions about cosmology, particularly concerning the nature of dark energy and dark matter, two forces that play pivotal roles in the formation and evolution of cosmic structures. Moreover, cosmic voids challenge our understanding of the universe's expansion. These enormous empty spaces may have a profound effect on the movement of surrounding matter and influence the overall dynamics of the cosmos. For instance, the gravitational forces exerted by matter in the cosmic filaments that stretch across the voids could have an impact on the rate at which the universe is expanding. Understanding how these forces interact on a cosmic scale provides crucial insights into the behavior of the universe over time, shedding light on how it has evolved from its earliest stages to its present state. Importantly, the study of voids also helps astronomers develop models to explore the conditions of the early universe, an essential endeavor for uncovering the origins and future trajectory of our cosmos. As researchers delve deeper into these empty expanses of space, they gain new perspectives on how the universe came to be and what might lie ahead for its ultimate fate. With each discovery, we are forced to adjust our understanding of the universe, appreciating the complex interplay between voids and galaxies that shapes the cosmic tapestry beyond our own planet. Meanwhile, certain asteroids have displayed behaviors that defy conventional explanations, prompting astronomers to reconsider our understanding of these celestial bodies. One such anomaly involves a group of asteroids known as active asteroids. Unlike typical asteroids, which usually follow stable orbits and remain inert, these active asteroids occasionally display comet-like features, including outgassing and the formation of tails. This unexpected behavior suggests the possibility of volatile materials hidden within these asteroids that may be released when exposed to heat or other environmental factors. Another perplexing observation revolves around the trajectory changes of some asteroids, particularly those located within the inner solar system. Certain asteroids have been observed to accelerate or alter their orbits in ways that cannot be solely explained by the gravitational influence of nearby celestial bodies. This phenomenon, known as the Yarkovsky effect, occurs when an asteroid absorbs sunlight and re-emits it as heat, creating small forces that gradually alter its orbit. However, in some cases, the observed changes in an asteroid's trajectory go beyond what the Yarkovsky effect can account for, prompting researchers to consider other forces or irregularities within the structure of the asteroid itself. In addition, the discovery of so-called asteroidal moons, small moonlets that orbit larger asteroids, has further complicated the study of these objects. These moonlets may form through collisions or be captured by the gravitational pull of their parent asteroid, but the exact dynamics behind their formation and retention remain a mystery. Some asteroids, such as the well-known asteroid Itokawa, have even been observed to take on peculiar shapes, like the famous pancake shape of Itokawa, raising questions about how such forms evolve over time. Each of these anomalies provides a window into the complex behavior of asteroids, shedding light on the forces and materials that govern not only asteroids, but also the broader dynamics of our solar system. As scientists continue to investigate these strange phenomena, they move closer to uncovering the hidden history of our solar system and the celestial mechanics that shape it. Similarly, magnetars, a rare and extremely powerful type of neutron star, are challenging our understanding of magnetic fields in space. Magnetars are renowned for their extraordinarily strong magnetic fields, which can be trillions of times stronger than Earth's magnetic field. These objects push the boundaries of current astrophysical models, which are generally effective in predicting the behavior of magnetic fields in other celestial bodies, but struggle to accommodate the extreme properties of magnetars. The creation of such intense magnetic fields remains a subject of much debate. It is hypothesized that the gravitational collapse of a star during the formation of a magnetar can amplify its magnetic field to staggering proportions. Additionally, the rapid rotation of the neutron star can twist and distort the magnetic field, causing it to unleash powerful bursts of energy. These bursts, often detected as gamma-ray flares, offer tantalizing clues about the physics behind magnetars, but also present puzzles that challenge existing theoretical frameworks. Scientists are particularly interested in how matter behaves under the extreme magnetic conditions found around magnetars. The ionized matter surrounding these objects may exist in unusual states, such as quantum fluids, that defy our typical understanding of matter. These strange states could provide new insights into the fundamental principles of magnetism and matter, forcing researchers to rethink established theories and possibly leading to groundbreaking discoveries in fundamental physics. In exploring the nature of magnetars and their magnetic fields, scientists are not only expanding our understanding of these mysterious objects, but also pushing the frontiers of astrophysics and quantum mechanics. With every new revelation, the universe continues to surprise us, urging us to deepen our understanding of the forces that govern the cosmos and the strange, often unpredictable behaviors that emerge in the most extreme environments. Magnetars, some of the most mysterious and intense objects in the universe, hold the potential to reveal far more than just their immediate surroundings. Understanding these enigmatic entities could provide us with a deeper understanding of the life cycles of massive stars and the powerful dynamics of supernova explosions, events that forge these dense and highly magnetic stellar remnants. As scientists continue to explore the properties of magnetars, they are uncovering the profound role magnetic fields play, not only within these extraordinary stars, but across the entire cosmos. This research promises to open doors to new discoveries in astrophysics, offering insights that may change how we perceive the very fabric of the universe itself. In a similar vein, planetary nebulae, the spectacular remnants of dying stars, present scientists with a host of unanswered questions that continue to captivate the minds of astrophysicists. These nebulae, often glowing with the hues of ionized gas, are born from stars that once resembled our own sun but have reached the final stages of their life cycle. Although we know that they form from the outer layers of these stars being ejected into space, the intricate processes responsible for their diverse shapes and structures remain largely a mystery. From nearly perfect spheres to intricate multi-lobed forms, the variety of planetary nebulae raises a fundamental question. What exactly determines the geometry of these structures? One of the most intriguing avenues of research in this area is the role that binary star systems might play in shaping planetary nebula. In the universe, many stars are not solitary. Instead, they exist in binary systems, where one star's gravitational influence can significantly affect the evolution of its companion. In some cases, these interactions could play a pivotal role in how the material is ejected during a star's death, potentially explaining the complexity of planetary nebulae. Scientists are particularly focused on unraveling the ways these gravitational forces affect the dispersal of material, as the binary dynamics may contribute to the intricate patterns observed in these nebulae. The chemical composition of planetary nebulae adds yet another layer of intrigue. When these nebulae release their material into the vast expanse of space, they enrich the interstellar medium with elements like carbon, oxygen, and nitrogen, key building blocks for new stars and planets. Yet, the full extent of this chemical enrichment remains unclear. How do these elements distribute themselves, and how do they influence the formation of future generations of stars and planetary systems? The origins and spatial distribution of these elements, forged in the heart of stars during their lifetimes, are crucial pieces of the puzzle in understanding not only stellar evolution, but also the very building blocks of galaxies. Even after planetary nebulae fade from view, the remnants of their stellar cores can undergo further transformations. These remnants, often in the form of white dwarfs, represent the final stages of stellar evolution for many stars. However, the interaction between these dwarf remnants and the surrounding nebular material is still not fully understood. Investigating this transition from nebula to white dwarf can offer valuable insights into the long-term impact these nebulae have on galactic evolution. Their role in the broader context of star formation helps us to piece together the narrative of how galaxies evolve, providing a cosmic backdrop for the continuous cycle of life, death, and rebirth in the universe. In addition to these stellar phenomena, the motion and alignment of galaxies themselves present a series of complex challenges that continue to puzzle astronomers. Galaxies, far from being static objects, are constantly moving through space, driven by the gravitational forces exerted by their neighbors. These movements can result in dramatic interactions, such as mergers or collisions, which can lead to the formation of entirely new galactic structures. However, the dynamic nature of galaxies introduces significant complications when it comes to measuring their positions and predicting their future behavior. Observing galaxies in 2 dimensions on the sky does not give us the full picture. The third dimension, how far apart they are in space, remains elusive. This creates a misalignment in our understanding, as galaxies that appear close together may actually be separated by vast distances, making it difficult to accurately estimate their positions and velocities. Furthermore, the cosmic web, the vast, interconnected structure of galaxies and dark matter that forms the large-scale framework of the universe, adds another layer of complexity. Galaxies do not simply exist in isolation. They cluster together in vast filaments and sheets, with immense voids in between. These structures, while visible through astronomical observations, are still not fully understood. How galaxies cluster, the forces that bind them, and the evolution of these galactic structures over time are some of the most compelling and unresolved questions in modern astrophysics. These challenges, the mysterious nature of magnetars, the complexity of planetary nebulae, and the motion of galaxies, represent just a fraction of the immense unknowns that still exist in our understanding of the universe. But as we continue to delve into the mechanics of stellar and galactic evolution, each discovery brings us one step closer to unraveling the vast and intricate tapestry of the cosmos. Through continued research and observation, scientists are uncovering the subtle connections that weave together the life cycles of stars, the dynamics of galaxies, and the evolution of the universe itself. With each breakthrough, we move ever closer to understanding the grand narrative of existence, from the smallest stellar remnants to the largest galactic structures. However, the motion of galaxies within the vast expanse of the cosmic web is far from a simple phenomenon. It is intricately influenced by a mysterious force known as dark matter, a substance that, despite having mass, does not emit or reflect light. Our limited understanding of dark matter's true properties means that we are unable to accurately account for its gravitational effects on the movement of galaxies. This gap in knowledge introduces significant uncertainty into our cosmic models, challenging our comprehension of the forces that govern the universe. Galactic motion is driven by a complex interplay of factors, including cosmic inflation, the rapid expansion of the universe in its earliest moments, and the ongoing expansion of the universe itself. As galaxies move away from one another, driven by the expansion of space-time, measuring their velocities becomes a task laden with assumptions. These assumptions are built upon the uniformity of the universe's expansion and the even distribution of mass across the cosmos. Yet discrepancies in these assumptions often lead to unexpected results, revealing the deeply interconnected and puzzling nature of the universe. This constant revelation underscores the fact that our understanding of the cosmos is far from complete and continues to evolve as new data and insights emerge. One of the most captivating enigmas that arises from this vast and seemingly uninhabited universe is the Fermi paradox. This paradox presents a profound contradiction. Given the high probability of extraterrestrial life existing in the universe, why have we not yet encountered any evidence or established contact with such civilizations? The sheer number of stars within our Milky Way galaxy alone, estimated to be in the hundreds of billions, suggests that a significant portion of these stars could host planets capable of supporting life. When we combine this with the 13.8 billion years the universe has been in existence, the possibility of numerous advanced civilizations emerging becomes tantalizingly plausible. The Fermi paradox is thought-provoking because it highlights the mystery of silence in a universe that seems full of potential. Humanity has made significant strides in exploring our own solar system, but we have only just begun to scratch the surface of distant worlds. With current technologies, we can detect exoplanets in the habitable zone of their stars, yet we have not found definitive signs of intelligent life. This absence of evidence fuels curiosity about the barriers that may prevent us from discovering or making contact with extraterrestrial civilizations. Could it be that technological limitations are keeping us from detecting alien signals? Or is it possible that sociological factors, such as cultural isolation or a lack of interest in interstellar communication, are hindering the advancement of civilizations? As we continue to push the boundaries of our scientific capabilities, the Fermi paradox invites a variety of theories. Some suggest that advanced civilizations might self-destruct or become so absorbed in their own technological pursuits that they fail to make contact with others. Others speculate that we might not even recognize the signals of alien intelligence if they were to reach us, or that these civilizations could deliberately choose to avoid us altogether. The paradox doesn't only pose questions about the possibility of extraterrestrial life, it also prompts profound philosophical and ethical reflections. If intelligent life does exist, why have we not been visited by any advanced civilizations? Are we, humans, a relatively rare phenomenon in the universe, or have other civilizations already encountered their own extinction before they could reach out? These questions stir the imagination and challenge our assumptions about existence, intelligence, and the very nature of communication in a vast and complex cosmos. Scientific inquiry surrounding the Fermi paradox continues to inspire new hypotheses and theories. Among the most intriguing is the Great Filter theory, which suggests that there exists a significant, possibly insurmountable barrier that prevents intelligent civilizations from emerging or surviving long enough to establish interstellar communication. Other hypotheses venture into the realms of the multiverse, or propose the existence of temporal phenomena that might explain the apparent silence. These theories invite us to rethink our place in the cosmos, expanding the boundaries of our imagination and spurring the quest to understand life beyond our own planet. As we grapple with these possibilities, one thing becomes clear. We are only beginning to explore the vast, uncharted territories of the universe, and the journey ahead is as much about asking the right questions as it is about finding the answers. In our exploration of the stars, scientists have developed sophisticated methods for interpreting the peculiar patterns of light emitted by distant stars. By analyzing how light interacts with its surroundings as it travels from a star to Earth, astronomers can unlock vital information about the star's characteristics. Light can be altered by factors such as the star's own properties, the influence of nearby celestial objects, or the presence of intervening material like gas and dust. These changes in the light's patterns provide critical clues about the star, including its composition, temperature, distance, and even its motion through space. One of the most important tools in this investigation is spectroscopy, the study of light's interaction with matter. When light passes through a prism, it breaks into a spectrum of colors. Each element in a star's atmosphere absorbs specific wavelengths of light, creating unique absorption lines in the spectrum. By examining these lines, scientists can identify the elements present in the star's atmosphere and gain insight into its chemical composition. This technique also allows researchers to determine a star's age, life cycle, and even detect the presence of exoplanets orbiting the star. Peculiar light patterns can also indicate other phenomena, such as pulsations or eruptions within a star. Some stars, known as variable stars, experience periodic changes in brightness due to internal processes, while others might display erratic behavior caused by dramatic events such as supernova A or the merging of stars. Each fluctuation in the light's pattern tells a unique story about the forces at work within the star, offering us a glimpse into the star's evolutionary processes and its role within the larger cosmic context. These observations of light not only help us understand the stars themselves, but also serve as windows into the broader mechanics of the universe. Every new discovery challenges our existing models and assumptions, reminding us of the complexity and vastness of the cosmos. As our understanding deepens, we are confronted with even more questions, each more profound than the last, inviting us to continue our exploration of the mysteries of the universe. Moreover, certain cosmic patterns reveal intriguing shifts in light, red shifts and blue shifts, that offer crucial insights into the movement of stars relative to Earth. A red shift occurs when a star is receding from us, causing its light to stretch and appear redder. Conversely, a blue shift occurs when a star is approaching, compressing the light and making it appear bluer. These shifts act as cosmic markers, enabling astronomers to determine the velocity and direction of celestial bodies, providing us with a dynamic view of the universe. This interplay of light and motion paints an intricate and ever-changing picture of how stars interact with one another and their cosmic environments. Delving deeper into the fabric of the universe, string theory emerges as a fascinating concept. This theory suggests that the fundamental building blocks of the universe are not point-like particles, as traditionally believed, but rather tiny, vibrating strings. These strings, though minuscule, oscillate at various frequencies, and their vibrations give rise to the particles we observe, such as quarks and electrons. This radical idea proposes that everything in the universe, from the smallest particles to the forces that govern them, can be explained by these one-dimensional strings. It carries with it profound implications, suggesting that gravity, electromagnetism, the strong nuclear force, and the weak nuclear force are all manifestations of these vibrations. For decades, scientists have longed for a theory that can unite the fundamental forces of nature, specifically gravity, with the framework of quantum mechanics. String theory offers one of the most promising solutions to this long-standing quest. It attempts to address some of the most profound mysteries in physics, such as the nature of gravity at the quantum scale, the behavior of black holes, and even the reasons behind the number of dimensions in our universe. While our everyday experience leads us to perceive only 3 dimensions of space and 1 dimension of time, string theory proposes the existence of additional hidden dimensions, curled up and beyond direct observation. One of the most captivating aspects of string theory is its potential to unify seemingly disparate forces. It provides a framework where all 4 fundamental forces, electromagnetism, the strong and weak nuclear forces, and gravity, are intricately connected, revealing a more comprehensive understanding of how these forces interact. This interconnectedness enables scientists to explore their behaviors at both the macroscopic and microscopic scales. However, despite its elegant potential, string theory remains largely speculative. It has yet to be tested experimentally, and its abstract nature presents challenges in terms of empirical validation. While critics argue that the lack of direct evidence makes it difficult to confirm its validity, the ongoing research into string theory continues to illuminate some of the most enigmatic questions in modern physics. The multiverse theory, on the other hand, presents an entirely different, yet equally fascinating perspective. It proposes that our universe is merely one of an infinite number of universes, each with its own set of physical laws, constants, and even dimensions. This idea has its roots in multiple fields of theoretical physics, including quantum mechanics and cosmology. One of the strongest pieces of evidence supporting this theory comes from the phenomenon of cosmic inflation, the rapid expansion of the universe immediately following the Big Bang. This expansion implies that if one region of space can inflate, other regions could do the same, leading to the creation of separate universes, each independent and not interacting with one another. Quantum mechanics further bolsters the concept of the multiverse through the many worlds interpretation. This interpretation suggests that for every quantum event with multiple possible outcomes, the universe splits into different branches, each corresponding to a different outcome. In this way, every decision or event could spawn a new universe where the alternative outcome occurs. This raises the possibility of an endless number of parallel realities where choices and circumstances unfold in ways that differ from our own. String theory also dovetails with the multiverse theory, proposing that additional dimensions beyond the 3 familiar ones could harbor other universes with entirely distinct properties. These universes could feature different physical constants, allowing for matter and energy to behave in ways that are unrecognizable to us. While some universes might share similarities with our own, others could be governed by entirely different sets of rules. This speculative view of the multiverse continues to provoke thought, raising profound questions about the nature of existence and our place within a potentially boundless reality. Despite the excitement it generates, the multiverse theory remains controversial and unproven. Yet, its very existence challenges our understanding of the cosmos and invites speculation on the infinite possibilities that may lie beyond the limits of our observable universe. The idea that there could be alternate versions of ourselves across the multiverse, each exploring divergent paths, opens up a realm of philosophical inquiry that continues to inspire both scientists and dreamers alike. Wormholes, another captivating theoretical concept, represent potential shortcuts through space and time. Often envisioned as bridges linking distant points in the universe, wormholes could allow for instantaneous travel between regions separated by vast distances, perhaps even light years apart. The idea originates from Einstein's theory of general relativity, which describes how gravity influences the curvature of space-time. According to this theory, a wormhole consists of two ends situated at different points in space-time, creating a kind of tunnel through the fabric of the universe. If such structures could be stabilized, they could revolutionize interstellar travel, allowing spacecraft to journey across the cosmos in a fraction of the time it would take using conventional methods. This possibility offers tantalizing prospects for exploring distant star systems, transforming our understanding of space travel, and the potential for human exploration beyond our own solar system. However, the challenges involved in making wormholes a reality are immense. To date, wormholes remain purely theoretical, with no experimental evidence supporting their existence. Despite these obstacles, the allure of wormholes as a means of traversing the vastness of the universe persists. They represent a potential key to unlocking the mysteries of space-time and offer a glimpse into the future of cosmic exploration. The pursuit of such groundbreaking concepts continues to push the boundaries of our knowledge, offering hope for new discoveries and the possibility of a future where the stars are within our reach. In the speculative world of theoretical physics, some scientists explore the fascinating possibility of wormholes, hypothetical tunnels that could connect distant regions of space-time, potentially offering shortcuts across the universe. However, if these cosmic bridges do indeed exist, they may require exotic forms of matter or energy to keep them stable. This form of matter would have to possess negative energy density, an elusive concept that remains a topic of intense debate within the scientific community. The idea of wormholes excites the imagination, stirring thoughts of intergalactic travel and the potential to reach the farthest corners of the universe in the blink of an eye. But while such travel might seem straight out of a science fiction novel, these theories challenge the very foundation of our understanding of physics and the nature of space travel itself. They force us to rethink what could be possible, pushing the boundaries of science as we know it. As our knowledge evolves, we may find ourselves one day standing at the edge of a new era, capable of doing what was once thought impossible. Delving into the concept of time, especially within the vast expanse of the cosmos, introduces another set of challenges that have perplexed scientists for centuries. Unlike physical objects that can be measured directly, time is an intangible force. It is not something that can be held or seen, but rather something that we experience and observe. This abstract nature makes it difficult to define time in a way that applies universally, complicating both theoretical studies and practical experiments. Without a standard definition, crafting a universal framework of time that works across various contexts has proven to be a monumental task. Einstein's theory of relativity introduced a revolutionary shift in our understanding of time. According to relativity, time is not a fixed, absolute entity. Instead, it is fluid and relative. It changes depending on the speed at which an object moves and the strength of the gravitational fields it experiences. This means that the passage of time is not the same for everyone. For example, time appears to slow down in strong gravitational fields, like those near black holes or dense stars. This creates a major challenge when trying to synchronize time across vast cosmic distances, where different regions of space experience time in very different ways. Another complication in the study of time arises when scientists look back to the early moments of the universe. To understand how time behaved during the Big Bang and other pivotal moments in the cosmos' infancy, researchers rely heavily on theoretical models and indirect measurements. These models are built on what we know about physics today, but the early universe was an environment far beyond our current technological capabilities. The interplay of high-energy physics and gravity in such extreme conditions is still largely unexplored. Without direct empirical data from that time, researchers must speculate based on our best available theories, often dealing with significant uncertainties. Moreover, the philosophical implications of time add another layer of complexity. The age-old question of whether time flows in a linear, unidirectional fashion, or if it follows a cyclical pattern repeating endlessly, challenges not only traditional scientific views, but also the very nature of reality itself. These philosophical debates shape the scientific discourse and raise profound questions about existence, the flow of events, and the fundamental structure of the universe. As these discussions intertwine with scientific inquiry, they introduce an additional challenge in formulating coherent theories about time's role in the cosmos. In the face of these challenges, simulations have become invaluable tools in modern scientific research. These computational models allow scientists to visualize and understand phenomena that are far beyond the reach of human observation. Many cosmic events, such as the formation of galaxies, the behavior of black holes, or the interactions of subatomic particles, occur on scales too vast or too small for us to directly perceive. By creating highly detailed, mathematically accurate models based on the laws of physics, scientists can simulate these events and study their behavior. Advanced simulations are not just theoretical exercises, they provide insights into how the universe works on a fundamental level. Using high-powered computational resources, researchers can build virtual environments that mimic real-world physics, allowing them to manipulate variables and explore a range of possibilities. For instance, simulations of the cosmic microwave background radiation, an afterglow from the Big Bang, help scientists understand the very earliest moments of the universe. By integrating data from telescopes and other observational instruments, these models become more accurate, providing a clearer picture of what occurred billions of years ago. This process enables researchers to push the boundaries of our knowledge and refine their theories, ensuring that their predictions are as precise as possible. Simulations, while indispensable, are still limited by the data available. As technology progresses and more data is gathered from space probes, telescopes, and other instruments, these models will only become more detailed, providing deeper insights into the origins and evolution of the universe. Each new discovery could bring us one step closer to unraveling the greatest mysteries of time, space, and the forces that shape our reality. And as we continue to explore the cosmos, the nature of time itself, once an abstract concept, may eventually become a key to unlocking the universe's most profound secrets. Simulations have become an indispensable tool in a variety of scientific fields, offering us unparalleled insights into complex systems that would otherwise be nearly impossible to study. In climate science, for instance, simulations are critical to understanding long-term weather patterns and predicting future climate scenarios. By recreating the intricate interactions between oceans, the atmosphere, and the land, scientists are able to model how climate change will unfold under different intervention strategies. This not only helps us visualize the potential consequences of our actions, but also drives conversations around environmental sustainability. The power of these simulations goes beyond just predictive modeling. It allows for a deeper understanding of the Earth's systems and provides an educational framework that inspires both scientific discovery and technological advancements. Through these digital experiments, new hypotheses emerge, which in turn foster innovative experimental designs that propel our understanding of the natural world forward. In the realm of physics, particle science plays a pivotal role in unraveling the mysteries of the universe's fundamental forces. Think of it like an investigative detective story, where researchers uncover hidden truths about the building blocks of the cosmos. At its core, particle physics explores the tiniest units of matter, particles so small they're almost impossible to see, and the forces that govern their behavior. These interactions are key to understanding the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. One of the greatest achievements in this field has been the development of the Standard Model, a comprehensive theory that explains how these forces interact at a microscopic level. According to the Standard Model, quarks and leptons are the fundamental components of matter, while force-carrying particles like photons and gluons mediate the interactions between these particles. The The photon, for example, is responsible for electromagnetic interactions, and the gluon is the particle that binds protons and neutrons together inside atomic nuclei. The path to understanding these forces involves high-energy experiments, such as those conducted in particle accelerators, which simulate conditions similar to the moments just after the Big Bang. When particles collide at nearly the speed of light, they create extreme conditions that reveal how the universe's forces behaved in its earliest stages. These experiments not only confirm existing theories, but also raise new questions about phenomena such as dark matter and dark energy, two mysterious components that make up a significant portion of the universe but remain largely undetectable. As scientists continue their exploration of the subatomic world, the quest to answer these questions propels us beyond the limitations of the Standard Model, prompting new projects like the Large Hadron Collider, which seeks to uncover even deeper mysteries and evidence of particles or forces that might extend our understanding of the universe. Equally transformative is the concept of space-time, which fundamentally redefines how we perceive the universe. Introduced by Albert Einstein through his theory of relativity, space-time merges the three dimensions of space with the dimension of time, creating a unified four-dimensional continuum. This novel framework has revolutionized our understanding of gravity, motion, and the structure of the cosmos. Instead of treating time and space as separate entities, Einstein's theory shows us how they influence and shape one another, offering a more holistic view of the universe. The concept of space-time helps us understand the nature of gravity. When a massive object, like a planet or star, occupies a region of space-time, it causes the fabric to warp, creating what we experience as gravity. For instance, Earth's orbit around the Sun is explained by the Sun's mass creating a dent in space-time, which guides Earth's trajectory. This curvature is what shapes the motion of objects throughout the cosmos. Space-time's effects are especially profound in extreme environments, such as near black holes. The intense gravity of black holes warps time itself, causing it to flow differently than in regions further away from these cosmic giants. The impact of space-time stretches beyond these celestial bodies. It influences some of the most dramatic events in the universe, such as supernova explosions and the collision of neutron stars. These high-energy events produce ripples in space-time known as gravitational waves, disturbances in the fabric of space-time itself that can be detected by sensitive observatories. The first detection of gravitational waves in 2015 marked a groundbreaking moment in physics, opening a new avenue of exploration into cosmic phenomena previously invisible to traditional methods of observation. The study of space-time not only helps us understand distant galaxies and celestial events, but also invites us to reconsider our own existence. The dynamic relationship between space and time challenges our traditional understanding of reality and pushes us to question the very nature of the universe itself. As we delve deeper into the workings of space-time, it becomes clear that all events in the cosmos are intricately connected, forming a unified tapestry where every moment is tied together in the vast continuum of space-time. Meanwhile, scientists continue to make progress on one of the most perplexing puzzles in theoretical physics: the black hole information paradox. This riddle arises from the conflict between quantum mechanics and general relativity, as it suggests that information swallowed by black holes may be lost forever, defying the principles of quantum theory. To tackle this mystery, researchers are advancing quantum computing technologies which allow them to simulate complex models of black hole behavior. Using quantum bits, or qubits, these simulations aim to explore how information might be encoded within the quantum states of particles that fall into black holes. Another key development in black hole research is the rise of gravitational wave detection technologies. Observatories like the Laser Interferometer Gravitational Wave Observatory, LIGO, have provided invaluable insights into the merging of black holes. These high-energy events not only help scientists understand the nature of black holes, but also offer clues about the preservation or loss of information during these extreme interactions. By analyzing the patterns in gravitational waves, physicists are gaining new insights into the mysterious mechanics of black holes and their potential role in the larger framework of quantum information theory. In addition to these technological breakthroughs, advancements in high-energy particle physics are also helping to refine our understanding of black holes. New particle accelerators, which recreate the extreme conditions found near black holes, are allowing scientists to study how matter behaves under intense gravitational forces. These facilities offer critical experimental data that could lead to major breakthroughs in our understanding of the fundamental laws of nature, ultimately shedding light on the enigmatic nature of black holes and the behavior of matter in their proximity. In summary, the merging of simulation technologies, particle physics, space-time theory, and the exploration of black holes represents an exciting era in scientific discovery. Every breakthrough opens new possibilities for understanding the universe's deepest mysteries, from the fundamental forces that govern matter to the nature of time and space itself. As we continue to advance in these areas, we stand on the brink of new revelations that will reshape our view of the cosmos and our place within it. Ongoing research into holographic principles within the realm of theoretical physics is uncovering fascinating perspectives on the nature of the universe. At the forefront of these studies lies the hypothesis that information may be preserved in a manner analogous to a hologram at the event horizon of a black hole. This idea, which challenges our understanding of space, time, and information, is part of an emerging body of thought that could lead to groundbreaking discoveries about the universe's most enigmatic phenomena. As technological advancements continue to evolve, scientists are increasingly optimistic that these innovative approaches will provide clarity on the infamous black hole information paradox. This could take us one step closer to deciphering the true nature of reality itself. At the intersection of quantum mechanics and cosmology, researchers are exploring ways in which the minute subatomic behaviors of particles can shape the grand structure and evolution of the cosmos. The behavior of atoms and particles, of things that exist on an unfathomably small scale, holds the key to understanding how the universe functions on the grandest of scales. Concepts like superposition and entanglement, which lie at the heart of quantum mechanics, challenge everything we thought we knew about locality, causality, and the very nature of existence itself. These phenomena raise fundamental questions about reality that philosophers and physicists have been grappling with for centuries. One of the most profound intersections between quantum mechanics and cosmology emerges when we consider the birth of the universe itself, the Big Bang. This event, which occurred roughly 13.8 billion years ago, marks the beginning of space, time, matter, and energy. The early conditions of the universe were so extreme that understanding them requires a quantum theoretical framework. In particular, quantum fluctuations during the moments after the Big Bang were responsible for the rapid expansion of the universe, a process known as cosmic inflation. This inflationary model explains how minute quantum variations laid the groundwork for the large-scale structure of the universe that we observe today. These fluctuations acted as the seeds for galaxies, stars, and other cosmic phenomena, linking quantum mechanics directly to the observable universe. In addition to explaining the early universe, quantum mechanics is also instrumental in the quest to unify gravity with the laws of quantum theory. General relativity, formulated by Albert Einstein, explains how massive objects warp the fabric of space and time, while quantum mechanics governs the behavior of particles at microscopic scales. These two frameworks, however, have long been incompatible, leading scientists to search for a unified theory, what we call quantum gravity, that might merge the two. This pursuit opens the door to captivating possibilities, such as a new understanding of black holes, which may behave differently at the quantum level compared to how they are described in classical physics. Additionally, certain quantum theories suggest the existence of parallel universes, other realms that exist alongside our own, each with its own unique physical laws. As research into these realms continues, groundbreaking ideas like the multiverse theory are gaining ground. Some theorists propose that our universe is just one of many in a vast, interconnected multiverse. In this scenario, each universe would have its own set of physical laws, potentially giving rise to drastically different forms of matter and energy. The more we explore these ideas, the more we realize that our understanding of the cosmos, and perhaps of reality itself, is still in its infancy. The relationship between quantum mechanics and cosmology does not only have the potential to reshape the scientific theories we hold dear, but also compels us to reconsider our very existence. It urges us to explore fundamental questions about our place in the universe and the nature of the reality in which we live. Theories about the Big Bang provide us with a fascinating glimpse into the earliest moments of the universe's existence. According to leading theories, the universe began as an extraordinarily hot and dense point around 13.8 billion years ago. This singularity underwent an explosive expansion known as cosmic inflation, during which it stretched out at an unfathomable rate. As the universe cooled, elementary particles like quarks and electrons began to form. As cooling continued, these particles combined to form protons and neutrons, which ultimately coalesced into the first elements, hydrogen and helium. One of the most profound aspects of the Big Bang theory is its ability to unify matter and energy, two of the fundamental components of the universe, under the famous equation E equals c squared, proposed by Einstein. This equation demonstrates that energy and matter are interchangeable, allowing us to understand how energy could transform into matter during the early moments of the universe. Essentially, the energy present in the universe gave birth to the matter we see today, highlighting the intimate connection between these two forces that shape our cosmos. As the universe continued to evolve, the formation of stars and galaxies played a key role in the creation of heavier elements through nuclear fusion. Inside the cores of stars, hydrogen atoms fused to form helium, and this process continued in more complex ways to form heavier elements. These stars, however, did not live forever. At the end of their life cycles, they exploded in violent supernova events, scattering these newly formed elements into the cosmos. This process enriched the primordial hydrogen and helium gas that had dominated the early universe, providing the building blocks for new stars, planets, and ultimately, life. The expansion of the universe didn't stop with the creation of stars. Observations today indicate that the universe is still expanding at an accelerating rate, driven by a mysterious force known as dark energy. This force, whose nature remains elusive, is believed to be responsible for the accelerating expansion of the cosmos. As our understanding of this increasingly complex picture of the universe deepens, we see more clearly the intricate relationship between matter, energy, and the vast, ever-expanding cosmos. From the Big Bang to the present day, the forces of nature continue to shape the universe, revealing a rich, interconnected tapestry of existence, one that challenges our perceptions of reality and invites us to explore the mysteries of the cosmos. Several groundbreaking missions are currently unfolding, each designed to deepen our knowledge of the solar system and the vast cosmos that surrounds us. These ambitious projects, spanning from space telescopes to rovers and spacecraft, hold the potential to revolutionize our understanding of planetary systems, the birth of stars, and even the origins of life itself. One of the most thrilling of these missions is the James Webb Space Telescope, launched to explore the farthest reaches of the universe. This state-of-the-art telescope is not just about peering into distant galaxies. It also offers a closer look at the atmospheres of exoplanets and provides insights into the formation and evolution of planetary systems. With its ability to capture infrared radiation that previous telescopes struggled with, Webb can observe galaxies that formed billions of years ago, their light having shifted into the infrared spectrum due to the ever-expanding universe. Unlike its predecessors, the James Webb Space Telescope is equipped with an enormous segmented mirror and highly advanced instruments capable of detecting incredibly faint light from distant sources. These capabilities allow astronomers to explore phenomena such as the birth of stars, the formation of galaxies, and the intricate processes that lead to the creation of stars and planetary systems. By peering through clouds of cosmic dust that often block the view of other telescopes, Webb provides an unparalleled view of the universe's most mysterious and distant objects, offering clues that will help us understand the fundamental processes that shaped the universe as we know it. Another mission that is capturing the imagination of scientists and space enthusiasts alike is NASA's Perseverance rover, currently exploring the Martian surface. Perseverance's main objective is to search for signs of ancient life and collect samples that could eventually be returned to Earth. Despite being in the midst of its 2-year primary mission, Perseverance has already uncovered remarkable discoveries, such as strange rock formations and the identification of organic compounds. These findings could provide vital clues to understanding Mars's past, and possibly even its potential to have supported life. The rover's sophisticated suite of scientific instruments continues to send back data that will pave the way for future missions and deepen our knowledge of the Red Planet. Beyond Mars, the Juno spacecraft is continuing its journey around Jupiter, unraveling the mysteries of this gas giant's atmosphere, magnetic field, and its many moons. Juno's groundbreaking findings have revolutionized our understanding of Jupiter, revealing details about its interior and magnetic environment that were previously beyond our reach. These discoveries have far-reaching implications, not only for our understanding of Jupiter itself, but also for the broader study of gas giants across the universe, offering clues about the formation of planetary systems in other star systems. Meanwhile, the OSIRIS-REx mission has achieved a major milestone by successfully collecting samples from the near-Earth asteroid Bennu. This asteroid, which is a remnant from the early solar system, holds vital information about the building blocks that formed our solar system. By studying these samples, scientists hope to uncover the secrets of the materials that may have played a role in the origin of life on Earth. This mission, which also holds the potential for a return mission to Earth in the coming years, is not just a triumph of space exploration, but also a step closer to understanding the very beginnings of life on our planet. As these missions progress, they continue to fuel a sense of wonder and curiosity about our place in the cosmos. They remind us that despite all we've discovered, the universe is vast, mysterious, and full of unknowns waiting to be uncovered. Each discovery, each mission, serves as a reminder of the immense complexity of the solar system and beyond. The work being done by scientists, engineers, and astronauts on these missions will undoubtedly inspire generations to come, showing us just how much there still is to learn about the universe. In particular, telescopes like the James Webb Space Telescope play an essential role in expanding our understanding of distant galaxies. Where earlier instruments focused primarily on visible light, Webb's ability to capture infrared radiation opens new doors to exploring the universe. This capability is especially crucial for studying the oldest and farthest galaxies, whose light has been stretched into the infrared spectrum as a result of the expansion of the universe. By detecting this infrared light, scientists can peer back in time and gain insight into the formation and evolution of galaxies that existed billions of years ago during the early stages of the universe. Webb's powerful infrared vision allows it to look beyond the barriers of dust and gas that often obscure our view of distant cosmic phenomena. By observing these areas, scientists can gain new perspectives on the birth of stars and the assembly of galaxies. These discoveries not only enhance our understanding of the specific galaxies and phenomena Webb observes, but also help to contextualize the evolution of the universe as a whole, revealing the interconnected nature of cosmic history. As we continue to explore the universe, these missions serve as a testament to human ingenuity and the unquenchable thirst for knowledge. With every new discovery, we edge closer to unraveling the mysteries of our solar system and the cosmos, bringing us one step closer to understanding our place in the vast and awe-inspiring universe. The universe, vast and enigmatic, has always captivated human curiosity, inviting exploration and discovery. To unravel its mysteries, scientists have developed an array of advanced tools that allow us to observe, analyze, and understand the distant corners of space. One of the most groundbreaking innovations in this pursuit is the ability to study the chemical compositions of distant galaxies. This is a key area of exploration for astronomers, and thanks to modern telescopes, particularly the James Webb Space Telescope, JWST, we are now able to peer back into the history of the universe itself. By analyzing the spectral signatures of elements in these far-off galaxies, astronomers can determine the conditions under which these galaxies were born and how they have evolved over billions of years. This information provides invaluable insights into the broader cosmic timeline. It allows scientists to trace the intricate processes of galaxy formation and evolution, shedding light on phenomena such as galactic mergers and the role that dark matter plays in shaping the structure of the universe. The data we are gathering is fundamentally altering our understanding of cosmic history, revealing new perspectives on how galaxies have interacted over time. Each new discovery made by the James Webb Space Telescope brings us closer to answering profound questions about the formation of galaxies. These revelations help us piece together a larger narrative about the origins of the universe and its ongoing evolution. With each new observation, we are invited to reflect on the vastness of space and the innumerable wonders it holds, mysteries that have eluded humanity for centuries. While space telescopes like the JWST provide unprecedented views of distant galaxies, we also rely on space probes, unmanned spacecraft that venture deep into our solar system and beyond. These probes serve as humanity's eyes and ears in the vast expanse of space, gathering vital information from planets, moons, asteroids, and comets. Designed to travel vast distances, these space probes are equipped with sophisticated instruments capable of measuring a wide range of data. This includes the atmospheric conditions, surface temperatures, and chemical compositions of distant worlds, offering scientists a wealth of knowledge about the origins and evolution of these celestial bodies. One of the remarkable features of space probes is their ability to capture images and spectroscopic data from planetary surfaces. Take, for example, the Voyager probes, launched in the late 1970s. These iconic spacecraft provided humanity with its first ever close-up images of Jupiter and Saturn, transforming our understanding of these distant gas giants. Similarly, the Mars rovers, Spirit, Opportunity, and Perseverance have been instrumental in exploring the Martian landscape. These robotic explorers have searched for signs of past life, analyzed soil and rock samples, and provided us with crucial data about the planet's geological history. Beyond the planets, space probes like NASA's New Horizons have ventured into regions of the solar system that were previously unexplored. After completing its historic flyby of Pluto in 2015, New Horizons continued its journey into the Kuiper Belt, a region beyond Neptune that is populated with icy bodies and dwarf planets. This mission has expanded our knowledge of the outer reaches of our solar system, revealing new information about the formation and evolution of these far-flung worlds. Space probes are sometimes the only viable option for exploring certain locations. Sending humans to distant planets or regions of the solar system presents a range of logistical and safety challenges. Robotic probes, on the other hand, can be sent on long journeys with minimal risk, and the data they return can be used to guide future missions and help prioritize areas of exploration. Each piece of information gathered by these machines raises more questions, fueling humanity's endless quest to uncover the secrets of the cosmos. In parallel with the work done by space probes, advances in satellite technology have revolutionized the way we study celestial phenomena. Satellites equipped with cutting-edge instruments can observe the universe in ways that ground-based telescopes cannot. Positioned above Earth's atmosphere, these satellites avoid the atmospheric distortion that often blurs the view from the ground, enabling them to capture clearer images and collect more accurate data from distant stars, galaxies, and other cosmic events. One of the most notable milestones in satellite-based astronomy was the launch of the Hubble Space Telescope in the early 1990s. Since then, Hubble has provided breathtaking images and crucial data that have fundamentally expanded our understanding of the universe. Among its many discoveries, Hubble revealed the accelerated expansion of the universe, a breakthrough that has reshaped our understanding of cosmic dynamics. Furthermore, Hubble's ability to capture light across various wavelengths, ranging from ultraviolet to near-infrared, has opened new windows into the cosmos, allowing astronomers to study objects that are invisible to ground-based telescopes. The field of satellite-based astronomy has continued to advance with the introduction of new observatories, most notably the James Webb Space Telescope. Unlike Hubble, which operates primarily in optical wavelengths, JWST is designed to observe the universe in infrared. This allows it to peer into the early stages of the universe, investigating the formation of stars, galaxies, and even planets. It also enables astronomers to study the atmospheres of exoplanets, planets that orbit stars beyond our own solar system, providing key insights into the potential for life elsewhere in the universe. These advancements in satellite technology are transforming our ability to explore the cosmos in greater detail than ever before. JWST's infrared capabilities are particularly powerful, allowing scientists to gather data on the composition, temperature, and dynamics of celestial bodies that were previously beyond our reach. The information collected by these space-based observatories not only enriches our understanding of the universe, but also deepens our appreciation for the complexity and wonder of the cosmos. As we continue to develop and refine these technologies, each new discovery brings us closer to understanding the origins of the universe and our place within it. From the far reaches of distant galaxies to the intricate details of our own solar system, the tools we use to study the cosmos are helping us rewrite the story of the universe itself. Satellites have evolved into indispensable tools in modern astronomy, playing a pivotal role in monitoring dynamic and often unpredictable cosmic events. For instance, they provide real-time data crucial for tracking phenomena such as solar flares and gamma-ray bursts. With this wealth of information, scientists can study these occurrences as they happen, offering unprecedented insights into their origins and potential consequences for life on Earth. By harnessing the power of satellite technology, astronomers can dive deeper into the mysteries of the universe. This synergy between space technology and astronomical research has been instrumental in unveiling some of the cosmos's most profound secrets, continuously reshaping our understanding of the universe's vast complexities. Among the space agencies advancing this mission is the European Space Agency, ESA, whose exploration of Venus has become a cornerstone of its planetary science research. ESA has outlined a set of ambitious goals for understanding the enigmatic planet, focusing particularly on its thick, cloud-laden atmosphere. One of the agency's primary objectives is to investigate the complex chemical interactions and dynamic processes occurring within Venus's clouds, which are primarily composed of sulfuric acid. Studying these layers of clouds offers valuable insights into cloud formation mechanisms that are drastically different from those found on Earth. ESA is also exploring the intriguing possibility that Venus may have once harbored conditions suitable for life. By closely analyzing the composition of Venus's atmosphere and searching for potential biosignatures, scientists hope to uncover the planet's history and understand the factors that might have contributed to its dramatic transformation into the inhospitable environment we see today. Though Venus is often referred to as Earth's sister planet, the stark contrast between the two worlds has sparked intense curiosity. Understanding the underlying mechanisms that led to Venus's divergence from Earth could unlock key lessons about planetary evolution. Another key focus of ESA's Venus mission is to investigate whether volcanic activity and tectonic processes are still active on the planet. These geological processes, which shaped Venus in the past, could still be at work today, offering important clues about the planet's past and present dynamics. By studying Venus's internal geology, scientists hope to gain insights not only into Venus itself, but also into the broader processes that might allow for the habitability of exoplanets with similar characteristics. Through missions like the upcoming Envision orbiter, ESA plans to map Venus's surface in unprecedented detail, using advanced radar and spectrometers to analyze both its surface and atmosphere. These efforts will complement the work of international partners, contributing to a more comprehensive understanding of the planet and enhancing our knowledge of planetary environments. In addition to these efforts, astrobiologists on Earth are conducting groundbreaking research into some of the most extreme environments on our own planet. By exploring the limits of life in the harshest conditions on Earth, such as deep-sea hydrothermal vents, acid lakes, and the frozen expanses of Antarctica, scientists are gaining new insights into how life can thrive under extreme stress. These environments serve as natural laboratories, offering a glimpse into the resilience of life and how organisms can adapt to extreme conditions, from intense radiation and high acidity to freezing temperatures and scorching heat. One of the most striking examples of life thriving in such extremes is the discovery of extremophiles, microorganisms that flourish in environments that would seem utterly inhospitable to most forms of life. For instance, certain extremophiles thrive in heat near volcanic vents, where temperatures can exceed the boiling point of water. By studying these organisms, researchers are learning about the biochemical pathways they use to extract energy and survive in such extreme conditions. This knowledge could inform our search for life on planets like Venus, which experiences similarly harsh conditions, or moons like Europa, where extreme environments are thought to exist beneath icy surfaces. Another fascinating area of astrobiological research revolves around the study of halophiles, salt-loving microorganisms that thrive in saline environments like salt flats and salt mines. These microorganisms offer valuable insights into the possibility of life on other celestial bodies, such as Mars. Evidence of ancient salt deposits on Mars suggests that liquid water may have once flowed across its surface, creating conditions that could have supported life. By studying how halophiles survive and thrive in such saline conditions, researchers can refine their models for searching for life on Mars and beyond. These cutting-edge studies of life's resilience on Earth not only expand our understanding of life on our planet, but also pave the way for future missions to other planets. By applying the knowledge gained from Earth's extreme environments, scientists hope to identify signs of extraterrestrial life and understand the potential for life to exist on distant worlds. Whether through the study of extremophiles or halophiles, researchers are laying the groundwork for the search for life beyond Earth, crafting more effective strategies for detecting and understanding life on other planets. Deep space exploration, however, presents some of the most profound challenges yet faced by humanity. The distances involved in missions to distant planets and moons are vast, with a journey to Mars, for example, potentially taking several months. This means astronauts would be far from Earth and its immediate support systems, placing them in isolation for extended periods of time. This long-duration space travel also increases astronauts' exposure to cosmic radiation, which poses significant health risks, including cancer and potential damage to the central nervous system. As a result, engineers and scientists are diligently working to develop spacecraft equipped with advanced radiation shielding and life support systems to mitigate these dangers. The psychological toll of deep space missions presents another major challenge. The isolation and confinement that astronauts experience during long missions can lead to mental fatigue, stress, and even depression. Ensuring the psychological well-being of astronauts is crucial, and designing spacecraft environments that promote teamwork, morale, and mental health is now a top priority. Researchers are also developing strategies to combat the challenges posed by communication delays, which can range from several minutes to over an hour, depending on the distance from Earth. During these delays, astronauts will need to be self-reliant and capable of making critical decisions without real-time guidance from mission control. Despite these formidable challenges, the rewards of deep space exploration are immense. Human missions beyond Earth's orbit have the potential to expand our understanding of the universe, offering insights into planetary formation, the potential for life elsewhere, and the origins of our own planet. Moreover, the very act of sending humans to distant worlds could ignite a renewed interest in science and technology, inspiring future generations to engage in research, engineering, and problem solving. These missions could also serve as a testament to human resilience and ingenuity, demonstrating our ability to overcome extraordinary obstacles in our quest to explore the cosmos. The potential for uncovering resources on distant planets or asteroids holds enormous promise, offering transformative opportunities for humanity. Imagine materials mined from asteroids, crucial for Earth's industries, or even serving as the foundation for construction efforts in space. Such endeavors may not only provide critical raw materials for Earth, but they could also help pave the way for long-term, sustainable living beyond our planet's borders. The ongoing quest for deep space exploration represents humanity's relentless drive to push the boundaries of possibility, to explore the unknown, and to unlock the mysteries of the universe. At the heart of this grand vision lies the importance of international collaboration. In the realm of space research, nations that combine their knowledge, expertise, and resources are capable of achieving far more than any single country could on its own. This global cooperation leads to the development of ambitious projects that have the power to change our understanding of the cosmos. Take, for instance, the International Space Station, ISS, a remarkable laboratory where scientists from all corners of the globe conduct cutting-edge experiments in microgravity. Here, groundbreaking research into fundamental processes of the universe is not just conducted, it is accelerated. The ISS serves as a symbol of what humanity can achieve when working together to solve complex scientific questions. Collaborations like this are essential for driving technological innovation. When countries pool their budgets, they can invest in state-of-the-art equipment and missions that go beyond the scope of what any single nation could fund alone. One of the most striking examples of this is the James Webb Space Telescope, a revolutionary tool that is redefining our understanding of the universe. This telescope provides unparalleled insights into the early universe, the formation of stars and galaxies, and the search for exoplanets. Such missions, made possible through international cooperation, create instruments that operate on a scale unimaginable for any one nation. They allow for more in-depth exploration of space, ultimately revealing cosmic phenomena that were once beyond our reach. Moreover, these international collaborations foster a scientific environment enriched by diversity. Scientists from different cultural backgrounds bring unique perspectives to the table, approaching challenges with novel ideas and methods. This diversity of thought is critical to the advancement of science, as it encourages creative problem-solving and the development of new theories. The result is a more dynamic, innovative research process that not only speeds up discoveries, but also enriches the quality of the knowledge gained. In essence, these partnerships allow humanity to turn the greatest mysteries of the cosmos into answers that benefit everyone. The effects of these collaborations extend beyond the lab, helping to promote a sense of global unity. Space research transcends national boundaries, reminding us that the search for knowledge about the universe is a collective human endeavor. Through such alliances, we are not only advancing our understanding of cosmic phenomena, but also reinforcing the bonds between nations. In the vastness of space, we are all united in the pursuit of knowledge, and these international partnerships help strengthen the ties that bind us together on Earth. Yet, space exploration is not without its challenges, particularly when it comes to space weather, a force that can profoundly impact both Earth and missions venturing into the depths of the cosmos. Space weather, primarily driven by solar activity, is an ongoing phenomenon that can have significant consequences. The sun emits a continuous flow of charged particles known as solar wind. But when solar flares or coronal mass ejections, CMEs, occur, this flow can become much more intense, releasing vast amounts of energy and charged particles into space. While this interaction with Earth's magnetic field often produces awe-inspiring auroras, it can also pose serious risks to both our technology and our safety. For instance, fluctuations in the magnetic field caused by solar activity can disrupt satellite operations, interfere with radio communications, and even cause power grid failures on Earth. As we push further into space, the dangers of space weather become even more pronounced. Satellites, spacecraft, and astronauts are all at risk during solar storms, with heightened radiation levels potentially damaging sensitive electronics or presenting health risks to astronauts, especially on long-duration missions like those to Mars. As a result, mission planners must continuously monitor solar activity, taking precautions such as shielding spacecraft or adjusting mission timelines to avoid solar events. Beyond these immediate concerns, space weather can also affect Earth's atmosphere, altering conditions that influence satellite orbits. The influx of charged particles can cause changes in the upper atmosphere, increasing drag on low Earth orbit satellites and necessitating constant adjustments to their trajectories. This makes space missions more complex, requiring engineers to adapt to a constantly shifting environment. Understanding and predicting space weather is crucial, not only for safeguarding current missions, but also for preparing for future explorations deeper into our solar system. The influence of space weather will undoubtedly play a pivotal role in the success of these ambitious endeavors. Artificial intelligence, AI, plays an increasingly vital role in the realm of space exploration, particularly through its integration into robotic missions. With the vast distances and communication delays involved in missions to planets like Mars, AI-powered robots are becoming indispensable. These robots are equipped with machine learning algorithms that enable them to perform complex tasks autonomously, making decisions without constant human oversight. This level of autonomy is especially important when communication with Earth can take anywhere from several minutes to over 20 minutes, depending on the location of the spacecraft. Robotic systems in space use AI to analyze vast amounts of data gathered from their surroundings. For example, a rover exploring the surface of Mars can assess images and sensor readings to identify obstacles, calculate the most efficient path, and select scientifically valuable locations for further investigation. This ability to learn from experience allows the robots to adapt to unforeseen challenges and ensure their missions continue smoothly, even in harsh and unpredictable environments. Another key aspect of AI in space exploration is the robot's ability to make informed decisions based on a variety of factors. These include energy consumption, the safety of the mission, and the potential scientific value of certain actions. With AI, robotic systems can make real-time decisions, such as avoiding hazards like dust storms or adjusting their mission strategies based on new data. This autonomy not only enhances the efficiency of space exploration, but also increases the success rate of missions, providing a significant advantage when navigating the unknown. In essence, AI is transforming the way we explore space. It allows for more sophisticated, self-sufficient robotic missions that can carry out complex tasks without direct human intervention. As humanity looks toward the future and contemplates longer, more ambitious missions beyond Earth's orbit, the role of artificial intelligence will be indispensable in ensuring the success of these ventures. The synergy between artificial intelligence, AI, and robotics has revolutionized the capabilities of robotic agents, especially in the context of complex missions. The fusion of AI with robotics enables a new level of collaboration between multiple robotic units, unlocking the potential for these agents to work seamlessly together in ways that were previously unimaginable. Imagine a fleet of robots, each equipped with AI, that enables communication and coordination with one another. This networked collaboration enhances the overall efficiency of missions, whether they're aimed at exploring distant worlds or solving complex problems on Earth. By harnessing AI to analyze collective data, the robots can assess each other's strengths and assign tasks accordingly. Each agent focuses on what it does best, ensuring that no aspect of the mission is overlooked. This cooperative approach guarantees a more thorough exploration and greater depth in our understanding of the universe. As robotic fleets operate in concert, the outcomes of their collaborative efforts could lead to groundbreaking discoveries, ones that reshape our understanding of space, time, and even the fundamental laws of physics. Their combined intelligence is poised to reveal hidden corners of the cosmos that would have remained out of reach for human explorers alone. In this sense, the combination of AI and robotics doesn't just enhance efficiency, it transforms what is possible in the exploration of distant worlds. Looking back, it's fascinating to note that ancient civilizations laid the foundation for many of the astronomical principles that we still use today. Long before modern telescopes and space probes, early astronomers relied on their keen observations of the night sky to understand the world around them. Among the earliest of these astronomers were the Babylonians, whose advanced knowledge of mathematics and celestial movements paved the way for future developments in both astronomy and mathematics. The Babylonians meticulously documented celestial events, such as eclipses and planetary movements, crafting detailed records that allowed them to predict future events with remarkable accuracy. Their work influenced not only their own civilization, but also laid the groundwork for future astronomical breakthroughs. The ancient Egyptians, too, made significant strides in the field of astronomy, particularly through the alignment of their monumental structures, such as the pyramids and temples, with celestial bodies. Their understanding of the stars was deeply intertwined with their practical lives, and this connection can be seen in their tracking of the heliacal rising of Sirius. This event, which marked the beginning of the annual flooding of the Nile River, was crucial for agriculture. For the Egyptians, the stars were not mere objects of fascination. They were essential to survival, providing a framework for understanding the cycles of nature. This blend of celestial knowledge with daily life is a hallmark of ancient cultures. It was not just about observing the sky, but about making sense of the world through its patterns. Similarly, the Mayan civilization developed a complex and highly accurate calendar system that was based on careful observations of the sun, moon, and planets. Their astronomical knowledge was not only advanced, but also predictive. The Mayans could accurately forecast solar and lunar eclipses, demonstrating a level of precision that echoed through their understanding of time itself. Their work was a testament to their intellectual prowess and has had a lasting influence on modern scientific thought. Today, we still rely on many of the foundational principles established by these ancient astronomers. The techniques they developed for tracking and predicting celestial phenomena remain at the heart of modern astronomy. Their legacy continues to shape our understanding of the universe and our place within it. The precision and depth of their observations provided the tools that future generations would use to probe the farthest reaches of space. The discovery of pulsars in the 1960s marked another leap forward in our understanding of the universe, particularly in the study of neutron stars. Before this breakthrough, neutron stars were largely theoretical constructs, predicted to be the remnants of supernova explosions, but their exact nature was unknown. This all changed when Jocelyn Bell Burnell and Anthony Hewish detected regular pulses of radio waves coming from a mysterious celestial source. Initially, the signals were thought to be a form of extraterrestrial communication, earning the nickname Little Green Men. However, further investigation revealed that these pulses were not from alien life, but were instead emissions from rapidly rotating neutron stars. These neutron stars, now known as pulsars, emit beams of radiation from their magnetic poles. As the stars rotate, the beams sweep across space in much the same way a lighthouse beam rotates around its tower. If Earth happens to lie within the path of these beams, we observe periodic bursts of radiation, giving the appearance of a pulsating source. This discovery opened up an entirely new way of studying these enigmatic objects. Pulsars, with their precise and regular emissions, provided a tool to study neutron stars' incredibly dense and compact nature, density that can exceed that of an atomic nucleus. The regularity of pulsar signals also offered a means to test predictions made by Einstein's theory of general relativity. These tests have helped scientists explore extreme conditions such as those found in high-density environments and strong gravitational fields. Pulsars, in essence, became natural laboratories for studying the behavior of matter under conditions that cannot be replicated on Earth. As we continue to study pulsars, we uncover deeper insights into the nature of gravity, the fundamental structure of matter, and even the very fabric of the universe itself. Through these diverse scientific advancements, from the ancient astronomers to the modern discovery of pulsars, humanity has progressively expanded its understanding of the cosmos. The legacy of these early observers continues to resonate, providing the building blocks for our modern understanding of space, time, and the fundamental forces that shape our universe. What once began as stargazing in ancient times has evolved into the cutting-edge exploration of the cosmos, driven by the synergy of AI, robotics, and human curiosity. The discovery of pulsars holds significance far beyond the confines of astrophysics. These rapidly rotating neutron stars have become a cosmic benchmark, enabling astronomers to make extraordinarily precise measurements of time and distance on a grand cosmic scale. Pulsars have evolved into indispensable tools for exploring fundamental phenomena, such as gravitational waves and the very nature of space-time itself. Their initial detection did not merely expand our knowledge of neutron stars, but also ignited a revolution in our understanding of the universe, reshaping the field of modern astrophysics. With the advent of these cosmic timekeepers, a new era of exploration into the fabric of the universe began. Interestingly, the human fascination with the heavens is not a recent phenomenon. Ancient cultures, long before the advent of telescopes or modern scientific tools, displayed an extraordinary grasp of celestial mechanics. This is especially evident through a variety of ancient artifacts and historical texts. One of the most remarkable pieces of evidence is the Mayan calendar, a sophisticated system designed not only to track the solar year, but also to account for the phases of the moon and the complex movements of planets. The Mayas' understanding of astronomy was profound, demonstrated by their ability to make highly accurate predictions about celestial events. This intricate knowledge reflects an intellectual legacy that continues to astonish modern researchers. Another striking artifact is the Antikythera mechanism, which was uncovered from a shipwreck off the coast of Greece. Dating back to around 100 BCE, this ancient analog computer was used to predict astronomical positions and eclipses. Its complexity, consisting of a system of gears and dials, reveals that the ancient Greeks possessed not only advanced technological capabilities, but also an astonishing depth of understanding regarding celestial mechanics. The level of craftsmanship and knowledge embedded in the mechanism challenges our modern perceptions of ancient science, revealing a sophisticated approach to astronomy and timekeeping. Stonehenge, the prehistoric monument in England, further illustrates the astronomical prowess of ancient civilizations. Believed to have been constructed as a kind of observatory, Stonehenge's alignment with the solstices suggests it served not only as a ritual site, but also as a sophisticated calendar. The arrangement of its massive stones indicates that early humans were acutely aware of the cycles of the sun and possibly the moon, harnessing this knowledge to guide agricultural practices and organize their societies. The monument stands as a testament to how deeply human cultures have engaged with the cosmos, seeking to chart its rhythms for practical and spiritual purposes. Ancient texts also provide invaluable insight into early astronomical thought. The Greeks, for instance, produced extensive works on the subject, with astronomers like Ptolemy shaping our understanding of the universe for centuries. His seminal work, the Almagest, outlined a geocentric model of the cosmos, presenting a detailed account of celestial motions. Meanwhile, ancient Indian texts like the Vedas and Siddhantas demonstrated a keen understanding of planetary positions, eclipses, and the cyclical nature of celestial events, highlighting the remarkable astronomical knowledge possessed by these civilizations. Across various cultures and epochs, the fusion of artifacts and written records illustrates a universal curiosity about the stars, a shared quest to unravel the mysteries of the heavens, and a desire to understand humanity's place in the cosmos. The advent of the telescope in the early 17th century marked a pivotal moment in the history of astronomy. When Galileo Galilei first aimed his rudimentary telescope at the night sky, he opened a new chapter in humanity's exploration of the universe. His observations, including the moons of Jupiter, the phases of Venus, and the lunar surface, provided irrefutable evidence that not all celestial bodies revolved around the Earth. This challenged the centuries-old geocentric view of the cosmos and paved the way for the heliocentric model of the solar system, fundamentally altering our understanding of the universe and our place within it. As telescopic technology improved, so too did our perception of the cosmos. By the mid-19th century, astronomers such as William Parsons, the third Earl of Rosse, used larger reflecting telescopes to reveal the intricate spiral structures of distant galaxies. This period marked the birth of our understanding of galaxies as vast collections of stars, shifting our comprehension of the universe from a view centered on our solar system to one that recognized the existence of countless other star systems spread across a vast, expanding space. The development of more advanced telescopes in the 19th and 20th centuries allowed astronomers to probe even deeper into the universe. With the advent of radio telescopes and later space telescopes, humanity gained the ability to study objects that are billions of light years away. These breakthroughs revealed phenomena such as pulsars, the cosmic microwave background radiation, and the expansion of the universe. Such discoveries have granted us glimpses into the very origins of time itself, shedding light on the fundamental forces that govern the universe. The introduction of these technologies not only broadened our observational capabilities, but also forced us to reconsider our philosophical and scientific outlook. No longer confined to the notion that the Earth occupies a central place in the cosmos, we began to embrace a dynamic and ever-expanding universe, one that continually challenges our understanding of existence and our role within it. As our tools of observation improve, so too does our ability to probe deeper into the mysteries of the cosmos. Over the centuries, a variety of celestial events have sparked intense curiosity, sometimes leaving even the most seasoned scientists both intrigued and perplexed. These events, ranging from the sudden appearance of comets to mysterious gamma-ray bursts, continue to fuel our fascination with the universe, inspiring both awe and a thirst for further exploration. With each new discovery, the enigma of the cosmos deepens, inviting us to look up and contemplate the infinite possibilities that lie beyond our understanding. One of the most perplexing and mysterious occurrences in history is the Tunguska event, which took place in the remote wilderness of Siberia in 1908. The event remains an enigma, captivating the minds of scientists and the public alike. On the morning of June 30th, an explosion of extraordinary magnitude rocked the region, flattening an estimated 2,000 square kilometers of dense forest. The blast was so powerful that it was felt thousands of miles away, and it produced a shockwave that registered on seismographs across Europe. Yet, despite the scale of the destruction, no impact crater was ever discovered. This has led many to speculate about the nature of the event, with some proposing that it was caused by the airburst of a comet or asteroid. However, the exact cause remains elusive, and no consensus has been reached. The Tunguska event continues to fuel a wide array of theories and questions about what truly happened that fateful day in Siberia, leaving a deep sense of intrigue that has lasted more than a century. Equally fascinating are the ancient records of supernovae, stellar explosions that occur when a star reaches the end of its life cycle and releases an immense amount of energy. These events have been documented throughout history, with some of the earliest accounts coming from ancient Chinese astronomers. One particularly remarkable instance is the supernova that exploded around the year 1006 CE, known as SN 1006. This extraordinary event, which was visible during the daylight hours for several weeks, is thought to have been one of the brightest stellar explosions ever recorded by humanity. Yet, despite the awe-inspiring nature of this event, the precise location of the explosion remains uncertain, and its implications for our understanding of stellar life cycles are still not fully understood. Supernova remnants, clouds of gas and dust left behind at an explosion, offer valuable insights into the processes of stellar evolution, but the complete story of these ancient supernovae continues to elude definitive explanation. What is clear, however, is that these celestial events have profoundly influenced human cultures, shaping ancient cosmologies and our understanding of the universe. The mystery of UFO sightings, or unidentified aerial phenomena, UAPs, has captured the imagination of people worldwide for decades. Events like the infamous Roswell incident of 1947 have become ingrained in popular culture, fueling conspiracy theories and the belief that extraterrestrial life has visited Earth. While many UFO sightings can be attributed to man-made objects, atmospheric phenomena, or optical illusions, there remain numerous cases that defy easy explanation. Investigations into UAPs have yielded few definitive answers, and many sightings remain shrouded in uncertainty. This enduring mystery has sparked intense debate and speculation about the possibility of life beyond our planet, prompting questions about the true nature of these phenomena and what they might reveal about our place in the universe. Despite the technological advances of modern science, certain aspects of the UFO phenomenon remain inexplicable, continuing to intrigue and challenge researchers. Another fascinating celestial occurrence in recorded history is the Great Meteor Procession of 1846, an event during which thousands of meteors were observed streaking across the skies of Europe and North America. The sheer scale of this meteor shower captivated both scientists and the general public, raising profound questions about the behavior of meteoroids and cosmic activity. The event was a spectacle that could not be ignored, and it inspired both awe and curiosity among those who witnessed it. The ongoing study of such celestial phenomena not only enriches our understanding of the universe, but also connects historical records with modern scientific inquiry, offering valuable insights into the nature of cosmic forces that shape our world. These occurrences remind us of the dynamic and ever-changing nature of the cosmos, and our ongoing quest to understand its mysteries. The ongoing exploration of the universe also brings to mind the fascinating history of humanity's evolving understanding of our place in it. One of the most captivating intellectual battles in the history of science was the debate between the heliocentric and geocentric models of the universe. The geocentric model, which posited that Earth was the center of the cosmos, was widely accepted for centuries. Ancient civilizations, including the Greeks and Romans, believed in a universe where the Earth was immovable and at the center of everything. This view was bolstered by influential thinkers like Claudius Ptolemy, whose complex system of epicycles tried to account for the apparent motions of celestial bodies while still maintaining Earth's central position. For much of human history, the geocentric model was the dominant worldview, deeply intertwined with religious and philosophical beliefs. However, as astronomical observations advanced, this model began to face serious challenges. The work of Copernicus, Galileo, and Kepler eventually led to the acceptance of the heliocentric model, which placed the Sun at the center of the solar system. This shift in perspective marked a profound turning point in human thought, as it challenged long-held assumptions about the nature of the universe and our place within it. The journey from geocentric to heliocentric thinking symbolizes humanity's continuous evolution in understanding the cosmos, pushing the boundaries of knowledge and perception. These historical and astronomical phenomena, whether it is the mysterious Tunguska explosion, the ancient supernovae, the ongoing mystery of UFO sightings, or the celestial spectacle of meteor showers, represent just a few of the many unresolved mysteries that continue to captivate our imagination. They remind us that the universe is vast, dynamic, and full of wonder, and that our understanding of it is always evolving. Through careful scientific inquiry and the interpretation of ancient records, we gain new insights into the workings of the cosmos, yet many questions remain unanswered, fueling the quest for knowledge and discovery. Ultimately, these events underscore humanity's eternal curiosity and our desire to understand the mysteries of the universe that lie beyond our comprehension. However, as human understanding of the cosmos evolved, so too did the questions and challenges that gradually undermined the long-standing geocentric view of the universe. It was in the late 15th century that a Polish astronomer, Nicolaus Copernicus, introduced a revolutionary concept that would forever change our view of the universe. Copernicus proposed the heliocentric model, a groundbreaking theory suggesting that, contrary to the prevailing belief, the Sun, not Earth, was at the center of the universe. This insight radically shifted the paradigm, offering a simpler, more coherent explanation for the movements of the planets and other celestial bodies. Despite the profound implications of Copernicus's heliocentric model, its acceptance was far from immediate. The theory faced intense opposition not only from religious authorities, but also from many scientists of the time who were firmly entrenched in the Earth-centered or geocentric model of the universe. For centuries, the geocentric perspective had been the cornerstone of both scientific and theological thought, and the heliocentric model was viewed with skepticism, even hostility. It wasn't until the 16th and 17th centuries that momentum began to build in favor of Copernicus's vision. This shift in perspective can be largely attributed to two pioneering astronomers, Johannes Kepler and Galileo Galilei. Kepler, building on the foundation laid by Copernicus, formulated his laws of planetary motion, revealing that planets did not orbit the Sun in perfect circles, as once believed, but rather in elliptical paths. This discovery further validated the heliocentric model and provided crucial insights into the true nature of planetary orbits. Galileo, whose work revolutionized the way we observe the cosmos, made some of the most significant contributions to this scientific revolution. Using a telescope, a new instrument at the time, Galileo made a series of groundbreaking observations. He discovered that Jupiter had moons orbiting it, directly challenging the Earth-centered view, which held that all celestial bodies must revolve around the Earth. These observations provided compelling evidence in support of the heliocentric model and further undermined the geocentric theory. However, the transition from the geocentric to the heliocentric model was not without its challenges. The conflict between these two perspectives persisted for years, but the development of more advanced astronomical instruments, such as the Newtonian telescope, and the formulation of Newton's law of universal gravitation in the late 17th century, pushed scientific understanding even further. These advancements not only enhanced our ability to observe the universe, but also helped explain the fundamental forces that govern the motion of celestial bodies. The work of early astronomers like Copernicus, Kepler, and Galileo marked a profound shift in human thought. Moving away from an Earth-centered view, humanity began to see itself not as the fixed center of the universe, but as part of a vast, dynamic system in which the sun, along with countless other stars, formed the heart of a greater cosmic reality. This change in perspective was not just scientific, but deeply philosophical, as humanity began to grapple with its place in the grand expanse of the universe. As the 19th century dawned, yet another technological innovation would alter the course of astronomical research and deepen our understanding of the cosmos: the invention of photography. Prior to the development of photography, astronomers relied heavily on sketches, notes, and rudimentary observations. These methods, though valuable, had inherent limitations. Human hands could only capture so much, and the accuracy of these records was often dictated by the speed and skill of the observer. With the advent of photography, astronomers gained a powerful new tool that enabled them to capture celestial phenomena with unparalleled precision. Detailed images of the moon, planets, and distant stars could now be recorded, and this new medium opened up a world of possibilities for scientific exploration. The earliest photographic images of the moon, for instance, revealed its surface in stunning detail, showing craters and mountains that had never been visible to the naked eye. Photographic techniques, particularly long-exposure photography, also allowed astronomers to capture the faint light of distant stars, galaxies, and nebula, objects that were previously too dim to detect. These long-exposure images provided a wealth of data, enabling astronomers to study the structure and composition of these distant objects, advancing our understanding of the formation and evolution of the universe. In addition to advancing our knowledge of celestial objects, photography also played a pivotal role in the development of astrometry, the branch of astronomy concerned with measuring the positions and motions of celestial bodies. By creating precise photographic records of the night sky, astronomers could track the movements of stars, planets, and other objects with remarkable accuracy. This laid the groundwork for future advancements in celestial mechanics, cosmology, and our broader understanding of the universe. The work of astronomers from centuries past laid the intellectual foundation for our modern understanding of the cosmos. The revolutionary ideas of Copernicus, for instance, forced humanity to confront a new cosmic reality in which the Earth was no longer the center of everything. Copernicus' heliocentric model, published in the early 1500s, marked a profound departure from millennia of Earth-centered thought. Kepler, building on Copernicus's work, refined our understanding by revealing that planets follow elliptical orbits rather than perfect circles. This breakthrough not only validated the heliocentric model, but also provided critical insights into the mechanics of planetary motion. Kepler's discoveries would go on to pave the way for Isaac Newton's formulation of the laws of motion and universal gravitation. Newton's work, published in the late 17th century, unified the laws governing both terrestrial and celestial bodies, offering a comprehensive theory of gravity that fundamentally altered how we viewed motion and force in the universe. Newton's theories formed the bedrock of classical mechanics, which continued to shape scientific thought for centuries. In the 20th century, the discoveries of Edwin Hubble would build upon the work of astronomers like Copernicus, Kepler, and Newton. Hubble's observations of distant galaxies, made possible by advanced telescopes and photography, revealed that galaxies were receding from one another, leading to the groundbreaking conclusion that the universe is expanding. This discovery formed the cornerstone of the Big Bang theory, which proposes that the universe began as a singularity and has been expanding ever since. Hubble's findings, grounded in centuries of astronomical research, would go on to reshape our understanding of the cosmos in profound ways. His work, along with the theoretical frameworks provided by previous scientists, continues to influence contemporary cosmology. The journey of scientific discovery that began with the radical ideas of Copernicus and continued through the work of Kepler, Galileo, Newton, and Hubble is a testament to the power of inquiry and the relentless quest for knowledge that has defined human progress throughout history. Through the lens of modern astronomy, we continue to build on the work of these early pioneers, expanding our understanding of the universe and our place within it. From the heliocentric revolution to the advent of photography and the study of cosmic expansion, each step in this ongoing journey has brought us closer to unraveling the mysteries of the universe. A journey that began with the bold insights of a few determined thinkers and continues today as we seek to understand the true nature of the cosmos. Astronomy as a field has been profoundly shaped by the efforts of early astronomers whose pioneering work laid the foundations for the sophisticated techniques and advanced tools that modern astronomers rely on today. Instruments like powerful telescopes, cutting-edge imaging technology, and analytical methods have all evolved directly from the centuries of progress made by those who sought to unlock the secrets of the universe long before us. Every stride we make in our exploration of the cosmos stands as a tribute to the innovators and dreamers of ancient times, who with limited tools and knowledge dared to gaze upward and question the mysteries of the skies. One of the most fascinating artifacts of early astronomical ingenuity is the Antikythera mechanism. Discovered in 1901 within a shipwreck off the coast of the Greek island of Antikythera, this ancient device dates back to approximately 150 to 100 BCE. Its intricate construction and engineering reveal a level of sophistication that was astonishing for its time, far ahead of what was commonly recognized in the ancient world and not truly appreciated until centuries later. Often referred to as the world's first analog computer, the Antikythera mechanism comprises at least 30 gears, each meticulously crafted, forming a complex system that could track the movements of celestial bodies with remarkable precision. This device was not just a simple tool for stargazing. It could predict the positions of the sun and the moon, and it could even forecast the orbits of the 5 known planets of the time: Mercury, Venus, Mars, Jupiter, and Saturn. By adjusting its dials, users could gain detailed insights into astronomical phenomena, such as eclipses, which held significance for a variety of practical purposes, including navigation, agriculture, and religious observances. The Antikythera mechanism was more than just a scientific instrument. It was a vital tool that helped shape daily life and societal structures in the ancient world. The discovery of the Antikythera mechanism also revealed a crucial gap in our understanding of technological history. For centuries, historians believed that complex mechanical devices only emerged during the Renaissance, yet this ancient Greek invention challenged that assumption. The sophisticated design of the mechanism suggested that early civilizations were capable of far more advanced technology than we had previously imagined. This discovery has since reshaped historical narratives, prompting a reevaluation of the achievements of ancient astronomers and craftsmen who were, it turns out, far more innovative and forward-thinking than many had assumed. Modern scholars, upon studying the Antikythera mechanism, have unearthed a treasure trove of knowledge about ancient Greek astronomy and technology. The mechanism itself is a testament to the incredible ingenuity of its creators, and it has sparked a renewed interest in similar devices from other ancient cultures. As research into these ancient technologies continues, we gain deeper insights into the early scientific inquiries that laid the groundwork for modern astronomy, and in turn, these discoveries continue to inspire contemporary explorations of the universe. The study of the cosmos has long been intertwined with human mythology, particularly through the stories and folklore surrounding comets. These celestial wanderers have captured the imagination of societies across the world, often seen as harbingers of significant change, disaster, or even divine messages. From the Greeks to the Chinese, comets have been interpreted as powerful symbols, representing omens from the gods or signals of great fortune. This enduring fascination speaks to humanity's desire to find meaning and connection in the universe, as if the movements of the stars and planets could offer insights into our own existence. The appearance of a comet in the sky has historically evoked both awe and fear. its streaking light across the heavens, stirring the imagination and raising existential questions about the unknown. For example, Halley's Comet, which has appeared numerous times throughout recorded history, has often coincided with major historical events. These comets became embedded in cultural memory, symbolizing more than just astronomical phenomena. They were seen as signs of larger, often catastrophic shifts in the world. This connection between celestial bodies and human history reinforced how deeply intertwined the cosmos was with our understanding of ourselves and our place within the larger universe. Comets have also sparked creativity, influencing art, literature, and mythology. In stories of gods and heroes, they often symbolize forces of hope or destruction, embodying the duality of human nature itself. These tales illustrate the human tendency to find patterns in the universe, even where none may exist, reflecting both our fears and aspirations. As we have looked up to the night sky, we have projected our deepest questions about life and death, existence and meaning, onto the fiery streaks of these transient visitors. Interestingly, modern astronomical research continues to fuel new myths and stories about comets, albeit with a scientific twist. As we learn more about their composition and behavior, scientists have begun to hypothesize that comets may have played a role in the origins of life itself, possibly delivering essential organic materials to Earth. This revelation adds yet another layer to the rich cultural significance of comets, blending ancient folklore with contemporary scientific discoveries. In this way, comets continue to captivate us, symbolizing the timeless allure of the unknown and reminding us that while our understanding of the universe may evolve, our fascination with these enigmatic visitors remains as powerful as ever. Perhaps the most profound shift in our understanding of the cosmos would come with the discovery of extraterrestrial life. If we were to find definitive evidence of life beyond Earth, it would have profound implications for our worldview. It would challenge the long-held belief that Earth is the only cradle of life in the universe, and suggest that the conditions necessary for life may be more common than we once thought. Such a revelation would not only transform our understanding of biology, but would also fundamentally alter the trajectory of space exploration. The discovery of extraterrestrial life would likely ignite a new era of scientific exploration, as researchers would turn their attention to the search for life on other planets, moons, and distant exoplanets. Within our own solar system, scientists would focus on moons like Europa and Enceladus, where subsurface oceans may harbor life. Beyond our solar system, the search for habitable exoplanets would become a primary objective. Such a breakthrough would not only fuel advancements in technology and space exploration, but would also invite deeper philosophical and existential questions about our place in the vastness of the universe. This potential discovery, while still hypothetical, serves as a reminder that our understanding of the cosmos is still in its infancy. Every new discovery, from ancient technologies to the ongoing search for extraterrestrial life, reminds us of how much more there is to learn. It challenges us to continue pushing the boundaries of human knowledge and to remain open to the possibility that, in the grand scheme of the universe, we may not be as unique as we once thought. Such a discovery could fundamentally alter the course of human understanding, resonating deeply with both philosophy and theology. The realization that intelligent life exists beyond Earth would likely shake the foundations of long-held beliefs about humanity's place in the universe. It may prompt a re-evaluation of our existence, pushing us to confront profound questions about spirituality, consciousness, and the nature of being. The concept of divinity itself could come into question, as the acknowledgement that intelligence might emerge in myriad forms across the cosmos challenges the exclusive nature of traditional religious narratives. This new awareness could inspire a reimagining of the human experience, as we begin to see ourselves not as solitary beings in a vast, uncaring universe, but as part of a much larger tapestry of life and intelligence that spans beyond the confines of our planet. On a broader societal level, the discovery of extraterrestrial intelligence could catalyze significant shifts in human priorities. The realization that we are not alone in the universe could foster a sense of unity among the people of Earth. As we look outward to the stars, we may begin to see ourselves as part of a global community with shared responsibilities toward each other and the planet. The presence of other intelligent civilizations might prompt humanity to shift focus from competition to collaboration, working together to tackle urgent global challenges such as climate change, resource scarcity, and geopolitical tensions. This shift in perspective could redefine how we approach problems, encouraging innovation and cooperation on a scale never before imagined. Moreover, the encounter with extraterrestrial life could ignite a new wave of curiosity and excitement, especially among younger generations. The possibility of contact with alien civilizations would likely inspire a surge in interest in science, technology, and astronomy. Students and aspiring scientists might be motivated to pursue careers in these fields, driven by the allure of unraveling the mysteries of the universe. Such a monumental event would, of course, prompt an avalanche of new questions about how we might interact with other intelligent beings. How would we communicate? What ethical principles should guide our interactions? Would we be able to establish meaningful, peaceful relationships with extraterrestrial civilizations, or would we face conflicts rooted in fundamental differences? These questions could become central to humanity's approach to the cosmos, guiding our efforts to navigate the complexities of interspecies diplomacy, both terrestrial and extraterrestrial. This new chapter in our understanding of the universe could herald a period of unprecedented exploration, not just of outer space, but of the philosophical, ethical, and diplomatic challenges that such discoveries present. As our gaze turns toward distant exoplanets, the search for habitable worlds will play a pivotal role in shaping the future of space exploration. The detection of thousands of exoplanets orbiting stars far beyond our solar system has opened up exciting new possibilities for the study of life beyond Earth. A growing interest in identifying planets that may be capable of supporting life has spurred rapid advancements in telescope technology, enabling scientists to examine the atmospheres of these distant worlds for crucial signs of habitability. Indicators such as water, oxygen, and biosignatures could provide the first real clues that life exists elsewhere in the universe. Instruments like the James Webb Space Telescope and the Transiting Exoplanet Survey Satellite, TESS-S, have been specifically designed to study these exoplanets in greater detail. These missions focus not only on locating Earth-like planets, but also on analyzing their conditions, understanding their formation, and assessing their potential to support life. Moving forward, future missions will likely incorporate even more sophisticated technologies, including space-based observatories capable of direct imaging of exoplanets. This would allow scientists to examine the climates, surfaces, and atmospheres of distant worlds with unprecedented precision, offering new insights into their potential for harboring life. The search for habitable exoplanets has already fostered unprecedented collaboration between scientists, engineers, and institutions around the globe. This collective effort has not only advanced our understanding of the cosmos, but also opened up new avenues for international partnerships and funding, pushing the limits of what was once thought possible in the field of astronomical research. The excitement surrounding this search has captured the imagination of both the public and the scientific community alike, sparking a renaissance in humanity's quest to understand the universe and our place within it. As our technology improves, the possibility of discovering microbial life on distant planets becomes more tangible with each passing year. Every mission brings us one step closer to answering the age-old question, are we truly alone in the universe? Several revolutionary technologies are poised to shape the future of space exploration in profound ways. Among the most exciting of these advancements are new propulsion systems that promise to drastically reduce travel times within our solar system and beyond. Sophisticated technologies such as ion drives and nuclear thermal propulsion are paving the way for faster, more efficient space travel. These systems, which utilize innovative fuels and methods, could enable spacecraft to reach distant destinations with unprecedented speed, unlocking new possibilities for human exploration of the outer planets and their moons. Nuclear propulsion, for example, holds the potential to make human missions to Mars and other distant worlds more feasible by reducing the time required for travel. Alongside this, artificial intelligence, AI, is playing an increasingly critical role in space exploration. AI algorithms are already being used to analyze vast amounts of data collected from telescopes and spacecraft, helping scientists to detect exoplanets and identify conditions conducive to life. Moreover, robots equipped with machine learning capabilities are being trained to make real-time decisions during complex missions, thereby improving mission success rates and reducing the need for constant human intervention. Advancements in materials science are also having a transformative impact on space exploration. New, lighter, and stronger materials are being developed to withstand the harsh conditions of space, including the radiation and micrometeoroid impacts that spacecraft encounter during extended missions. One particularly exciting area of development is the creation of self-repairing materials, which could mitigate damage caused by long-term exposure to space's extreme environments. Innovations in thermal protection systems are also enabling spacecraft to endure the extreme temperature fluctuations encountered during missions to the outer planets and their moons. In parallel, communication technologies are evolving to meet the demands of deep space exploration. Quantum communication, in particular, holds the promise of revolutionizing how we share information across vast stretches of space. This emerging technology could enable virtually instantaneous communication between spacecraft and mission control, facilitating more effective coordination of uncrewed missions and human space travel. As these technologies mature, they will play a critical role in ensuring the success of future missions, both robotic and human, to the outer reaches of the solar system and beyond. As we stand on the precipice of this new era in space exploration, the potential for groundbreaking discoveries is limitless. Advanced propulsion systems, AI-driven mission planning, and next-generation materials are transforming the landscape of space exploration. With each new breakthrough, we come closer to uncovering the mysteries of the cosmos, potentially answering questions that have lingered for centuries. As our reach extends ever further into the universe, we are poised to rewrite the story of humanity's place in the vastness of space. However, the landscape of space exploration is rapidly evolving, fueled by groundbreaking advancements in propulsion technology that promise to reshape our understanding of the cosmos and our capacity to explore it. Among the most promising developments are ion drives and nuclear thermal propulsion, which have the potential to revolutionize space travel by providing greater thrust, enhanced efficiency, and the ability to operate continuously over extended periods. These technologies open the door to interplanetary travel and beyond, offering a glimpse into a future where humanity can explore deeper into space than ever before. Ion propulsion, in particular, is a game changer. This system works by ejecting ions at high velocities, generating a continuous, albeit modest, thrust. While it may not match the immediate power of traditional chemical rockets, it offers a unique advantage. It can operate for months or even years without the need for refueling or restarts. Over time, this gradual acceleration allows spacecraft to reach astonishing speeds. Imagine traveling to the outer reaches of our solar system in a fraction of the time it would take with current technology. Missions that would normally take decades could now be completed in just a few years, opening up possibilities for exploration that were once confined to the realm of science fiction. Similarly, nuclear thermal propulsion represents another innovative approach that promises to transform space travel. In this system, a nuclear reactor heats a propellant, which is then expelled to generate thrust. The power of nuclear energy makes this propulsion method not only more potent than conventional chemical rockets, but also far more efficient. For example, a trip to Mars that would typically take several months could potentially be completed in a matter of weeks, greatly reducing the time required for human missions. This has profound implications for the future of space exploration, particularly with regards to colonization and resource utilization on other planets. The dream of sending humans to Mars and even establishing permanent settlements becomes significantly more achievable, allowing us to study Martian resources and potentially unlock the secrets of the Red Planet. Beyond these well-known technologies, there are even more ambitious concepts emerging that challenge our understanding of propulsion and space travel. One such concept is the photon sail, which uses light, either from lasers or solar radiation, to propel spacecraft forward. Although this technology is still in its infancy, it holds the promise of achieving speeds previously thought unattainable. Photon sails could potentially reach vast distances at unprecedented velocities, making interstellar travel a real possibility for future generations. Electromagnetic propulsion, another cutting-edge idea, further explores this uncharted territory, using electromagnetic fields to propel spacecraft without the need for traditional fuels. Each breakthrough in propulsion technology takes us one step closer to becoming an interstellar species, capable of visiting celestial bodies that, until now, were unreachable. These advancements are not just about achieving technological feats, they are about unlocking new realms of human possibility and discovering the unknown. However, as we set our sights on the stars, we are confronted with profound ethical considerations that cannot be ignored. One of the most pressing concerns is the potential impact of human exploration on existing ecosystems on other planets or moons. Could our ventures inadvertently harm alien life forms or disrupt fragile environments? Just as we are dedicated to preserving the biodiversity of Earth, should we not apply the same level of respect to extraterrestrial ecosystems? Many argue that our exploration of other worlds must be guided by a moral responsibility to protect these uncharted territories, ensuring that our actions do not cause irreversible damage to environments that may harbor unknown forms of life. This raises the question of how we should approach the potential discovery of alien life. If microbial life is found on Mars or one of Jupiter's moons, for example, how do we balance the quest for scientific knowledge with respect for these organisms? The dilemma is not just about exploration, but about the ethical rights of potential extraterrestrial life. The question of whether we have the moral right to alter, exploit, or destroy ecosystems on other planets requires careful thought and consideration. As we venture further into the cosmos, the guidelines we establish for interacting with alien life will set the ethical tone for future exploration and colonization. Resource utilization is another critical issue that will define the future of space exploration. The vastness of space presents tremendous opportunities for mining asteroids, extracting water from moons, and tapping into other extraterrestrial resources. However, these activities could give rise to conflicts over ownership and environmental concerns, mirroring the resource battles we see on Earth. As nations on our home planet grapple with issues of resource scarcity and environmental degradation, similar challenges could arise on an interplanetary scale. Who owns the resources extracted from an asteroid? How do we regulate the mining of extraterrestrial bodies to prevent exploitation and preserve the balance of space ecosystems? The potential for resource-driven conflicts is not just a hypothetical concern. As we develop new technologies and capabilities for space colonization, questions of governance, legality, and shared responsibility will become ever more pressing. How will spacefaring nations cooperate or compete for control over the vast resources of the cosmos? What mechanisms will ensure that space exploration benefits all of humanity, rather than being monopolized by a select few? These are the questions that must be addressed as we move toward becoming a multiplanetary species. The societal implications of space exploration are equally profound. As we embark on ambitious projects to colonize other planets, we must also ask, who will benefit from these ventures? Will space exploration remain the domain of the wealthy and powerful, or will it be accessible to all of humanity? The disparities that exist on Earth should not be replicated in space. It is crucial that we ensure that the benefits of space exploration and colonization are shared equitably, allowing all people the opportunity to partake in this new frontier. Artificial intelligence, AI, is poised to play a transformative role in space exploration, revolutionizing the way we process and analyze the enormous amounts of data generated by space missions. Traditional methods of data analysis, while effective, are often too slow and inefficient to keep up with the sheer volume of information generated by satellites, telescopes, and space probes. AI, with its unparalleled computational power, offers a solution. By harnessing the power of machine learning, researchers can process data at unprecedented speeds, uncovering patterns, anomalies, and insights that would otherwise go unnoticed. One of the most exciting applications of AI in space exploration is its ability to classify celestial objects. Using vast datasets, machine learning algorithms can be trained to recognize and categorize stars, galaxies, black holes, and other cosmic phenomena. This capability is invaluable in missions such as the James Webb Space Telescope and the Wide Field Infrared Survey Telescope, both of which are expected to generate petabytes of data. By automating the process of object classification, scientists can focus on more complex analyses and hypothesis testing, accelerating the pace of discovery. Ultimately, the integration of AI into space exploration will not only enhance our ability to explore the universe, it will fundamentally change the way we interact with the cosmos. As we venture further into the unknown, the combination of advanced propulsion technologies, ethical considerations, and artificial intelligence will shape the future of humanity's journey among the stars. Artificial intelligence is poised to revolutionize the field of astrophysics by significantly enhancing our understanding of complex cosmic phenomena. Through the use of advanced neural networks, AI has the potential to model and predict the behavior of celestial objects with remarkable accuracy. This includes modeling the intricate orbits of exoplanets, as well as simulating the dynamics of galaxy formation, areas traditionally difficult for scientists to fully grasp. By harnessing AI's predictive power, astronomers are not only able to test existing theories, but they can also develop new hypotheses, which in turn pushes the boundaries of our knowledge about the universe. AI thus serves as a vital tool in expanding the frontiers of astrophysical research. One of AI's most groundbreaking applications lies in its ability to aid in anomaly detection. In the vast expanse of space, rare events such as supernovae or the detection of gravitational waves may go unnoticed without constant, thorough observation. AI systems continuously analyze incoming data, swiftly identifying these extraordinary occurrences. When such an event is detected, AI algorithms can alert researchers to significant findings almost in real time, allowing for rapid follow-up and observation. This fast response time is critical, as timely reactions can lead to critical breakthroughs in our understanding of the cosmos. Through its role in anomaly detection, AI helps bridge the gap between vast datasets and scientific discovery, enabling us to identify and understand rare events that could otherwise remain hidden. However, AI's potential extends beyond optimizing data analysis. It is also at the heart of a new era in space exploration, where human researchers and artificial intelligence collaborate to reach new scientific frontiers. Perhaps one of the most transformative developments in modern science is the rise of citizen science. This movement has revolutionized the way ordinary people engage in space research. Once passive observers, the public is now actively contributing to the scientific process. By leveraging the diverse skills and interests of non-professionals, researchers are able to gather vast amounts of data that would otherwise be difficult, if not impossible, to collect. Take, for example, initiatives such as Galaxy Zoo, which invites volunteers to classify galaxies by examining thousands of images taken by telescopes. Through these kinds of collaborative efforts, scientific discovery is not only accelerated, but it also fosters a sense of involvement and ownership. The public is no longer relegated to the sidelines. They are now active participants in uncovering the mysteries of the universe. Moreover, citizen science helps demystify complex scientific concepts, making them more accessible to the general public. As volunteers engage in hands-on activities, they not only gain a deeper understanding of the scientific process, but also learn about the nature of astronomical research itself. This type of engagement enhances public awareness and appreciation for space exploration. Platforms like Zooniverse have further expanded the reach of citizen science, providing anyone with an internet connection the opportunity to engage in space research. These online platforms allow users to participate in projects ranging from tracking the movements of asteroids to identifying exoplanets. The collaborative nature of these projects fosters a global exchange of knowledge, empowering individuals from all over the world to contribute to scientific advancements. This sense of community and collective action is a powerful driver of enthusiasm for space exploration, as contributors come to realize that their efforts can lead to meaningful discoveries. Moreover, by making space research more accessible, citizen science also cultivates a more scientifically literate society. encouraging public support for continued funding and investment in space exploration. The impact of citizen science goes beyond data collection. It also has the potential to influence the future direction of scientific inquiry. As more people become engaged in space research, they are more likely to advocate for increased funding for scientific education and space exploration. This growing public interest creates a feedback loop wherein both scientific progress and public engagement are mutually reinforcing. Ultimately, citizen science plays a critical role in shaping the future of space exploration, enriching both our understanding of the universe and the society that supports this knowledge. In parallel, robotics and automation have become indispensable tools for exploring some of the most hostile environments known to humankind, whether on distant planets, the ocean's depths, or even within Earth's extreme conditions. These technologies allow us to send machines to places where human exploration would be not only impractical, but often impossible. Robots can endure extreme temperatures, high radiation, crushing pressures, and toxic atmospheres, conditions that would be fatal to human explorers. A prime example of this is the Mars rovers, which have revolutionized our understanding of the red planet. Equipped with advanced sensors, cameras, and scientific tools, these robotic landers and rovers are capable of conducting extensive scientific research autonomously. They can analyze soil samples, capture high-resolution images, and even search for signs of past life on Mars. Each successful mission provides invaluable data, laying the groundwork for future human exploration. By testing Mars' environmental conditions and resources, robots are helping pave the way for potential human colonization of the planet. Similarly, in ocean exploration, autonomous underwater vehicles, AUVs, have transformed our understanding of deep-sea ecosystems. These robots are capable of diving to immense depths, mapping underwater terrains, studying marine life, and even conducting repairs on submerged structures. Their ability to operate without human presence enables them to undertake long-duration missions in environments that few, if any, human divers could survive. As technology continues to advance, the capabilities of robotics will only improve. In particular, the integration of artificial intelligence will allow these machines to make complex, real-time decisions, enabling them to navigate unpredictable conditions more effectively. This evolution not only enhances the safety of exploration, but it also expands the scope of our understanding, both of the deep oceans and outer space. Private companies are also making significant strides in space exploration, setting ambitious long-term goals that encompass both scientific discovery and practical benefits. One of the most exciting prospects is the establishment of a sustainable human presence beyond Earth. With plans for permanent human settlements on the Moon and Mars, companies envision not just temporary missions, but thriving communities where humans can live, work, and grow. This idea of interplanetary habitation is the first step in humanity's long-term expansion into the cosmos, offering the possibility of a future where humans are not confined to Earth alone. Another critical goal for these private companies is the utilization of space resources. As Earth's natural resources continue to dwindle, the ability to mine asteroids and other celestial bodies presents a potentially transformative solution. Materials such as water, metals, and rare elements found in space could be extracted and brought back to Earth or used to fuel operations in space. This shift toward a broader interplanetary economy has the potential to revolutionize industries on Earth, creating a new model of resource management that is not reliant solely on terrestrial materials. The promise of space-based resources represents an exciting new frontier for both scientific research and economic development. In the coming decades, space exploration is likely to experience unprecedented advancements driven by technological innovation, citizen engagement, and private industry. Together, these forces are shaping a future in which humanity's understanding of the universe and its role within it will continue to expand in ways we can only begin to imagine. In the pursuit of exploring the vast reaches of space, private companies are emerging as key players, not only enhancing technological innovation, but also tackling the unprecedented challenges that space exploration presents. These challenges, while formidable, have catalyzed remarkable advancements in fields such as engineering, material science, and information technology. The technologies initially developed for space missions often find profound practical applications back on Earth. Innovations created to withstand the harsh conditions of space travel frequently lead to breakthroughs that resonate in everyday life, influencing industries ranging from telecommunications to healthcare and even environmental monitoring. These developments represent the far-reaching impact of space exploration on Earth, demonstrating the broad utility of technologies originally designed for cosmic endeavors. Moreover, the growing involvement of private entities in the space sector aims to revolutionize access to space itself. By lowering the cost of space travel and increasing the frequency of launches, these companies are making space exploration more inclusive. Their efforts promise to democratize the cosmos, inviting a wider range of participants into the fold: scientists, researchers, and even non-professionals who previously had limited opportunities to engage in space-related experiments and experiences. This shift toward inclusivity has the potential to ignite public interest and engagement, fostering a culture of exploration that extends far beyond Earth's atmosphere. It could inspire generations of new explorers that pushing the boundaries of what we know and what we can achieve. The continuous unveiling of new cosmic phenomena holds the potential to transform the course of scientific research in profound ways. Each new discovery, whether it be a novel event, object, or process, has the capacity to challenge existing scientific theories, providing insights that may illuminate previously unconsidered aspects of cosmology. For example, the groundbreaking detection of gravitational waves opened an entirely new field within observational astronomy, allowing scientists to directly observe events like colliding black holes in real time. This breakthrough not only redefined our understanding of the universe, but also sparked the creation of entirely new technologies and methodologies designed to explore these phenomena further. The development of advanced telescopes and more sensitive detectors are just the beginning of what promises to be an era of unprecedented scientific exploration. As each new discovery leads to a cascade of further questions, new experiments, missions, and instruments are developed to unravel the mysteries of the universe. This cyclical process of discovery and innovation extends beyond the realm of astrophysics. It impacts fields such as engineering, computer science, and a host of other disciplines, demonstrating the interconnectedness of scientific research and the interdisciplinary nature of space exploration. What's more, these cosmic discoveries often prompt humanity to reconsider fundamental philosophical questions about existence, the nature of reality, and our place in the universe. For instance, the potential discovery of extraterrestrial life would not only accelerate research into biology, chemistry, and ecology, but would also have far-reaching implications for societal values, ethics, and even global politics. Such a discovery could reshape how we view life on Earth and beyond, challenging the very framework through which we understand existence. At the heart of these ongoing explorations is the ever-expanding frontier of cosmic discovery, which compels scientists and the public alike to rethink what we know about the universe and what remains a tantalizing mystery. Every new revelation invites us to confront the unknown, and in doing so, it spurs us toward a future filled with the possibility of transformational understanding. These discoveries may lead us to answers that we have yet to imagine, propelling humanity into new realms of scientific, technological, and philosophical inquiry. One of the most intriguing and elusive aspects of the universe is dark energy, a mysterious force that is thought to make up about 70% of the cosmos. Despite its overwhelming presence, our understanding of dark energy remains shockingly limited. This enigmatic force is believed to be responsible for the accelerated expansion of the universe, a phenomenon first observed in the late 1990s. As galaxies move farther apart from each other at an ever-increasing rate, dark energy is presumed to be the driving force behind this expansion. Yet, the true nature of dark energy remains a subject of intense speculation and investigation. Numerous theories have been proposed to explain what dark energy could be. One popular hypothesis suggests that dark energy may be a property of space itself, a phenomenon known as vacuum energy. According to this theory, space is not truly empty, but instead is filled with a form of energy that exerts an influence on the fabric of the universe. Alternatively, some physicists have suggested that dark energy may be an indication that Einstein's theory of gravity requires revision. This theory posits that our current understanding of how celestial bodies interact may need to be adjusted to account for the effects of dark energy. Indirect evidence for dark energy has been gleaned from measurements of the cosmic microwave background radiation and the distribution of galaxies. These observations suggest that dark energy exerts a smooth, uniform influence on the cosmos, affecting even the most distant regions of space. Despite our inability to directly detect dark energy, its impact is undeniable. It has played a key role in shaping the evolution of cosmic structures and continues to be a determining factor in the fate of the universe itself. The quest to uncover the secrets of dark energy is far from over, and with upcoming space missions and next-generation telescopes, scientists are poised to gain deeper insights into this mysterious force. As researchers gather more data, they hope to unravel the complex nature of dark energy and place it within the larger context of cosmology. These efforts could lead to answers that have eluded humanity for generations, providing clarity about the role of dark energy in shaping the universe. In addition to dark energy, there are other cosmic phenomena that challenge our understanding of physics, such as the unusual rotation curves of certain galaxies. These anomalies defy traditional laws of dynamics, like as originally described by Sir Isaac Newton and later refined by Albert Einstein. When astronomers observe spiral galaxies, they typically expect the rotation speed of stars to decrease as they move farther from the galactic center, in much the same way that planets in our solar system orbit more slowly as they move farther from the sun. However, this is not the case for many galaxies. Instead, stars at the outer edges of these galaxies often rotate at speeds that are much higher than expected, suggesting that some unknown force or phenomenon is influencing their motion. This curious observation has prompted scientists to reevaluate long-standing theories of gravity and motion, adding yet another layer to the mystery of our universe. As humanity ventures deeper into the cosmos, these discoveries and challenges serve as reminders of the boundless potential for discovery that lies ahead. With every breakthrough, we are pushed to reconsider what is possible and to imagine new frontiers in our understanding of the universe. Space exploration, driven by both public and private efforts, continues to be a catalyst for innovation, inquiry, and the pursuit of knowledge, one that will ultimately shape the future of science, technology, and society as a whole. However, in many galaxies, the speed of rotation remains constant, or in some cases even increases as one moves outward from the galactic center. This anomaly becomes glaringly evident when scientists attempt to calculate a galaxy's mass. When only considering the visible mass, such as stars, gas, and dust, the total mass falls significantly short of what would be needed to account for the observed rotation speeds. The discrepancy between observed gravitational effects and the visible matter led scientists to propose the existence of dark matter, an invisible and enigmatic substance that pervades the cosmos. Dark matter does not emit, absorb, or reflect light, making it exceptionally challenging to detect using conventional methods. Yet, despite its invisibility, scientists can infer its presence through the gravitational effects it has on visible matter. This has profound implications for how we view the universe. If dark matter makes up a significant portion of a galaxy's mass, it suggests that the structure of galaxies, and the universe as a whole, is far more intricate than what we can observe directly. It reshapes our understanding of how gravitational forces work on galactic scales. The prevailing hypothesis is that dark matter exists in a halo surrounding galaxies, providing the necessary gravitational force to explain the flat rotation curves observed in many galaxies. Without the gravitational pull of dark matter, the outer stars of galaxies would be traveling far slower than they actually do. As astronomers refine their observations and enhance their models, the true nature of these unusual rotational patterns continues to elude our understanding. The study of galaxies with their intricate structures and behaviors pushes us deeper into the mysteries of the universe, prompting questions about the very fabric of space and time. The phenomenon of cosmic rays presents another compelling mystery in modern astrophysics. These high-energy particles travel through space at speeds close to that of light, crashing into Earth's atmosphere with immense energy. While the majority of cosmic rays are composed of protons, they can also include heavier atomic nuclei and even electrons. What remains puzzling to scientists is the origin of these particles and the mechanisms responsible for accelerating them to such extraordinary velocities. One of the most intriguing aspects of cosmic rays is their energy, which can vastly exceed the capabilities of human-made particle accelerators. The particles they carry often possess energies that are orders of magnitude greater than anything we have been able to replicate on Earth. This raises important questions. What processes in the universe can produce such high-energy particles? Supernova explosions, active galactic nuclei, and gamma-ray bursts are all suspected sources, but the exact physics behind these phenomena remains incompletely understood. Researchers are grappling with these cosmic mysteries, seeking to bridge the gap between high-energy astrophysical events and fundamental particle physics. Moreover, as cosmic rays interact with the Earth's atmosphere, they produce a cascade of secondary particles. This interaction offers a unique opportunity for scientists to observe particles and forces under extreme conditions, conditions that cannot be recreated in laboratories. By studying these secondary particles, researchers can gain insights into how the fundamental particles of the universe behave at incredibly high energies. However, cosmic ray experiments sometimes yield results that defy existing theories, forcing scientists to reconsider and refine their models of particle interactions and cosmic processes. Furthermore, the composition of cosmic rays is another area that poses questions. While they are predominantly made up of protons, the presence of heavier atomic nuclei and isotopes suggests that the particles undergo complex transformations as they travel across space. This variability challenges the assumptions of uniformity that are often made in particle physics, hinting at the existence of dynamic and complex astrophysical environments. Cosmic rays, therefore, present both an exciting opportunity for discovery and a challenge to our understanding of the universe's most fundamental processes. Shifting to an even more fundamental aspect of the universe, the accelerating expansion of the cosmos has profound consequences for our understanding of space, time, and the very nature of the universe itself. The discovery that the expansion of the universe is accelerating suggests the presence of a mysterious force dubbed dark energy, which makes up approximately 70% of the universe. Dark energy exerts a repulsive force that drives galaxies apart, counteracting the attractive force of gravity. This has forced us to rethink our previous understanding of gravity as an exclusively attractive force. The presence of dark energy challenges long-held assumptions about the very forces that shape the universe. As the universe continues to expand at an increasing rate, questions about its ultimate fate become even more pressing. One possibility, known as the Big Freeze, envisions a future in which galaxies drift further apart, stars burn out, and the universe becomes cold and dark over billions of years. In this scenario, stars would eventually extinguish, leaving behind a universe dominated by black holes and subatomic particles, with temperatures approaching absolute zero. This dark, cold future is one possible outcome if the rate of expansion continues unchecked. The accelerating expansion also presents a dilemma in our understanding of the large-scale structure of the universe. If dark energy remains constant over time, it will ultimately determine the fate of the cosmos. The formation of new galaxies might slow down, resulting in a more isolated and sparse universe. Additionally, the rapid expansion of space-time could cause distant galaxies to recede beyond our observable universe, altering our perception of the cosmos and making it seem increasingly less diverse as time progresses. Grasping the true nature of dark energy could unlock new realms of physics, opening doors to previously unimagined discoveries. It challenges us to rethink the fundamental forces of the universe and may lead to breakthroughs in our understanding of reality itself. The quest to understand why the universe is expanding at an accelerating rate is one of the primary drivers behind modern cosmological research, pushing scientists to explore beyond classical theories and into the cutting edge of theoretical physics. The discovery of anomalies in stellar evolution has also led to significant advances in our understanding of how stars are born, evolve, and die. For many years, scientists adhered to a relatively simple and linear model of stellar life cycles. Stars form in nebulous clouds of gas and dust, progress through a main sequence phase, and then either become red giants and white dwarfs or explode in supernovae, depending on their mass. However, this model is increasingly being challenged by new discoveries that suggest a far more complex and varied series of events governing the lives of stars. Recent observations have uncovered stellar populations and behaviors that do not fit neatly into the traditional framework. Some stars appear to form in unexpected ways, while others seem to evolve differently than predicted by earlier models. These discrepancies are prompting scientists to rethink and refine their models of stellar evolution, taking into account factors that were previously overlooked or underestimated. As we continue to probe the depths of the cosmos, the life cycles of stars, those fiery furnaces of matter that light up the night sky, remind us that even the most fundamental aspects of the universe may harbor secrets yet to be uncovered. In conclusion, the study of galaxies, cosmic rays, dark energy, and stellar evolution reveals a universe that is more complex and mysterious than we ever imagined. Each discovery opens new questions and avenues of research, urging us to expand our understanding of the cosmos. The universe, with all its enigmas, continues to challenge us, offering opportunities to refine our knowledge of the fundamental forces that govern everything, from the smallest particles to the grandest cosmic structures. As we venture further into these unknowns, we are reminded that the quest for understanding is not just a scientific endeavor. It is a journey that reshapes the very way we perceive reality itself. However, recent breakthroughs in astronomical research have revealed that the cosmos is far more intricate and dynamic than once imagined. Observations of massive star clusters, which have long been the subject of study, now point to a compelling realization: stars do not evolve in isolation as previously thought. Instead, they often exist in binary systems or larger groups, where their interactions with one another play a crucial role in shaping their life cycles. This discovery radically alters our understanding of stellar evolution. The profound impact of these interactions is particularly evident in close binary systems. Here, stars can exchange mass in a complex and often unpredictable process, leading to accelerated evolution compared to their solitary counterparts. Such interactions create conditions where massive stars may evolve in ways that defy traditional models, ultimately leading to a dramatic end. For instance, massive stars in these systems can explode as supernovae before ever reaching the red giant phase, a scenario that directly contradicts long-standing theories about the progression of stars. Furthermore, the study of stellar remnants has introduced even more surprising revelations. The detection of certain neutron stars and black holes challenges the very assumptions scientists had made about the end stages of stellar evolution. Some of the younger neutron stars, for example, are rotating at extraordinarily high speeds, suggesting they have undergone unique and complex processes during their formation. This is a strong indication that the mechanisms behind stellar collapse may be far more intricate than previously thought. In addition, the discovery of black holes that surpass the traditional mass limits for stellar remnants has led researchers to reconsider the role of supernovae in the collapse process. The presence of these unusually massive black holes implies that we may need to rethink the mechanisms by which stars collapse and how they give rise to such enigmatic objects. These revelations challenge the simplicity of older models and force a reevaluation of our understanding of the cosmic phenomena that govern the universe. But these developments are not confined to individual stars alone. As our observational capabilities continue to evolve, astronomers are broadening their view of how stars interact and evolve within the larger context of galactic structures. What was once thought to be a relatively predictable process is now seen as a dynamic and often chaotic phenomenon, prompting astrophysicists to reconsider long-held assumptions and theories about the universe. The study of galactic evolution, too, remains a frontier that is rich with unresolved questions and surprising twists. One of the most fascinating, yet perplexing aspects of this field is the ongoing mystery surrounding the role of dark matter in galactic formation. It is widely accepted that dark matter constitutes a significant portion of the universe's mass, yet its precise influence on the formation and structure of galaxies remains elusive. Researchers are investigating how variations in the distribution of dark matter could affect everything from the shape and size of galaxies to their very existence. This line of inquiry is helping to redefine the framework in which we understand the creation of galaxies, suggesting that dark matter may play a more active role than initially suspected. At the same time, the exact conditions that trigger star formation within galaxies are far from understood. While it is clear that stars are born from the gas and dust present in galaxies, the specific factors that spark the birth of new stars remain unclear. Astronomers are now exploring a variety of possible influences: magnetic fields, shockwaves from supernovae, and even interactions with neighboring galaxies, each of which could either promote or hinder the formation of stars. Understanding how these elements come together to create the stars that populate our universe is a crucial step in deciphering the mechanics of galaxy evolution. The evolutionary pathways of galaxies themselves present another set of complex questions. For instance, how do galaxies interact and merge over cosmic timescales, and what are the long-term consequences of such events on their morphology and behavior? Collisions and mergers between galaxies are known to produce dramatic transformations, but the precise mechanisms governing these interactions are still a matter of ongoing investigation. These processes not only reshape the structure of the galaxies involved, but also contribute to the larger cosmic narrative of the universe's evolution. The role of supermassive black holes at the centers of galaxies adds yet another layer of complexity. These enigmatic objects exert a profound influence on the stars and matter surrounding them, potentially altering the behavior and evolution of entire galaxies. Understanding the relationship between supermassive black holes and their host galaxies is crucial for a comprehensive picture of galactic evolution, yet many questions remain unanswered. Finally, the impact of the cosmic environment on galaxy formation is still far from being fully understood. Different regions of the universe, such as dense galaxy clusters and vast empty cosmic voids, exhibit distinct characteristics that shape the galaxies within them. How these diverse environments influence the growth and evolution of galaxies is an area of active research. Some regions may foster the rapid formation of stars, while others may suppress it, leading to dramatically different galactic structures. Studying these variations is essential to gaining a holistic understanding of the universe's grand design and the forces that have shaped it throughout cosmic history. In tandem with these broader investigations into galactic and stellar evolution, one of the most fundamental challenges in astronomy remains the measurement of cosmic distances. Techniques such as parallax, used for measuring distances to nearby stars, and standard candles like supernovae, utilized for more distant objects, each come with their own set of uncertainties. These challenges are magnified when measurements yield inconsistent results, forcing scientists to re-examine existing models of the universe. For example, astronomers once placed considerable faith in the assumption that the universe's expansion rate, quantified by the Hubble constant, was constant and uniform across time and space. However, discrepancies in measurements have raised doubts about this long-standing belief, urging the scientific community to reconsider the very nature of cosmic expansion. As more advanced technologies come online, and as our ability to observe and measure the universe improves, astronomers are increasingly forced to confront these inconsistencies. In doing so, they are gradually refining our understanding of the universe's true scale and evolution, and perhaps even reshaping our vision of the cosmos as a whole. These ongoing discoveries, fueled by technological advancements and breakthroughs in observational techniques, continue to reveal the universe as a dynamic and ever-changing entity. Every new finding adds another piece to the cosmic puzzle, gradually bringing us closer to unraveling the profound mysteries of our universe, its origins, and its ultimate fate. As our capacity to observe the universe expands, so too does our understanding of the intricate and interconnected processes that govern the life cycles of stars, galaxies, and the universe itself. The journey is far from over, and each discovery propels us further into the unknown, urging us to reimagine what we thought we knew about the vast and wondrous cosmos. However, discrepancies in distance measurements have sparked a wave of debate within the scientific community, as they reveal a fundamental inconsistency in our understanding of the universe's expansion. These inconsistencies, apparent in the differing values derived from observations of the early universe, such as the cosmic microwave background, CMB radiation, and those obtained through more recent supernova data, suggest that our model of cosmic expansion might need a significant overhaul. What was once considered settled science is now being called into question. The mismatch in measurements is not simply a matter of academic curiosity. It could hold far deeper implications for our understanding of the cosmos. These discrepancies might point to unknown aspects of physics, possibly hinting at the influence of dark energy, or even the emergence of phenomena we have yet to conceptualize. Such revelations could alter our perception of the fundamental forces that govern the universe. It is possible that some of these inconsistencies arise from limitations in the methods used to measure cosmic distances. As our observational tools and technological techniques continue to evolve, it is likely that we will uncover more accurate measurements that refine our understanding. New technologies and advanced telescopes are steadily increasing the precision with which we can gather data about the universe. These tools, including cutting-edge, space-based observatories, allow scientists to observe cosmic phenomena with far greater clarity than ever before. As the resolution of our measurements improves, so too does our ability to challenge previously held theories. And this iterative process of refinement enriches our comprehension of the universe's vast expanse. What is becoming increasingly evident is that each new discovery, whether it strengthens our current theories or compels us to reconsider them, brings us closer to a deeper understanding of the fundamental nature of reality. These moments of scientific breakthrough offer more than just data. They open doors to new possibilities, reshaping how we think about everything from the birth of the universe to the ultimate fate of distant galaxies. Each reevaluation and recalibration of our methods and ideas not only improves the accuracy of our measurements, but also offers a clearer view of the laws that govern the cosmos, helping us unlock the secrets of space itself. Turning our gaze to Mars, we find a world whose surface is shaped by dramatic geological features that continue to captivate the imagination of scientists and theorists alike. Among these is Olympus Mons, the largest volcano in the entire solar system, towering nearly 25 kilometers high. It stands as a silent sentinel, its presence a reminder of the planet's violent geological history. Mars also boasts an intricate network of canyons and river-like channels, evidence of ancient hydrological activity that suggests liquid water once coursed over its surface. These features lead to tantalizing questions about Mars's potential for life and its dramatic transformation over billions of years. The features of Mars's surface, volcanoes, canyons, and riverbeds, are not just relics of ancient geological processes. They prompt us to consider whether Mars once harbored conditions that could have supported life. Could this planet, now dry and cold, have been home to an ecosystem in its distant past? Or have these features been shaped over time by volcanic eruptions and relentless wind erosion, slowly erasing any trace of a more hospitable climate? These questions are not mere curiosities. They strike at the heart of our desire to understand the evolutionary path of planets and whether life can exist elsewhere in the cosmos. Another fascinating feature of Mars is its polar ice caps, which are composed of a mix of frozen carbon dioxide and water ice. These ice caps are far more than just geological curiosities. They undergo seasonal fluctuations that reveal critical insights into the planet's climate dynamics. As the ice caps expand and contract, they offer clues about Mars's changing atmospheric conditions over time. Moreover, the presence of ancient lake beds and minerals that form only in the presence of liquid water lend further weight to the theory that Mars once had a much wetter and warmer environment than the arid world we see today. Mars's history, however, is not solely a story of ancient climates. In recent years, scientists have detected evidence of transient liquid water on the Martian surface, particularly briny flows that appear during the warmer seasons. These ephemeral water flows have reignited questions about the potential for microbial life on the planet. Could microbes exist in the planet's harsh conditions, hidden in the depths of its arid soil, or clinging to the briny streaks of water that appear seasonally. The possibility that life once or still exists on Mars is a topic that continues to provoke both excitement and skepticism. The diversity of terrain on Mars, from its towering volcanoes to its vast plains and deep canyons, combined with a variety of meteorological phenomena, paints a picture of a planet in flux. This broad spectrum of characteristics invites a range of scientific theories, from ideas about how Mars's climate shifted over time to speculations about its potential to support life. Every new rover mission, every new data set collected, not only sharpens our understanding of Mars's past, but also fosters new questions about its future and ours. As we continue to explore Mars, we are not only peering into the history of another world, but into the possibilities for humanity's own place in the cosmos. Shifting focus to the mysteries of black holes, we encounter one of the most awe-inspiring phenomena in the universe: supermassive black holes. These behemoths, often found at the centers of galaxies, can weigh as much as millions or even billions of suns. Their gravitational pull so powerful that not even light can escape it. But despite their sheer size and influence, the origins of these supermassive entities remain elusive. How did they form? What processes led to their immense growth? These questions have captured the attention of astrophysicists and remain at the forefront of modern research. One widely accepted theory is that supermassive black holes might have formed from the collapse of massive gas clouds in the early universe. As these clouds collapsed under their own immense gravity, they could have given birth to clusters of stars, which in turn might have merged, growing larger and larger until they formed the black holes we observe today. However, this theory does not yet explain all the features of supermassive black holes, leaving room for further exploration. The processes behind their formation remain one of the great unsolved mysteries in the field of astrophysics, compelling researchers to continue searching for answers that might one day reveal the true nature of these enigmatic giants. In both cases, the measurement of cosmic distances and the study of black holes, we see a common theme emerge: the search for deeper understanding. In the same way that discrepancies in distance measurements challenge our grasp of the universe's expansion, the mysteries of black hole formation force us to reconsider the fundamental processes that govern the cosmos. Whether studying distant galaxies or the surface of Mars, every new piece of data leads us closer to unraveling the complex web of cosmic phenomena. And in doing so, we come closer to answering some of the most profound questions humanity has ever asked. How did we get here? What is our place in the universe? And what lies beyond the horizon of our current knowledge? The pursuit of these answers is what drives scientific discovery forward, revealing a universe more vast and mysterious than we could ever have imagined. The timeline and mechanics behind the formation of supermassive black holes remain an area of intense scientific inquiry. Despite numerous theories, there are still many unanswered questions about how these cosmic giants came into existence. One particularly fascinating possibility revolves around the role of smaller black holes in the early universe, shortly after the formation of the first stars. It is hypothesized that some of these early stars, in their final stages, exploded in supernova, leaving behind small black holes in their wake. Over time, these black holes may have merged with others or accumulated surrounding gas and dust, gradually growing in mass. This process, known as accretion, could have led to the formation of supermassive black holes, the very objects that we observe at the centers of galaxies today. However, this theory hinges on a series of complex factors. The efficiency of the merging events and the rate at which black holes could accrete material are crucial components of the equation. Moreover, the dynamics within these early galaxies, including how matter was distributed and how quickly it was available for accretion, play a significant role in determining whether such growth was even possible. The environment surrounding these black holes also matters greatly. Galaxies are not isolated. They interact with one another, often merging to create conditions that could accelerate the growth of supermassive black holes. During such galactic mergers, gravitational interactions can funnel gas and stars into the heart of the new galaxy, further feeding the black holes at its core. Despite the compelling nature of these theories, the exact pathways and timescales for black hole formation are still unknown, and astronomers continue to explore various models. Adding to the complexity is the challenge of observing these processes directly. While telescopes are adept at detecting the luminous activity surrounding black holes, such as the bright jets and accretion disks formed by the infall of matter, the early stages of black hole formation remain elusive. This makes studying their formation process a difficult task, as the key moments of growth may occur in regions of space too distant or too faint to be captured by current technology. Nevertheless, understanding how supermassive black holes form not only unveils the mysteries of these fascinating objects, but also offers invaluable insights into the evolution of galaxies themselves. The formation of these black holes is deeply intertwined with the history of the cosmos, revealing a complex and intricate story of galactic growth, star formation, and cosmic interactions that continue to shape the universe as we know it. In parallel with the mystery of black hole formation, the discovery of dark energy has revolutionized our understanding of the universe's future. Dark energy is an enigmatic force that constitutes roughly 70% of the total energy content of the cosmos. Its primary effect is the accelerated expansion of the universe, a phenomenon that defies traditional expectations. Given that gravitational forces generally pull matter together, the acceleration of the universe's expansion implies that dark energy exerts a repulsive force, overpowering the attractive force of gravity. One of the most intriguing aspects of dark energy is its potential role in determining the ultimate fate of the universe. If dark energy remains constant over time, the universe will continue to expand indefinitely, leading to a scenario known as the Big Freeze. In this future, galaxies will drift further apart, stars will burn out, and temperatures will gradually approach absolute zero. The universe will become a cold, dark, and lifeless place, with no new events or phenomena emerging. This grim outcome raises profound philosophical questions about the nature of existence and the eventual end of time itself. However, some theories propose that dark energy might evolve over time, leading to a variety of possible cosmic fates. If dark energy were to grow stronger, it could eventually tear apart galaxies, stars, planets, and even atoms in a scenario called the Big Rip. In this dramatic end to cosmic structures, everything in the universe would be pulled apart, marking the end of matter as we know it. These possibilities underscore the unpredictability of the universe's evolution and highlight how little we truly understand about dark energy's role in shaping the future. The study of distant supernovae, cosmic microwave background radiation, and large-scale structures in the universe holds the key to unraveling the mysteries of dark energy. Each new discovery brings us one step closer to understanding how the universe will evolve, shedding light on the fundamental forces that drive its expansion. In many ways, the exploration of dark energy not only impacts our understanding of the cosmos, but also raises profound existential questions about the fate of the universe and our place within it. Humanity's quest to comprehend the cosmos has deeply influenced our culture, art, and creativity, igniting the imagination of generations. Early civilizations, for example, looked to the stars for guidance, developing calendars and navigation systems based on celestial movements. This reliance on the heavens laid the foundation for astronomical knowledge, while also embedding the cosmos into the myths and cultural practices of ancient societies. From the Egyptians, who aligned their pyramids with the stars, to the Polynesians, who used the night sky to navigate vast oceans, the cosmos has been a source of wonder and meaning. During the Enlightenment, figures like Galileo Galilei revolutionized our understanding of the universe. By challenging the long-held belief in a geocentric cosmos and advocating for a heliocentric model, Galileo set the stage for a seismic shift in scientific thought. This new perspective not only spurred advancements in astronomy, but also inspired philosophical inquiry, leading to a greater understanding of the universe's vastness and complexity. Artistic movements during this period reflected this newfound knowledge of the cosmos. Artists such as Vincent van Gogh, whose iconic works captured the vastness and mystery of the night sky, reflected humanity's growing fascination with space. The influence of the cosmos extended into literature as well. Writers like H.G. Wells and Arthur C. Clarke used the concept of space travel and extraterrestrial life to explore the limits of human imagination, pushing the boundaries of what was possible in both science and fiction. The desire to understand the universe and its mysteries led to the creation of stories that were not only speculative, but also visionary, touching upon themes of exploration, discovery, and the unknown. The space age, which began in earnest with the moon landing of 1969, further intertwined human culture with the cosmos. This momentous achievement united people around the world in a shared sense of wonder and accomplishment, transforming what was once the realm of science fiction into reality. The successful landing on the moon served as a symbol of human ingenuity and the boundless potential of exploration. In the years that followed, the genre of space-related music, art, and literature flourished, capturing the essence of humanity's yearning to explore the unknown. These creative expressions reflected our collective desire to reach beyond the confines of Earth and venture into the stars. Today, as we continue our journey into space, our understanding of the cosmos continues to evolve. The development of advanced technology, including powerful telescopes and robotic probes, has expanded our ability to explore distant worlds, uncovering new mysteries about the nature of the universe. Each new discovery, from the detection of exoplanets to the study of cosmic radiation, sparks curiosity and wonder, fueling a new generation of artists, scientists, and dreamers. In this way, space exploration remains a central theme in human culture, continuously shaping our collective identity and inspiring creativity across all fields of endeavor. Space exploration also has profound psychological implications, particularly for astronauts who experience extended periods of isolation and confinement. The challenges of living and working in space for long durations can lead to feelings of loneliness, homesickness, and even psychological stress. The vast distance from Earth and the separation from loved ones amplify these emotions, making it essential for astronauts to have strong psychological support systems in place. Ensuring their mental well-being is just as crucial as their physical health, as the harsh conditions of space demand resilience and adaptability. In the high-pressure environment of space missions, astronauts are confronted with unique psychological challenges that can lead to significant stress and anxiety, particularly during the most critical phases of a mission, such as launch and re-entry. The isolation inherent in space travel can intensify these emotions, as astronauts operate within a confined, self-contained environment, far removed from the familiar social interactions and support networks they would experience on Earth. The absence of normal human contact, such as conversations with family, friends, or colleagues, can magnify feelings of loneliness, isolation, and mental strain. To mitigate these risks, space agencies implement various strategies aimed at preserving the mental health and well-being of their astronauts. This includes regular psychological evaluations and mental health check-ins during their missions. Additionally, astronauts undergo extensive psychological training before embarking on their journeys, which equips them with coping mechanisms for dealing with stress, anxiety, and the challenges of isolation. The goal is to ensure that they are mentally prepared for the demanding conditions they will face, both during their mission and in the preparation phase. Interestingly, some astronauts report that their experiences in space, particularly when viewing Earth from orbit, can lead to a profound sense of awe and perspective. Known as the overview effect, this phenomenon involves a heightened sense of purpose and focus, often accompanied by feelings of connection to humanity and a deep appreciation for the fragility of our planet. Witnessing the Earth from space can be a transformative experience, reducing feelings of isolation and sparking a renewed sense of well-being. This shift in perspective can significantly enhance an astronaut's mental state, providing them with a sense of connectedness that transcends the physical isolation of their environment. As space exploration ventures further into the cosmos, understanding and addressing the psychological effects of space travel will become increasingly important. Future missions to distant destinations, such as Mars or beyond, will require astronauts to not only be physically fit, but also mentally resilient. Preparing astronauts for the mental challenges of long-duration space travel will be crucial for the success of these missions, ensuring that crew members can thrive in the harsh, unforgiving conditions of space. In addition to supporting astronauts, Space agencies also play a key role in educating the public about space and fostering a greater understanding of the cosmos. Through a variety of outreach programs, these agencies engage with people of all ages, offering access to knowledge about celestial phenomena, space exploration, and the fundamental principles of astrophysics. Public lectures, seminars, and workshops provide valuable opportunities for experts to share their insights and knowledge with a wider audience, often sparking curiosity and inspiring future generations to explore the wonders of space. The advent of digital technology has revolutionized how space agencies communicate with the public, enabling them to reach a broader and more diverse audience. High-quality documentaries, live streams of rocket launches, and immersive virtual reality experiences allow viewers to experience space exploration in ways that were once unimaginable. Social media platforms further amplify these efforts, providing space organizations with a direct and immediate means of sharing real-time discoveries, captivating imagery, and groundbreaking research with millions of people around the world. Additionally, space agencies often collaborate with schools and educational institutions to promote STEM, science, technology, engineering, and mathematics, education. These partnerships provide valuable resources such as lesson plans, interactive exhibits, and special events designed to foster a deeper understanding of space science. Programs targeting both teachers and students help cultivate a sense of wonder and curiosity about the universe, inspiring young minds to pursue careers in the field of space exploration. By making space science more accessible, these initiatives play a crucial role in shaping the future of space exploration. Citizen science projects also contribute to public engagement by allowing individuals to actively participate in scientific research. Volunteers are invited to contribute to various initiatives, such as classifying star types or tracking asteroids. This hands-on involvement not only enhances public understanding of space, but also builds a global community united by a shared passion for uncovering the mysteries of the universe. Citizen science programs create a sense of ownership and connection, encouraging individuals to become more invested in the scientific discoveries that shape our understanding of the cosmos. Space agencies, through their diverse efforts, continue to spark curiosity, ignite the imagination, and inspire a sense of wonder about the vastness of space. They provide a platform for people from all walks of life to connect with the wonders of the universe, fostering a deeper appreciation for the unknown and the endless possibilities that lie beyond our planet. Art plays a pivotal role in bridging the gap between the complexities of cosmology and the human experience. While scientific research and data can provide us with detailed information about the universe, art captures the emotional, aesthetic, and often incomprehensible aspects of space. Through visual representation, artists evoke the awe and wonder inspired by the vastness and mystery of the cosmos. By using bold colors, imaginative landscapes, and captivating imagery, artists take viewers on journeys that stretch beyond the boundaries of our planet, illustrating the beauty of celestial bodies, galaxies, and the intricate dance of cosmic phenomena. The creative interpretation of space allows audiences to engage with abstract scientific concepts in a way that is both visually stunning and intellectually stimulating. Complex ideas such as black holes, distant nebulae, and the curvature of space-time are transformed into tangible, relatable representations that invite contemplation. Through the lens of art, phenomena that may be difficult to understand in purely scientific terms become vivid and accessible, offering a unique perspective on the universe. Art also fosters collaboration between artists and scientists, leading to innovative projects that merge the two disciplines. For example, animations and digital creations can visualize phenomena that are impossible to observe directly, such as the formation of stars or the collision of galaxies. These visualizations play a crucial role in educating the public about scientific advancements, making abstract ideas more comprehensible and engaging. As a result, art becomes a powerful tool for communicating complex scientific concepts to a wider audience, enriching our collective understanding of the universe. Ultimately, the intersection of art and cosmology enhances our appreciation of the cosmos and inspires curiosity about the mysteries that lie beyond our world. By capturing the awe and wonder of space, Art encourages us to explore ideas that extend beyond the limitations of data and equations, igniting a desire to learn more about the universe and our place within it. Art helps demystify the vastness of space, fostering a sense of connection to the cosmos and inspiring a deeper, more personal engagement with the exploration of space. Education in astronomy serves as a powerful catalyst for inspiring the next generation of scientists, engineers, and explorers. By studying the universe, students develop an appreciation for the vastness of space and the intricate processes that govern the movement of celestial bodies. This knowledge sparks curiosity and encourages young learners to ask important questions about the nature of space-time, the origins of the universe, and the physical laws that govern our existence. Astronomy education often begins with a sense of wonder, as students look up at the night sky and are captivated by the beauty of stars, planets, and distant galaxies. With the help of telescopes, planetarium visits, and interactive teaching methods, students gain a more tangible understanding of the cosmos, fostering a deeper connection to the universe. The opportunity to conduct hands-on experiments and work with advanced technology allows students to engage with scientific principles directly, making abstract concepts more accessible and relatable. Collaboration and teamwork are integral aspects of astronomy education. Through group projects, competitions, and community outreach activities, students learn to work together toward common goals, whether it's identifying exoplanets or tracking asteroids. These shared experiences help build a sense of accomplishment and belonging, motivating students to pursue further studies in the field of space science. The excitement of participating in national events, such as solar eclipses or the launch of Mars rover missions, serves as a tangible reminder of the impact their efforts can have on the world of scientific discovery. By inspiring young minds to explore the universe, astronomy education paves the way for future advancements in space exploration and science. It fosters a generation of thinkers, innovators, and problem solvers, ensuring that humanity will continue to reach for the stars and uncover the mysteries of the cosmos for generations to come. In the ever-evolving world of space exploration, renowned figures such as astronauts, astrophysicists, and space engineers serve as beacons of inspiration for the next generation of scientists. Their stories are not just tales of distant stars or unknown planets, they are narratives of resilience, innovation, and daring exploration. These individuals have not only mastered the laws of the universe, but have also paved the way for students to envision a future where their education can lead to revolutionary discoveries or even interplanetary journeys. Their journeys prove that a career in astronomy is not a far-off dream, but a tangible goal that can lead to extraordinary contributions to humanity. When young minds hear the stories of pioneers like these, whether it's the first astronaut walking on the moon or a groundbreaking discovery about a distant galaxy, they are encouraged to dream without limits. These stories highlight the possibilities that lie in the realm of space science and the wonders it holds. They reveal that space exploration is not just for the privileged few, but a field that can be accessed by anyone with curiosity, determination, and a love for the unknown. This narrative is vital in shaping the aspirations of future scientists, innovators, and explorers, making astronomy an indispensable pillar in the development of the next generation of intellectual pioneers. In addition to personal success stories, storytelling itself has proven to be a powerful method of engaging the public with the mysteries of space. It allows complex scientific concepts to be presented in a way that is both approachable and emotionally resonant. By framing astronomical discoveries and cosmic phenomena within the context of a grand narrative, storytelling invites audiences to see themselves as part of a larger, interconnected story. This transforms abstract science into something deeply human, an adventure of discovery that everyone can be a part of. Imagine, for instance, a scientist describing the search for life beyond Earth, not just as a series of equations or data points, but as a personal journey filled with obstacles, triumphs, and moments of wonder. This shift from dry scientific facts to a narrative driven by personal experience makes the research process more relatable, humanizing the figures behind the discoveries. Instead of simply recounting figures and data, scientists can share the human side of their work, the doubts, the challenges, the eureka moments, By doing so, they turn themselves into explorers, embarking on a thrilling quest akin to that of the heroes in an epic adventure. This kind of storytelling encourages viewers to see scientists as more than just researchers. They become part of an ongoing quest to understand the universe and our place within it. These narratives often tap into universal themes, such as humanity's age-old search for life beyond Earth, or the quest to understand the fundamental laws of the cosmos that resonate on a deeply personal level. These themes mirror the human experience of exploration and discovery, themes that have been part of our collective story for centuries. As people hear these stories, they are more likely to see their own personal aspirations reflected in the pursuit of scientific knowledge. This deep connection fosters a broader and more passionate engagement with the field of space science. The pursuit of answers to questions about the universe becomes not just a scientific endeavor, but a shared human experience, one that speaks to our collective desire to understand the unknown. Moreover, the medium through which these stories are told, be it through documentaries, films, or immersive experiences, plays a crucial role in making the abstract tangible. Stunning visuals of space, planets, stars, black holes, paired with animated simulations of complex phenomena, can make these scientific concepts come alive. The combination of rich, awe-inspiring imagery and compelling storytelling engages the audience, turning what might seem like cold, hard science into something beautiful and approachable. These visuals, when paired with the stories of exploration, offer a glimpse into the vast unknown that both excites and comforts. They invite viewers to journey into the cosmos with a sense of wonder and curiosity, providing an opportunity to explore the wonders of the universe with renewed enthusiasm and a sense of purpose. Finally, the impact of space exploration extends beyond individual discovery. It has significantly altered the landscape of international cooperation and diplomacy. As nations venture beyond the boundaries of Earth, they often find common ground in the shared pursuit of understanding the cosmos. In the face of the infinite vastness of space, political differences seem small, and collaboration becomes not only possible, but essential. The International Space Station, ISS, serves as a prime example of this cooperation, where astronauts from multiple nations live and work together in space, transcending political divisions in the name of science and discovery. This collaborative spirit is one of the hallmarks of space exploration, a testament to humanity's ability to unite for a common cause. Through shared missions and global partnerships, space exploration fosters relationships built on mutual respect, knowledge sharing, and the collective hope of unlocking the secrets of the universe. In conclusion, the role of storytelling in space exploration cannot be overstated. It serves as a bridge, connecting the vastness of space with the human experience, making the pursuit of knowledge not just an intellectual endeavor, but a collective journey. Whether through the inspiring stories of individuals, the emotional power of shared narratives, or the stunning visuals that bring the cosmos to life, storytelling has the power to captivate, engage, and inspire. It transforms space exploration from a scientific pursuit into a shared adventure that resonates with all of us, reminding us that we are all part of the same cosmic story. Space exploration has long been a symbol of human ambition, curiosity, and unity. Yet its influence reaches far beyond the confines of rocket launches and astronomical discoveries. As nations collaborate on missions to distant planets, the shared challenges of space exploration foster a profound sense of international solidarity. Issues like satellite navigation, climate monitoring, and planetary defense against potential asteroid impacts are not just technological hurdles, they are global concerns that necessitate cooperation. Through international treaties and agreements, countries have established frameworks for collaboration that address not only the scientific objectives, but also the ethical and legal dimensions of space activities. These treaties and frameworks serve as guidelines, establishing norms that promote peaceful exploration of outer space. Rather than fueling competition or conflict, they lay the groundwork for a cooperative approach to exploring the cosmos. The significance of these agreements extends far beyond the science itself. They help to ensure that space is used for the collective benefit of all, with a focus on peaceful and responsible exploration. In this context, space achievements transcend technical milestones. They become symbols of collective human effort, reinforcing the idea that we are all part of something greater than ourselves. The diplomatic power of space exploration also plays a pivotal role in shaping global relations. As countries like China and India make significant strides in space technology, they do more than just showcase their scientific prowess. These nations use their space accomplishments to bolster their standing on the global stage, signaling their growing influence and gaining respect from the international community. Their successes not only highlight technological advancements, but also serve as invitations for partnerships, fostering a spirit of collaboration. This dynamic has a ripple effect, encouraging other nations to engage in scientific research that transcends political and cultural differences. In a world often divided by geopolitical tensions, the collaborative nature of space exploration is a poignant reminder of our shared humanity and our collective curiosity to understand the universe. As we embark on missions to the Moon, Mars, and beyond, the spirit of international cooperation is likely to grow even stronger. The prospect of establishing lunar bases or sending humans to Mars offers a unique opportunity for countries to join forces in ways that could address pressing challenges, both in space and on Earth. Whether it's the pursuit of new resources, the development of cutting-edge technologies, or the exploration of other planets for the sake of humanity's future, the challenges of deep space exploration have the potential to unify nations in a common cause. Yet, the human side of space exploration cannot be overlooked. Astronauts, through their personal narratives, provide a deeply relatable connection to the otherwise technical and abstract world of space exploration. Their stories resonate with audiences on Earth, offering a glimpse into the emotional and psychological challenges of life in space. When astronauts speak about the awe they feel gazing at Earth from orbit, or the loneliness they experience during long missions, their words transcend the realm of scientific data. These personal reflections draw us into their experiences, making space exploration not just a scientific endeavor, but a deeply human one. For example, many astronauts recount the profound moment when they first saw Earth from space, often describing it as a thin blue line against the vastness of the cosmos. This image, both beautiful and fragile, serves as a powerful reminder of the vulnerability of our planet. These moments of reflection evoke a sense of responsibility and urgency to protect our world, transforming the exploration of space from a purely scientific pursuit into a collective human endeavor. Astronauts often emphasize the importance of environmental stewardship, inspiring individuals to take a more active role in safeguarding the Earth. Furthermore, the personal sacrifices made by astronauts highlight the human cost behind space exploration. Time away from family and friends, the strain of living in isolation for extended periods, and the physical toll of space travel underscore the dedication required for such missions. These stories not only shed light on the resilience and determination needed to succeed in space, but also remind us that the advancements we see in space technology are the result of real human effort. Behind every technological breakthrough is a person facing obstacles and overcoming adversity. This human element deepens our appreciation for space exploration, transforming it from a distant, impersonal science to something that is intricately connected to the human experience. The struggles of early pioneers in astronautics are rich with tales of perseverance, risk, and vision. Figures like Robert Goddard and Wernher von Braun faced enormous challenges in their pursuit of space travel. They battled skepticism from the scientific community, grappled with limited resources, and confronted the constant threat of failure. Many of their ideas were considered radical or impractical, and they often risked both their careers and reputations to push forward with their dreams. In the early days of space exploration, safety was a significant concern. Many of the rocket prototypes tested by pioneers exploded or malfunctioned, resulting in injuries or fatalities. The tragic loss of astronauts during these early missions underscored the immense risks involved. Yet, it was through these setbacks that critical lessons were learned, contributing to advancements in both safety protocols and technology. These early failures were not signs of defeat, but stepping stones toward greater successes. Political leadership also played a crucial role in shaping the trajectory of space exploration. Figures like President John F. Kennedy galvanized public and governmental support for space endeavors, framing the challenge of landing a man on the moon as both a political competition with the Soviet Union and a demonstration of human ingenuity. This political backing was instrumental in securing the funding and resources necessary for space exploration to advance at a rapid pace. The blending of personal ambition, societal challenges, and political dynamics created the perfect storm for the realization of space travel. The stories of these early pioneers are not just about triumph, but about the resilience of the human spirit. They illustrate the willingness to confront fears, learn from failures, and pursue the extraordinary, transforming the dream of space travel into a reality. This narrative continues to inspire future generations of scientists, engineers, and dreamers who believe in the potential of space exploration to transform our world. In addition to the technological and human elements of space exploration, the role of media in shaping public perception cannot be underestimated. Through movies, documentaries, and television programs, the portrayal of space has captured the imagination of millions. Films like Interstellar blend scientific principles with compelling storytelling, making complex concepts like black holes and time dilation accessible to a wider audience. These representations ignite curiosity, prompting viewers to explore real scientific phenomena and consider deeper questions about the universe, extraterrestrial life, and our place in the cosmos. Media also dramatizes the stakes of space exploration, often framing scientific events with a sense of urgency and importance. This dynamic helps shift discussions from being abstract or technical to something that feels immediate and relevant. By weaving narratives of heroism, innovation, and discovery into the fabric of space exploration, media outlets help fuel public interest in the sciences and underscore the importance of continuing to push the boundaries of human knowledge. In this way, space exploration transcends its technical roots to become a shared cultural pursuit, one that inspires people from all walks of life to look to the stars and dream of what might be. Documentaries that feature extraordinary images from telescopes or space missions are more than just captivating visuals. They serve as a bridge connecting us to distant galaxies, stars, and the unknown expanse of space. Through these breathtaking images, whether it's the glowing rings of Saturn or the mesmerizing swirl of a far-off galaxy, viewers experience a sense of awe and wonder. These visuals, potent in their simplicity and grandeur, not only educate the public but inspire action. They motivate individuals to get involved with the scientific community, attend lectures, or join stargazing events, sparking a deep curiosity that goes beyond passive viewing. As the camera zooms in on the awe-inspiring landscapes of space, it's not just about spectacle, it's about creating a connection. The stunning imagery of celestial bodies can evoke emotions that transcend the screen, stirring a sense of exploration that has been part of human nature for millennia. This visual stimulation encourages a profound engagement with science. It fuels our desire to understand the mysteries of the universe, inviting us to ask questions and consider the unknown. The role of media representations, particularly in the context of space exploration, extends far beyond entertainment. These portrayals blend fact with imagination, creating a space where scientific knowledge meets the human thirst for adventure and discovery. Through this dynamic fusion, the media helps shape our collective understanding of the cosmos, inspiring us to explore, to wonder, and to dream. Moreover, these portrayals influence our perceptions of what is possible, urging us to continue questioning our place in the universe. This drive for curiosity and discovery is fundamental to human progress, and documentaries provide a powerful catalyst for this ongoing journey. As we watch, learn, and imagine, we contribute to a growing cultural understanding of space, one that pushes us to confront the complexities of the universe and consider the vast unknowns that lie beyond our comprehension. At the forefront of these mysteries are two profound cosmic phenomena: dark matter and dark energy. Together, they account for about 95% of the universe's total energy content, yet remain largely undetectable by traditional scientific methods. Dark matter, invisible and enigmatic, does not interact with electromagnetic radiation in any measurable way, making it nearly impossible to study directly. However, scientists believe that dark matter plays a crucial role in the universe's structure by providing the gravitational framework that holds galaxies and galaxy clusters together. Without dark matter, the very fabric of the universe would unravel. On the other hand, dark energy is thought to be responsible for the accelerating expansion of the universe. As galaxies drift farther apart at increasing speeds, dark energy's influence becomes undeniable. This mysterious force is pushing the universe into an ever-expanding future, yet its nature remains shrouded in mystery. The combined understanding of dark matter and dark energy has the potential to completely transform our knowledge of the cosmos. It could change the way we think about the formation and evolution of galaxies, the behavior of cosmic forces, and the very fabric of space and time. The pursuit of knowledge about these elusive phenomena is one of the most exciting frontiers in modern science. Through advanced particle physics and cutting-edge cosmological observations, scientists are working tirelessly to uncover the truths hidden within these fundamental aspects of the universe. Decoding the secrets of dark matter and dark energy could not only reshape our understanding of the universe's origins, but also radically alter our concepts of physics, opening up entirely new realms of possibility. This quest to unlock the secrets of the cosmos is not just an intellectual pursuit. It is a journey that could revolutionize our understanding of existence itself. The more we uncover, the more we realize how much we still do not know, fueling a relentless drive to push forward. Each discovery brings us closer to understanding how galaxies form, evolve, and interact, revealing new layers of complexity in the universe on both large and small scales. As scientists continue to probe the depths of space, the answers to these questions will undoubtedly have profound implications for the future of physics. Understanding the nature of dark matter and dark energy could redefine our understanding of reality and challenge many of the assumptions we hold about the universe. It is the great unknown that beckons us, urging us to explore further and to ask questions that may one day reshape the very nature of existence. The scientific community faces an intriguing yet complex challenge when it comes to studying unexplained phenomena. These mysteries, whether cosmic, biological, or environmental, present both an intellectual temptation and a practical dilemma. The pursuit of these unknowns pushes the boundaries of knowledge, but it also requires a careful balancing act. Scientists must prioritize their research, allocating resources wisely while remaining driven by the hunger for discovery. This delicate balance ensures that the most promising leads are pursued with rigor while ensuring that research remains focused on questions that can fundamentally reshape our understanding of the universe. In this quest for knowledge, unexplained phenomena that hold the potential for groundbreaking discoveries often take precedence. Whether it's the search for dark matter in astrophysics or investigating new health anomalies, these mysteries drive the scientific agenda. The potential for discoveries that could change everything, from the way we understand gravity to how we might treat diseases, motivates scientists to explore these areas rigorously. These phenomena may hold the key to answering some of the universe's deepest questions, and in turn could lead to innovations that improve our daily lives. Public interest also plays a pivotal role in guiding scientific priorities when unexplained phenomena begin to touch the lives of individuals and communities, whether through unexplained health crises, environmental disasters, or societal shifts. The urgency for answers intensifies. It is during these times that the connection between science and society becomes most evident. Researchers, policymakers, and the public must work together, addressing these pressing issues in ways that drive meaningful change. These collaborative efforts can not only uncover answers to scientific mysteries, but also provide tangible solutions to real-world problems. The dynamic between scientific inquiry and societal engagement creates a powerful synergy. The public's curiosity and concern fuel the exploration of unknown phenomena, while scientific research brings new insights and solutions. In this way, the search for answers becomes a shared journey, one that not only expands our understanding of the universe, but also addresses the immediate challenges facing humanity today. The mysteries of the cosmos, once confined to theoretical questions, now have the potential to shape our present and future in ways that are both profound and transformative. In our ongoing quest to understand the vast and mysterious cosmos, one crucial truth stands out: the power of interdisciplinary cooperation. Many of the phenomena that remain unexplained cannot be neatly categorized into a single field of study. The mysteries of the universe are complex and often transcend the boundaries of any one discipline. In such instances, collaboration becomes key. When astronomers, physicists, biologists, and even psychologists work together, they bring diverse perspectives and insights that can unlock new pathways of exploration. This spirit of cooperation not only fosters innovation, but also propels us toward breakthroughs that we could never achieve in isolation. By dismantling the silos that often separate academic disciplines, the scientific community has a much greater chance of unraveling the complexities that remain hidden from us. This interdisciplinary approach is not just a practical necessity, it is a driving force that propels scientific progress forward. When different minds and expertise converge, they create a synergy that allows us to tackle the most challenging questions of our time, pushing the boundaries of knowledge and expanding our understanding of the universe. Humanity's deep-rooted desire to comprehend the cosmos goes beyond mere intellectual curiosity. It embodies a profound exploration of who we are, where we come from, and what our place in the universe might be. Each discovery, whether it's the mysterious nature of black holes, the intricate structures of galaxies, or the fundamental forces that govern the cosmos, reminds us of the endless potential for growth in our understanding of the world around us. These discoveries are not just facts, they are windows into the deeper questions that shape our existence, urging us to think beyond our immediate surroundings and ask questions that challenge the status quo. At the heart of this ongoing exploration is the willingness to question, to seek answers, and to push against the limits of current knowledge. Every breakthrough, whether small or monumental, is a result of someone daring to ask, what if and why not? This spirit of inquiry is what drives us to keep going, despite the challenges and setbacks that may come along the way. It's about embracing the unknown, knowing that each answer brings with it even more questions, each discovery opening the door to more mysteries waiting to be solved. In parallel, the exploration of the cosmos highlights a vital truth about the importance of collaboration. In the world of astrophysics, scientists, engineers, and experts from all corners of the globe combine their knowledge, tools, and resources to unlock the secrets of the universe. They work together in teams, sharing their findings and perspectives, because the complexity of the cosmos demands a collective effort. The same can be said for the challenges we face here on Earth, be it climate change, pandemics, or social inequality. The same spirit of global cooperation and shared expertise that drives cosmic exploration must be applied to address the pressing issues of our time. Only through collective action can we hope to overcome the obstacles we face on our planet. Moreover, the pursuit of understanding the universe instills a sense of humility in all who engage with it. As we study the vastness of space, with its seemingly infinite distances and the countless celestial bodies that dot the cosmos, we are reminded of our smallness in the grand scheme of things. This perspective is humbling, and it prompts us to reflect on our place in the universe, not just in terms of our own species, but in the broader context of life on Earth. The awareness that we live on a small, fragile planet floating in an endless expanse of space encourages us to act with greater responsibility toward each other and the world we inhabit. Our time on Earth may be fleeting, and our home but a small oasis in the cosmic ocean. This awareness serves as a constant reminder to cherish and preserve the planet for future generations. Equally important is the sense of wonder that arises from our exploration of the cosmos. From the theoretical possibilities of the multiverse to the puzzling mysteries of dark matter, our engagement with these concepts stirs our imagination and fosters a lifelong love for learning. This sense of wonder transcends the mundane aspects of everyday life, offering us a glimpse of something much larger and more profound than our immediate concerns. The pursuit of knowledge in this sense is not just an academic endeavor. It is a fundamental part of being human. Our innate curiosity, our yearning to explore, and our desire to understand the unknown are what make us who we are. A documentary focused on astrophysics plays a crucial role in bridging the gap between the complexities of scientific discovery and the general public. It brings the awe-inspiring beauty of the cosmos into our living rooms in a format that is visually compelling and intellectually accessible. By presenting these advanced scientific concepts in a way that is engaging and free from intimidating jargon, such a film can ignite curiosity and inspire wonder in viewers of all backgrounds. This storytelling approach not only makes the subject matter more relatable, but also fosters a deeper emotional connection with the discoveries being presented. As viewers witness the unfolding story of the universe, they are drawn into the narrative in a way that resonates personally, cultivating a sense of excitement and inspiration about the cosmos and the mysteries it holds. In conclusion, the pursuit of understanding the universe, whether through scientific collaboration, technological advancement, or simply the power of curiosity, reminds us that knowledge is a shared journey. It encourages us to think beyond ourselves, to explore the unknown, and to work together in the spirit of discovery. This is a journey that will continue for generations to come, and each step we take brings us closer to unraveling the mysteries that lie beyond the stars. Documentaries are powerful storytelling tools that not only inform, but also inspire. In the realm of astrophysics, they have become pivotal in presenting groundbreaking research and cutting-edge innovations, offering a platform for the latest discoveries and theories. These films delve deep into the world of space science, often featuring the work of prominent scientists, their dedicated efforts, and their personal narratives. By intertwining the human element within the realm of science, these documentaries create a narrative that resonates with viewers on a profound level. Audiences are introduced to real individuals, each with their own struggles, passions, and triumphs, making the science they present far more relatable. This approach not only humanizes the complex world of astrophysics, but also serves to inspire others, especially young viewers, to pursue careers in the sciences or to engage in meaningful conversations about the mysteries of the universe. As these documentaries unfold, they contribute to enriching public discourse around some of the most pressing issues of our time, such as space exploration and climate change. The educational impact is undeniable. Through a combination of expert interviews, captivating animations, and detailed visual simulations, these films break down complex scientific principles, making them accessible to a broad range of audiences, regardless of their background or level of knowledge. This clarity helps to enhance viewers' understanding of the intricate phenomena that shape the cosmos, while also boosting the retention of key concepts. Such documentaries empower their audiences by offering the tools to learn more about the universe and its implications for human existence. In educational settings, these documentaries become invaluable resources, fostering discussion and critical thinking among students and encouraging a deeper inquiry into the wonders of the cosmos. In addition to the intellectual benefits, there is also an emotional and psychological impact. The stunning imagery of distant galaxies, star formations, and cosmic events leaves a lasting impression, often evoking a sense of awe and wonder. These visual representations of the universe help viewers connect on a more personal level, reinforcing the idea that we as human beings are part of a much larger and more intricate story. This emotional connection with the universe has the power to ignite a lasting curiosity in science, leading many to develop a deeper interest in the scientific principles that govern our world. By fostering this emotional engagement, documentaries not only spark an interest in astrophysics, but also contribute to a broader cultural shift toward curiosity, exploration, and discovery. Looking to the future, one of the most exhilarating developments in space exploration is the continuous progress of human missions to Mars. Various organizations, including both governmental, space agencies, and private companies, are tirelessly working towards sending astronauts to the Red Planet. The goal of these missions extends beyond exploration. It is also about the possibility of human colonization of Mars. Exploring the Martian geology and climate is only the beginning. The ultimate ambition is to pave the way for a future where humans can live and work on another planet, a monumental leap for our species. This bold endeavor speaks not only to our innate exploratory spirit, but also to the potential for scientific breakthroughs that could redefine our understanding of life beyond Earth. Another captivating frontier in space science is the search for exoplanets, particularly those within their star's habitable zone. With the launch of sophisticated telescopes like the James Webb Space Telescope, scientists are now able to gather unprecedented data about the atmospheres and compositions of these distant worlds. The exploration of these exoplanets holds the tantalizing possibility of discovering life, perhaps in its most basic form, beyond our planet. Such a discovery would answer one of humanity's oldest and most profound questions. Are we alone in the universe? Even the detection of microbial life on an exoplanet would have extraordinary implications, radically shifting our perspective on the resilience and diversity of life in the cosmos. In parallel, the emerging field of space tourism is gaining increasing attention. What was once a fantastical dream is now on the cusp of becoming a reality. Private companies are developing cutting-edge technologies that could allow non-professional astronauts to experience space travel firsthand. Imagine the prospect of ordinary people venturing into low Earth orbit or even visiting the moon. This democratization of space has the potential to inspire an entirely new generation of scientists, engineers, and astronomers. What seemed like a distant possibility just a few years ago is now rapidly coming into focus, adding an exciting new dimension to humanity's relationship with the cosmos. Lastly, the intersection of artificial intelligence and robotics is poised to revolutionize space exploration in ways we could never have imagined just a decade ago. Today, autonomous spacecraft are capable of navigating the vastness of space, analyzing data, and making decisions without human intervention. This technological advancement opens up new possibilities for exploring the most inhospitable corners of our solar system, places like the gas giants and icy moons, where the conditions are far too extreme for human life. Through these autonomous systems, we can now venture into regions previously considered unreachable, unlocking new mysteries that could deepen our understanding of the universe. As AI and robotics continue to evolve, the potential for discovery expands exponentially, offering insights that were once beyond our wildest dreams. Through these various advancements in space exploration, the journey to uncover the secrets of the cosmos continues to captivate the imagination of people around the world. Documentaries, in their unique ability to weave together science, human stories, and stunning visuals, have the power to drive public interest in these fields, creating a global culture of curiosity and discovery. The future of astrophysics and space exploration is boundless, and with each new mission, telescope, or technological breakthrough, we inch ever closer to understanding the vast, awe-inspiring universe that surrounds us.